So it seems we're live on YouTube.
Yeah, it does work.
So it seems we're live on YouTube.
Yeah, it does work.
A bit delayed.
So it seems we're live on YouTube.
Yeah, it does work.
Yeah, everybody please turn off the loudspeaker. Everybody please turn off the loudspeaker. Yeah, or we should mute the sound on the YouTube side. Okay, cool. Yeah, it seems it's working now. Should I keep it live or should I turn it off? Hey, can anybody hear me?
Oh, I was muted. I just muted myself. I think, yeah.
The video stream seems to work, and I think we can pause it for now, figure out the Zoom,
Sure.
the TVPR Zoom, and
Background, left, right, it's coming up the wrong way round.
Oh, yeah?
Yeah.
Really? Wow. Oh, yeah.
Yes, I have started the CVPR Zoom.
Background, left, right, it's coming up the wrong
Great.
way.
Oh, yeah?
Yeah.
Really? Wow.
Okay, the streaming.
Yes, I have started the CVPR.
it's I would say we wait for Daniel to join, and then we start. I just sent him a link with the Zoom, the link to the Zoom. I guess he'll be there in a minute or so. And yeah. And I'll be back in a minute as well.
All right, unmuting.
Should we start?
Yes, please.
I think we can go ahead.
Okay. Welcome everyone to this 2-day workshop on SLAM, visual odometry, location-based services, and visual localization. Just for everyone to know, we're streaming this on YouTube, and we're also recording it. Okay, let me start by sharing my screen and giving you a bit of an intro of what we're going to do the next 2 days. Can everyone see my screen?
Yes, we can.
Wait a second. One more try. Okay, welcome again to the joint workshop on long-term visual localization, visual odometry, and geometric and learning-based SLAM. So as I said, the workshop will take place today and tomorrow. And first of all, I'd like to welcome you from all of our organizers. We have a rather large organizing team. I'm not going to go through all of the names, but want to mention Van and Go Yu Lu, who have been fundamental in organizing this workshop. In case you're wondering who I am, I'm Thorsten Sattler. I'm somewhere also on that list. So as I said, we're streaming this live on YouTube. There's also a live stream on the Zoom rooms organized by CVPR. So if you're registered for CVPR, you can also join there. For asking questions, I would suggest to use either the CVPR chats provided by the conference website or the chat of YouTube. So we will collect questions and then ask the speakers to get this in a bit more organized form. If you want to have the detailed schedule of this workshop, it's on the workshop website. And I'm also going to go through this a bit. So those times are Pacific time, so Seattle time. You find more times on the workshop website. So we're currently in the introduction part. And then we're going to have invited talks by Cremers and Davison before switching to the SLAM challenge that's part of the workshop. Then we'll have invited talks by Luca, Carlone and Simon Lucey before doing a short break. And then in the afternoon, we'll start with Tomasz Malisiewicz, followed by having contributed papers and invited talks by Shichao, Jana, Kristen, Grauman, Shuxue, Quan, and Pierre Moulon. And that will conclude the workshop for today. And then tomorrow morning we start early again, at least for in Pacific time, we will have invited talks by Andreas Geiger and Victor Prisacariu, followed by the results of the visual localization challenges that were part of this workshop. Then we'll have invited talks by Jana Kosecka and Jakob Engel, followed by a break. And then in the afternoon, we will have more invited talks: Raquel, Urtasun, Katerina, Fragkiadaki, Deva, Ramanan, Haibin, Ling, Xiaoming, Yasuyuki Matsushita, and Yingyi Ju. That actually concludes our welcome. And we are a bit early on time. Daniel, do you still need a couple of minutes? Daniel? Daniel?
We can hear you, but maybe Daniel has muted.
Yeah, Daniel. Daniel, can you hear me?
Would you like me to unmute Daniel? Oh, it seems like I couldn't unmute Daniel. Oh, now it's working. Oh, mute again. What's happening?
No, Daniel still seems to be muted.
Hi, can you hear me?
Yes, I can hear you.
Okay, sorry.
We're running a bit early, but are you ready?
Yes, I sent you a recorded version of the talk. Do you prefer me to speak live?
I think it would be preferable to speak live, yes.
Oh, okay, I didn't know.
If that works for you, we can otherwise also play the video.
Sorry, I was not prepared for that. I thought.
No problem. I mean, if you want, we can also play the video.
Just a second.
Sure.
Now let me look. Here we go. No, I'm happy to speak live. I can do that. I thought recorded video would be safer, but I'm happy to speak live. I mean, I'm here, right? Can you hear me well, everyone?
Yes.
Is the audio
quickly,
okay,
good. And then we'll start, yes?
Mm-hmm.
So it's my pleasure to introduce Daniel Cremers, who is a full professor at the Technical University of Munich since 2009 and has been working on a wide range of topics, including SLAM and visual odometry. And most of you will be familiar with LSD SLAM and direct sparse odometry. He has won starting grants, consolidated grants, and advanced grants from the European Research Council. He has won the Leibniz Prize, which is the biggest award in German academics. And of course, he organized EC 2018 in Munich, which was a very nice conference. And recently co-founded a startup called Artisense, which is doing visual odometry and SLAM solutions for industry. And yeah, Daniel, thank you very much for speaking at our workshop.
Okay, thank you, Torsten. Thank you for inviting me. It's a pleasure to be here. Let me see how to share my screen here. I think this, if you see something, let me know if it works. Just a second. Yes, now let me go to full screen. Do you see my screen?
Yes,
Yes.
we can.
Yes?
Yeah.
Okay, very good. So thank you again for the introduction. It's a pleasure to be part of this, my first virtual workshop. So I don't know how it works. I hope you can all see me. If you cannot see or hear, then let me know and I can try to fix it. So this is a talk on deep direct virtual SLAM. The work that I'm presenting has been done in a collaboration between TU Munich and the startup that you mentioned, Artisans. And so it's an effort between these two groups. Most of the work I'm presenting has been done by current and former members of my team, in particular Nan Yang, Lucas from Stumberg, Roy Wang, Jakob Engel, and Jörg Stückler. SLAM is a long-standing problem, often called structure from motion, structure and motion. There's different terms that, depending on who you listen to, have slightly different meaning. But essentially, the aim is to recover camera motion and 3D structure of our world. This is a very long-standing problem. Here, for example, is one of the pioneers, an Austrian mathematician by the name of Erwin Kruppa. And back more than 100 years ago, he proved that if this classical result that many of you know, if we observe 5 corresponding point pairs in 2 images, then we can recover camera motion and 3D structure of these points. And this is undoubtedly a pioneering result that paved the way for later computer vision and led to what I would often call the classical pipeline of camera-based reconstruction. And if we look at this pipeline, we see that it does follow Kruppa's pioneering work in fairly closely. We start, as Kruppa said, with 2 images. So we take 2 images. Then Kruppa said we need points, so we extract points. Then Kruppa said we need corresponding points. So we try to identify correspondences, typically by descriptor matching using SIFT, SURF, BRIEF, or more recently some deep learning-based descriptors. And then, if the descriptor matching doesn't work sufficiently, we can subsequently deploy techniques like ransack that kind of alternatingly do model estimation and correspondence estimation. Once we have a good set of corresponding points, then we can run reconstruction by, for example, bundle adjustment or something like that to determine camera motion and 3D structure. And there's, we all know, quite a number of really groundbreaking works that do that in a quite impressive manner. Nevertheless, I think one should always question prior research, and in particular, even the pioneers. And one of the things I realized is if you buy a camera today and you switch it on, what you see are not points, but you see colors, intensities, brightness values. And it's not really obvious how to identify points and which points to select, which ones to neglect. And so invariably at the first step of point selection, we throw away a lot of potentially valuable sensor information. Moreover, once we identify correspondences, any mistakes we make in the correspondence identification, they will propagate into the results and we can not easily recover. I mean, ransack is a way to kind of recover from bad correspondences, but it's rather, tricky, rather tedious and heuristic in many ways. And so from a sensor analysis point of view, the question arises, can we not directly go from the sensory data to an interpretation in terms of a camera motion and a 3D structure? And this approach is something that we typically call direct. So going direct from the raw sensory data, the brightness values of the camera, to what we want to compute. What is the benefit of going directly? The benefit is that, anyone who works on sensor analysis can tell you that the closer you work on the raw sensory data, the more you can achieve in terms of optimality, because you don't make any heuristic abstraction steps, you don't do computations on a previous, heuristically extracted subset of points, but you use all available information. Often people say, what's really the difference? In the end, you compute points here, you compute points there. What is the difference? Well, the key difference is, you see it in the bottom blocks. In the geometric approaches, the key point-based approaches, the traditional pipeline, what we optimize in the end is a geometric reprojection error in bundle adjustment, for example. Whereas in direct methods, everything is driven from a photometric color or brightness consistency measure. Much like in optical flow estimation, brightness consistency is essentially the driving term. And what we'll see in the remainder of the talk, the better we understand the subtle variations of brightness, the more we can achieve in terms of performance, optimality in terms of precision and robustness. And in fact, what we'll see in the remainder of the talk is, first of all, I talk about direct methods and how to leverage brightness consistency to drive all estimations. And then I will show how we can leverage the power of deep networks to actually try to understand the color or brightness variations in a more thorough manner. And the better, as I said, we understand the variations of the brightness and color, the more accurate our estimates. And so the aim of the second part is how to deploy deep networks to boost the performance of direct visual SLAM approaches. So part one, direct SLAM, one of the first, and to my knowledge, the first large-scale capable direct SLAM approach, is a technique that we call LSD SLAM for large-scale direct SLAM. If you're interested, the code of this technology is online. It's become extremely popular over the last years. This is a work presented by Jakob Engel at ECCV 2014. And the method is somewhat sophisticated, so let me just give you an overview here. On the top left, we have an incoming video streaming at 30 Hertz. Then there is two components that run alternatingly. One is a tracking component that tracks the camera motion, and one is a depth map estimation component. And then these depth maps for all keyframes are fused into a coherent 3D point cloud. What makes it large scale on the top right is a similarity, a post-graph optimization. This is a technique we adopted from LiDAR-based SLAM to get a consistent trajectory. Yes, the work, as I said, was done predominantly by Jakob Engel. My main contribution was to give the name LSD SLAM, which I believe helped a little bit to make it more popular, because it's a name that seemingly sticks. But what makes it direct, maybe let me just go a little bit more into detail into the tracking component. Essentially, as I said, everything is driven by brightness consistency. So let's say we have a keyframe, and then we have a current frame, and we want to warp the current frame with a rigid body transformation, GXI, so rotation and translation, in such a way that the brightnesses for all pixels coincide. And so this here you see very nicely how we have a sum over all pixels, and then the brightness consistency is essentially the loss function here. And since we're only estimating 6 parameters, this is easily done in a coarse-to-fine linearization framework, much like in optical flow, except we only estimate 6 degrees of freedom. This is easily done in real time on a single core of a laptop CPU. And so you can use the remaining cores to do depth map estimation and also global realignment with the post-graph optimization. And then all of it is running here on this laptop, as you see on the CPU, with the camera held on the top left. Here you see some results, and at least in contrast to what was there before among real-time capable SLAM methods, this provides not just reconstructions of a desktop environment, but of significantly larger outdoor environments where you can see that there's fairly little distortion and hence fairly little drift in the estimated camera motion. And the remainder of the talk is actually largely focused on how we can further reduce this drift to get more precision out. The first achievement is actually a follow-up work that Jakob Engel did following LSD slam, is sort of the next generation. And to understand what motivated this follow-up, when you look into LSD slam, we do estimate camera motion and 3D structure, but we do so alternatingly. It's not really done jointly. And if you look back at Krupa's work, he showed that it's a chicken and egg problem. It's a coupled problem that really needs to be solved simultaneously. That's why it's called simultaneous localization and mapping, after all. And so rather than having two alternating threads, we aimed at reconstructing both at the same time in a Gauss-Newton type iterative manner. So it's something like a photometric bundle adjustment, except in order to make it real-time capable, we do it in a time-windowed fashion. And this is what's called direct sparse odometry. You see the application here. Top left is the input video. You see there's even people walking through the scene. So it's designed to be very robust to moving objects. It tracks, as you see bottom right, the camera motion at very high precision and recovers a semi-dense reconstruction of the world, or a point cloud reconstruction. And here everything is again driven by brightness consistency, but in a window of say 7 consecutive keyframes, we jointly optimize their camera position at every time and also the location of these points. You see that obviously, you know, if we track the camera over thousands of frames in an online approach, there is errors that we make, that we accumulate. And this is not using a post-graph optimization. This is not using loop closing. We wanted to show explicitly what that drift is. You see the bicycle here on the top left is actually reconstructed twice on the bottom right. There is a drift of roughly 2 or 3 meters on a distance of hundreds of meters. So you could say the total drift is something like below 1%. But how can we quantify performance of these methods? This is one of the most important challenges in this domain, but in general, I think in computer vision, how do we measure accuracy of methods? And so this is not easy. Obviously, we can create a simulated environment, simulate the video, and then we know the ground truth. We know the precision and the performance of our method in the simulated environment. Now, I think we all agree that the world we live in is not a simulation, and it may be quite different. Even if simulations look very photorealistic nowadays, we often find that SLAM methods that perform well in some simulated environment do not necessarily have the same performance when you take them to a real world. And so instead, Jakob found a solution to quantify SLAM performance, which goes as follows. He recorded lots of videos, as you see here, indoor, outdoor, different environments, different types of motion, different lenses, some more fisheye, some more perspective lenses, a very broad variety of scenarios where he wanted his method to work. Now, for all of these sequences, we don't know where the camera was halfway through the sequence. But all these sequences have one thing in common. They all loop back to where they started from, such that we can evaluate where the camera is at the very end by aligning it to the first image. And so we can have an estimate. We can have a ground truth information about the final position of the camera. And so for each sequence, for each run, we can have a total numbers that describe the total drift in translation, rotation, and scale. And this is plotted here. So on the x-axis, you always see the total error, translation, rotation, scale drift. And on the y-axis, you see the number of sequences where we achieved that total error. And the idea is that if you have enough such sequences, here's 500, that this gives you a statistically reliable estimate of the performance. We performed to what we considered the state-of-the-art in real-time visual SLAM, a very powerful and popular technique called ORP SLAM from a team in Zaragoza. And as you can see, dashed is the real-time performing method. Solid is if you have a bit more compute time to dedicate, then you can get a bit better precision. You can read these plots in many ways. For example, you can say, what is the maximum error on the best 300 sequences? Orbslam has an error of around 6. We have an error of around 1. Or if so the error, you can say, reduced by almost a factor of 6, essentially. Or in terms of robustness, if you say you want to impose a maximum error of 2, how many sequences can you track with that error? Orbslam can track 100 out of 500, and DSO can track 400 out of 500, which means also a drastic boost in robustness, which I believe is due to the fact that we directly, as I argued, leverage the brightness intensity values. And so the better we understand how brightness variations come about, the more precision and robustness we can achieve. And this is somehow, in my view, confirmed by these experiments. But we can go further, and as we all know, deep neural networks have really swept the field of computer vision in the last decade and have essentially replaced classical methods in pretty much all domains of computer vision, especially high-level vision, object recognition, categorization, but even low-level vision, optical flow, segmentation is nowadays often approached with deep networks. But one of the holy grails of classical methods, I would say, to date, is the reconstruction of the world from moving cameras. And one can go into an endless discussion why deep networks to date have not shown spectacular performance yet, have often not outperformed the state of the art. I don't want to go too much into detail here. I want to show you a little bit what you can do with deep networks. For example, you can use deep networks to extract semantic meaning and then reconstruct not just the 3D world, but also the semantic meaning of each point in the world. What you see here are reconstructions that we achieved with our startup Artisense, where we deployed sensor systems that Artisense has been developing that involve cameras in particular, but also inertial and GPS sensors. And then we deployed this in a whole fleet of cars to recover very large parts of Berlin here in a publicly funded project in Berlin with many partners, big industrial partners. We showed that you can run this from a fleet of cars and merge all of it in a large map of the world. Here, I didn't go into detail, but red is the drivable area, blue is cars, vehicles, green is vegetation, turquoise is buildings. So you can distinguish typically about 20 classes depending on what your training data offers. And we traveled a distance of 8,000 kilometers of coverage in total to reconstruct the world. And this is in some sense the main vision of Artisense, is to deploy cheap sensory systems to recover semantic 3D maps of the world for driver assistance, for autonomous systems and self-driving cars. Now let's look more into how can we boost the performance of visual SLAM using this power of deep networks. There has been some efforts lately, starting around 2017, quite impressive results where people showed that indeed you can use deep networks to recover camera position, 3D structure in various ways. Nevertheless, if you look at least the early works from 17 and 18, often in terms of odometry, they do not provide state-of-the-art on the established benchmarks like Kitty, etc. Again, it's hard to summarize why that is, but I believe one issue is that often they try to tackle the problem in an end-to-end trainable network. In go the input, images, outcomes, the world and the camera trajectory, and that's maybe a bit overly ambitious. And so what we developed are techniques where we integrate the predictive power of deep networks in a classical SLAM approach. And there's many ways how you can bring it in. Our first approach was we saw that there's deep networks that can predict the depths of the scene from a single image. Here you have such example, a network by Kuznetsov and collaborators, CVPR17. We built up on this and proposed another network that we call StackNet. This is work by Nan Yang and Roy Wang and Jörg Stückler. And as you can see, the prediction of the depths is significantly more accurate. But beyond just predicting the depths, what we propose to do is to integrate this depth prediction into a SLAM approach. approach. We integrated on two levels. First, we initialize the depth maps for each keyframe with the prediction of the deep net. And secondly, we add a loss term in the cost function of a classical SLAM approach, where in addition to this brightness consistency term that I mentioned, we have a term that says the depth maps should be consistent with the predictions of the deep network. And this is why we call it deep. This is a technique called deep virtual stereo odometry. We can actually train it in a self-supervised manner. So these predictions allow to predict the disparity for left and right image, in some sense, the depths of the scene. And then we can recover, we can run the classical SLAM approach enhanced by a deep net prediction that assures that the reconstructions are consistent with what the deep network predicted. And as you can see, we can recover very large environments and drive around with just one single camera and have essentially no drift. This was for a long time, to my knowledge, the most accurate real-time capable monocular system on Kitty, for example. We can compare, but let's go right into numbers. We compare to some, at the time, state-of-the-art stereo systems, stereo LSD SLAM, stereo ARP SLAM, stereo DSO. Solid is always best performing, cursive is second best. And here comes this deep learning enhanced method. And as you can see, it performs quite on par, if not better than these top performing methods, although it only uses one single camera. And so I find this is quite an example of how you can leverage deep networks to compensate for missing sensory information. And in particular, what we found is that there's very little scale drift. Typically, you get scale drift if you just have a monocular method, but with a deep network that can predict the world, in fact, even the global scale of the world, you do not see that scale drift. And this is what we'll see further, how we can deploy deep networks to actually compensate for missing information and end up with monocular odometry and SLAM systems that are quite powerful. In fact, we can go deeper, and this is what we do in this work that is an oral at this upcoming CVPR conference. It's called D3VO. Again, Nanyang, the lead author here, it's called deep depth, deep pose, and deep uncertainty for visual odometry. And so rather than just predicting the depths of the scene, it turns out we can also predict the pose of the camera given two consecutive frames, and we can predict some form of uncertainty. And then all of these predictions are integrated into the SLAM method. Let's go more detail here. So from a single network, as we saw, we can predict the depths. If we have two frames in time, we can have a pose net to predict the relative pose between these two frames. So rotation and translation of the camera. And with that, we can align the two images and then train the whole network with the self-supervised loss, which basically is the brightness consistency again. Now, once you do that for real-world cameras due to aperture changes and brightness variations, typically, as you see here, even once we align the two images, the brightnesses are not the same. One is significantly darker than the other. We can correct for that with an affine brightness correction, and it turns out we can train a neural network to predict, given the two images, not just the pose transform, but also the affine correction of the brightness with two parameters A and B. And so this is another prediction of a network. And then once you do that, you can correct for these brightness variations due to aperture change, but it's still, you're largely relying on the assumption of a Lambertian world. And now, as we know, if we take a real world image like this one, it's not a Lambertian world. There's metallic structures on the cars, there's windows that are translucent. And in all these areas, brightness is not preserved. And for example, with windows, it's actually very hard to predict what is the brightness in a second image once I see the same point from a different vantage viewpoint. This is very hard to predict. And so what we do here is, instead of trying to predict that, we estimate what in the literature, for example, in Alex Kendall's and Maria Claude's works, is called aleatoric uncertainty. And so what we do is we basically downweight the residuals in locations of high uncertainty where the network predicts that there's likely not going to be brightness consistency in these locations. And so we can correct for this in this manner. And it turns out we can train this whole network, the PoseNet and the DepthNet, to predict all these quantities. Here you see a prediction of this aleatoric uncertainty. And indeed, you see in the window and on the cars, and even in the trees on the top right, where you typically have motion and no brightness consistency, the estimated aleatoric uncertainty is high. And so we can train this whole network and then integrate all of these predictions into the SLAM method. We integrate it on several levels, both on the front-end tracking and in the back-end optimization. In the front-end tracking, we construct a nonlinear factor graph for brightness consistency and impose it. In the back-end tracking, we add respective terms to the loss functions that say the reconstruction should be consistent with the predicted pose, with the predicted depths, etc. I don't want to go too much into detail. This is all covered in the paper, but once we do that, we can evaluate the performance of this method. Let's first look at depth prediction, monocular depth prediction. Here is an evaluation on Kitty and on UROC. And you see that it performs quite well compared to the state-of-the-art, or one of the state-of-the-art methods, a technique called monodepth2. But beyond that, it also generalizes quite well. So we trained it on Kitty and we evaluate it on cityscapes. And what you see here is that the depth predictions are quite accurate also on cityscapes. And if you look on the bottom right, in this area of the windows, for example, the aleatoric uncertainty that we predict here on the right is also quite convincing. Now, as I said, we can go further. We can evaluate odometry. Here's a comparison both to classical methods and to more recent deep learning methods. And you see the method performs quite well, both compared to monocular, but also compared to stereo methods like stereo DSO. It outperforms them. But beyond that, we can go further and show how much we can boost performance, how much we can compensate missing sensory information. Here is a comparison to both monocular, but also visual inertial and stereo inertial methods like Basalt, the state-of-the-art stereo inertial method, or visual inertial DSO here. And you see that the proposed D3VO performs on par with these methods, even though in contrast to these stereo inertial methods, it only uses one single camera. You can look into the reconstruction here, for example, mono DSO on the right, and in comparison, D3VO, a much more crisper, sharper reconstruction, indicating that indeed the trajectory is significantly more accurate. This is the last part I wanted to talk about. Beyond correcting brightness variations with a deep network, you can actually try to learn brightness variations. For example, if you take, if you want to relocalize in a previously mapped environment, one of the challenges is once you come back to the same environment, left is the old environment, right, we come back to it, you see often you have very drastic changes in lighting. You have, for example, water there in the scene where there was no water on the left. You have very sharp shadows, very different brightnesses, or on the bottom, you can have very dramatic changes in weather. The green grass is all of a sudden snow in winter. And then things, even to humans, look often very different across the seasons. And then it's not so easy to realign yourself to a previously recovered image. If we want to do this relocalization across different lighting and weather conditions, we need a data set, but we also need a method. And what we do here, this is an approach by Lukas von Stumberg, published at ICRA this year. It's called the Gauss-Newton net for multi-weather localization. And what we do here is we actually train a neural network to do an intensity transformation into a high-dimensional feature space. This has been done frequently with deep networks, but what's new here is that we do it in such a way that it is optimally suited for a Gauss-Newton-based SLAM algorithm to run. And this is, you can go into the paper for more detail. This is why we call it the Gauss-Newton net. There's actually a Gauss-Newton loss that we introduce here that makes it perfectly suited with a SLAM approach. What you see in this evaluation, we also have a data set that we offer publicly that has images with different weather, you know, and lots of moving objects, very realistic, challenging environment. And you see on the bottom left is always the current image, bottom right is the closest image in the data set, in the training set. And here you see the gray point cloud is the previously recovered 3D map. Blue is the new one. Here you see in blue lots of cars that were not there at the first time of mapping. And you see how everything, even the lane markings, nicely integrates into the old map, which indicates that we align the car not just in local coordinates, but also in relation to the global previously recovered world map. And our ambition here in developing these technologies is actually to find solutions that allow to relocalize and find yourself in a 3D world without any GPS. So the idea being is that you first map the world in a first run where you have a GPS sensor, then you have world reference coordinates of your points, and then you relocalize yourself in that previous map in the second run where you have only images. And hopefully then at some point we can completely get rid of the GPS dependency of odometry of localization systems for autonomous systems. There's more videos on YouTube. I'm going to conclude now. Here's a data set that we also offer. It's a multi-weather localization benchmark that uses data both from Carla, a simulated environment, but also from a real-world data set, the Oxford robot car data set. And what we collected is 9 training sequences from Carla that have different weather conditions. Here you see it left and right, where they're very different weather and lighting conditions. And in Oxford, we have also, you know, some sunny, some rainy, some snow conditions. The data set is available at our webpage. And then we can evaluate, and you know, as always, we're on the top right of these performance plots. What's interesting to note, though, is that we can not only align sunny and overcast, which is what we trained on, but we can train on the pairs of sunny and overcast and have also very good performance and on the transition between sunny and rainy, even though the system has never seen rain, or on sunny and snowy, even though the system, the training data didn't actually contain any snow data. So we find that this network does a fairly good job in generalizing this approach, this relocalization solution to multiple weather and lighting conditions. Let me conclude. I talked about visual SLAM and promoted the notion of direct visual SLAM using the sensory data directly to maximize precision and robustness. Then I showed how you can leverage the predictive power of deep networks on various levels to boost the performance of these monocular SLAM methods. And lastly, I showed that you can deploy it for autonomous systems, create large-scale semantic 3D maps acquired from a whole fleet of cars with the respective sensory systems on board. It allows you to do 3D mapping, to do localization, and also what we call relocalization. So thank you very much for your attention, and I'm happy to take questions.
Thank you very much, Daniel. It's Christian Mikolajczyk here. I think Torsten have left. So I will read the questions that the audience asked. I'm sure we would hear an applause right now if we have everyone unmuted. But
that's okay.
Let me ask the questions in no particular order. Actually, some of them you may have answered in your slide because they were put on early during the talk. So from the beginning, there is a question about what do you think are the limitations of using the photometric error, and there, you know, at any point the brightness consistency breaks.
That's a good point. Yes. So brightness consistency breaks. And basically, one of the things we do by deploying deep networks is to compensate for these issues. And I think I showed that you can compensate in my presentation. At least I highlighted 3 approaches of different sophistication. The first is that you can try to compensate by correcting for brightness changes, for example, with an affine transformation of all brightnesses to align to the target image. And you can train a deep network to predict that affine correction. The next more sophisticated thing is that if you know these are areas, windows, metallic structures where brightness consistency is clearly violated, you can train a network to predict these and then downweight the residuals in those areas. And the third thing you can do is you can actually train neural networks to learn what are the brightness variations that we observe in our world, from rainy to clear sky, etc., and train a neural network to learn this optimally. And so I was arguing the power of direct methods is that the more we understand about brightness variations, the better precision we can get. And then we move over to saying it's not necessary that we understand the brightness variations as long as the network understands them. And so the network is trained to understand the brightness variations, and that boosts the performance of direct SLAM methods.
Okay, thank you. I have also a couple of questions actually related to fusion with other sensors. So which of the systems, SLAM systems, you would is the most sort of suitable, and what kind of other sensors like LiDAR, GPS, would that be good to combine with?
So this is a question I often get. Once you're a practitioner, that plays an important role. In this presentation, I only talked about visual SLAM. So how much can you get out of cameras? And towards the end, even out of just one single camera. And I think we have an unrivaled performance now in terms of real-time capable monocular odometry. But once you deploy it in a real-world environment, in a robot, in a car, etc., and in autonomous systems, then of course you will leverage whatever sensory data you can get hold of, in particular sensory data that is complementary. And what we found works really well is inertial. In particular, when you have fast rotations, camera-based approaches typically have difficulty dealing with that, and inertial sensors are very good at picking those motions up. And so visual inertial is very powerful. Then GPS, in particular, if you have access to something like RTK GPS, that gives very high precision, also global reference, this is important. And then obviously LiDAR is powerful, radar, so you can fuse with all sorts of sensory system. What's important though is once you do that, you have to know what you're doing. So, if you're naive, I would say don't try this at home. And what I'm saying is you really have to know what you're doing and how you fuse sensory information to avoid a system that is dominated by the worst of these sensors, whereas you want to bring yourself into a position where the best sensor dominates the performance. And this is a tricky thing, how to get this working. So it's important that you know exactly how to do it. But once you can do it, then it does boost the performance. For example, at Artisans, we're doing exactly that. And we have systems that we demo where just visual inertial, stereo inertial, you can drive 3 kilometers through an unknown environment. And once you come back, you have a drift of about 1 meter or so over 3 kilometers distance. So we're talking about 1/3 per mil drift of a stereo inertial system. And so this is a boost, a whole order of magnitude or more that you can get by fusing sensory information.
Okay, thank you. And maybe a final question, actually. There is one about, what would you recommend for, I guess, users? Because there is a trend of going end-to-end with visual odometry, and some combined with sort of classical techniques for robustness and accuracy. What is the recommended approach?
This is hard to say at this point. What we are doing is we promote hybrid methods that exploit the power of both approaches. I think deep learning has a strong power when it comes to, for example, correspondence estimation or predicting depths. You know, you can predict depths from a single image. This is quite impressive. But the classical optimization-based methods, they are very powerful because they exploit all the information we know about the world. We know exactly how our camera works, how images are projected, how the world is projected into the camera screen with rigid body motion, with perspective projection. And how should I say, I think it would be stupid to not exploit the knowledge we have. And so the key challenge is how, and I think this holds for any application of deep networks in our world, you know, we can deploy them and apply them to many applications, but I would recommend not applying them blindly. And we need to find ways to really, you know, use the knowledge that we have, and not throw everything we've done before overboard, but somehow use the knowledge about, you know, epipolar geometry and all of that jazz, and how to integrate that with deep networks. I think this is one of the most important challenges for the vision community at large.
All right, thank you very much. So let me quickly applaud, and I think I speak for all the audience for the talk. And
Thank you very much, Christian. Thanks everyone for listening.
Thank you again. And let's move to the next talk that I have a pleasure to introduce. If we can switch the video. I'm really happy to introduce Andrew Davison from Imperial College London. So Andrew is a professor of robot vision and also head of the Dyson Robotics Lab at Imperial College. You may know Andrew well for his work on SLAM, on event camera, and various applications in robotics. So I could spend a long time to cite his really great contributions, but let me just hand to Andy and let him speak about his work.
Thank you very much, Christian, and thanks to all the organizers. So can you hear me okay, just to check?
I believe yes, and YouTube will hear you in 10 seconds, I guess.
Good. Okay, let me just share my screen.
Yes, Andy, we can hear you.
Good. Okay, and can you see my screen share?
Yes, everything is fine.
Good. Okay, well let me start then. So yeah, it's a pleasure to take part in this workshop. So I'm going to speak to you about SLAM, a little bit of a kind of broad view of where I think we are in this field right now, and how I think it's evolving into something even bigger and more important that I call spatial AI. So we're at this pretty interesting point now in the history of SLAM, I think, especially for those of us who've been working in this field for a long time. And for me, it's really about 25 years now that I've been working on this since my PhD in Oxford. But we actually have products and systems out there on the market now that are enabled with visual SLAM. So these are in actually several different categories, and that's what's particularly interesting. It's not just about one type of product. Some of these are certainly what you would recognize as robots. So in the top left here, you can see robot vacuum cleaners. So this is the Dyson 360i, which was a product I was directly involved in working on with Dyson. We have smart drones from companies like DJI or Skydio with pretty advanced visual SLAM capabilities. We have visual SLAM in smartphones. There are capabilities like ARKit or AR Core from Apple and Google, pretty nice performance. And then there's this huge area of AR, VR headsets that need to be tracked in the world in order to enable, smart augmentation, smart interaction. In many ways, these products are quite different. They have different combinations of sensors, but they've all kind of centered on cameras as really a core element of the sensing platform. Cameras have very nice points. They're cheap, they're small, and the potential upside of cameras in terms of what you can do with them is kind of almost limitless, I think. But if we look at what visual SLAM actually enables in products like this at the moment, it's largely about positioning and some level of mapping, which might be sparse or semi-dense. So all of these products can locate themselves accurately in the world relative to a map of landmarks. And then we have capabilities that are gradually coming in along the lines of dense and semantic mapping. So beyond positioning, smart devices need to understand, the shape of the world around them, and also increasingly, the content and identity of objects around them. And those capabilities are also, rapidly starting to enter products like this. So one way to think of this is a kind of a ladder or a set of levels. So this is an image from our startup SLAM core, where we think of layers of performance in SLAM, from localization, which is where am I, to mapping, which is what's the shape of the world around me, to semantic understanding, which means, what are the things in that space around me. And I think what's really interesting is within this field of SLAM, we've gradually been building up through these levels, but generally while keeping in mind the kind of requirements of, real-time interactive systems that hopefully you can actually get out and demo and test and put into real products. So I think the character of SLAM research that I've always enjoyed is it's been about, actual demos, systems, open source code. It's not necessarily just performance on benchmarks and running on images and data sets. But then we've evolved, towards these gradually increasing capabilities. So I would say SLAM is evolving into something bigger, and I'm using this term spatial AI. And let's call spatial AI the online problem where vision is to be used, usually alongside other sensors, as part of the artificial intelligence, which permits an embedded device to interact usefully with its environment. So here we're being clear that just localization and building a map is not the end point. It's not the aim in robotics or in other applications. The application is, the end point is intelligent operation of a device. So we're really turning attention to that now, and so that's very interesting. So where might that take us in a few years' time? Let's think about some potential breakthrough spatial AI equipped products of the future. So first of all, in robotics, and I should say very clearly, this is just a mock-up image I found on the internet somewhere, and certainly not representative of any product concepts at Dyson or anywhere else. But let's imagine, what a robot of the future might be like. So an indoor robot. It might, let's imagine a mass market, general purpose household robot for cleaning, tidying of complicated rooms and objects. It has a spatial AI system, which is constrained by price, aesthetics, size, safety, and power usage, which must fit within the range of a consumer product. So this would be a very capable device that you could just say, clean my room and go out and come back and expect it to be done. So this is going to need a full sort of 3D spatial semantic understanding of the space. It's going to need to understand objects. It's probably going to need to understand physics. It's going to actually have to interact physically with objects. So that's, I think, pretty much far beyond anything we can do right now. And especially when we consider the constraints that a real product would have to fit within. So price, safety, power usage, all of those things. So another type of product, which I also think is pretty difficult to build, is the sort of augmented reality system which I think will eventually change the world. And of course, there are companies working on this, but I think they've all realized just how hard it is. And I've called this a spatial AI product to stand for intelligence augmentation, which is a bit of a cute flipping of AI, but I think of it as AI with a human strongly in the loop. So the specs of this set of glasses might be along these lines: an augmented reality system with the form factor of a standard pair of glasses. So it's not going to be a chunky thing that sits on your head. I think if everyone's going to wear it all day, it's really got to look quite a lot like a normal pair of eyeglasses. But it would provide a robust and accurate real-time overlay and spatial memory of all places, objects, and people that you've come across. But here's the really tough thing: it should weigh 65 grams and have all-day battery life. So to make that point, more strongly, I think that these are products which will be hugely important when they arise. They don't exist yet, not because there's no demand, I think there is, but because no one yet knows how to build them. And that of course involves many different types of technology, both in robotics or eyewear. There's all sorts of problems to solve, but just within the sort of spatial AI area, I think we've got what current products can do. So these are the things I showed you in the first slide. We've got some things out there in research prototypes, in research labs, in companies, in universities. They're making some progress. But then I think there's still this big gap to cross to the capabilities that we need in these products that will really change the world. And I think the particular areas where we're lacking are robustness and efficiency. So robustness means devices that will really work in all sorts of different conditions. Whatever you throw at them, they'll do something fairly sensible. And then this other key one is efficiency, and I'm particularly focused there on the power that algorithms and sensors and computation uses to actually come to actual inferences that are useful. So these devices may be connected to the cloud. Some computation may happen there, but they're going to have to do a lot of the computation actually on board, and they're not going to be able to carry around huge supercomputers. So efficiency is really important. So I've thought quite generally about this area of spatial AI, and in particular, this concept of the computational structure of spatial AI systems. So I've written a paper that you may find interesting. So this is a long discussion paper called Future Mapping: The Computational Structure of Spatial AI Systems. It's available from Archive, and it really studies this whole concept of what a spatial AI system could do and what are the prospects in particular for making that robust and efficient. So there's a few kind of hypotheses in that paper. One is this one. So to enable embodied AI, a spatial AI system should build a persistent and understandable scene representation, which is close to metric 3D geometry, at least locally. So what I mean by that is, let's imagine something like a robot whose job is to tidy up a room. So whereas there's certainly been work that's shown that devices can navigate without necessarily building maps. You don't necessarily need a metric map of a space to, for instance, walk from your house to the railway station. But if you really wanted to do something like tidy a room up, which might mean vacuuming every corner of the room, knowing when you've done everything, and remembering which parts you've done, which parts you haven't done, finding any object in the room and then knowing where to put it and actually traversing to put that object in the right place, then come back to where you were before, find other objects. It's very, very hard for me to imagine how you could carry out tasks like that without a concept of a map that you carry around. And that map may or may not be metrically precise 100%, but I think it's going to be somewhat close, at least locally and at least a lot of the time. So that's what I mean by that hypothesis. And another hypothesis is that there's a generality to spatial AI systems which will be useful for many applications with a fairly small number of performance measures or constraints, defining the differences between different systems. So what I mean by that is, I think that, we could think of quite different applications: a robot vacuum cleaner, a drone, eyewear. Clearly, they're going to have different performance parameters that are important in terms of accuracy, robustness in certain types of measure, semantic capability. But I think there may be a relatively small number of parameters which you could think of as sliders that sort of set the performance of that system. But then under the hood, there's a relatively common spatial AI kind of workhorse that will apply to any of those problems. So those are kind of hypotheses. But I think that by working in this area of embodied intelligence, spatial AI, we may learn a lot about AI in general. We may learn a lot about, in general, embodied intelligence. What are the computations and storage patterns of the kind of memories of these systems that make such things possible? Okay, so let's move on and talk a little more concretely. So just a very sort of brief bit of history here and relating to these layers that I showed you earlier. So through my own research over the years, we've worked on sort of those different levels and really seen that cumulative build up in terms of capability. So I'd worked already on Visual SLAM for several years before this, but in 2003, a big kind of personal breakthrough for me was when I managed to make monocular SLAM work. So this was the monoslam algorithm where we had the input of a single handheld camera moving around within a space, detecting and tracking landmark features in the scene, and then building a 3D map, jointly estimating the positions of those landmarks and the motion of the camera, and then showing that could all be done in a closed loop at 30 frames per second, on a 2003 laptop. And this was quite a breakthrough, and we showed that you could do some different things with that. We showed some augmented reality, we showed some humanoid robotics, for instance. The tracking was not super accurate at that time, mainly due to the relatively low number of features that we used. It was reasonably robust, but you had to move the camera, kind of slowly and carefully. There was no additional inertial sensing that helped at that point, for instance. But then the real-time performance was enabled by quite kind of clever thinking about active processing. So we really paid attention to which parts of the image were most useful in giving accurate information about the camera position. So we worked on that for several years, and then the next kind of big milestone, I think, that was really important was around the time of about 2009 onwards. And this was particularly via the work of Richard Newcomb, who was working as a PhD student in my group at the time. And we started to show that we could do real-time dense or direct visual SLAM. So those are slightly different terms, dense and direct. Direct, as Daniel described earlier, refers to going straight back to raw pixel intensity information in terms of defining your cost functions. Dense means trying to use all of the information in a whole image, both for tracking and reconstruction. So an important paper for us was DTAM in 2011, where Richard showed that we could build a fully dense SLAM system, which both built a complete kind of surface level reconstruction of a scene, and then use that whole scene also for tracking. So this was a system that didn't use feature points at all. Also very much at the same kind of time, and also involving Richard, commodity depth cameras came along, and the Connect Fusion algorithm in particular showed what could really be done in terms of real-time SLAM using the pretty high quality flow of depth images that comes from something like a Connect camera. So whereas in the monocular SLAM work of DTAM and so on, we'd had to do quite a lot of difficult stuff in order to get dense depth maps out of a single moving RGB camera. With a Connect camera, they come flying at you at 30 frames per second. They're pretty good quality, and we could really focus on how could you fuse those into a long-term persistent map of a scene. So in Connect Fusion, using a volumetric representation. So just to very quickly show you, something representative of dense SLAM. So this is the elastic fusion algorithm. So this was developed in the Dyson Robotics Lab, led by Tom Whelan, this work a few years ago. And what's happening here is we're jointly estimating the motion of a camera, so a depth camera represented by this little moving purple shape here. And then at the same time, we're building this dense 3D map of the scene. So here we're using a slightly different representation. We're using a circle map which is a quite efficient way of representing surfaces as a kind of splatting of many disks. A particularly nice point about this representation is it enables loop closure. So when we come round, identify that we've revisited somewhere that we've been before, but there's a bit of drift in the map, we can correct that drift by basically bending the map round quite efficiently. Okay, so that's elastic fusion. And then really, I think what's very much a current area of research interest in SLAM is semantic level mapping. And there's many different approaches to this. One that we developed in 2017 was called semantic fusion. So in fact, I would characterize this as sort of the most obvious thing that you can do. So we're using exactly the same elastic fusion algorithm I just showed you for the dense mapping component of this system. And then we're using a CNN on a per frame basis to label frames with the expected labels in image space. And then what semantic fusion does is fuse all of those labels coherently into the 3D map. So actually each circle of the elastic fusion map holds a distribution over estimated categories of semantic classes, which gradually is refined over time. So you might get a single frame view of the scene, and then you gradually improve the semantic labels by seeing the scene from different viewpoints. Okay, so that in some ways leads me to the sort of crux of my talk. So in many ways, we can look at this progress over the years, this stepping up through the levels, and think of what's happened as we've thrown more and more computation at the SLAM problem. So through the years, better computers became available that we could use to run SLAM on in real time, and that's enabled us to do more. But some of the characteristics of that is it's led us to a lot of computation and quite complicated systems. So this is a sketch of a sort of rough idea of the computation graph of semantic fusion, the system I just showed you earlier. And don't worry at all about the details and whether or not you can read these. Roughly speaking, the green blocks are the kind of main data stores here, and the yellow blocks are computation blocks, and then they're joined together in this graph. So we've got all sorts of different things going on. We've got CNNs doing work labeling images. We've got a sort of tracking loop here where we calculate photometric errors and optimize. So I just want to make the point that this pretty complicated graph is really what we need to optimize in order to get to this high performance, efficient spatial AI that I'm talking about. And some of the problems at the moment, aside this kind of complication, one problem is that generally different parts of this might be running on different sorts of computation hardware. So some of these parts are actually very nicely parallelized on a GPU, like the CNN, like parts of the dense tracking loop, but other parts don't really work well on a GPU at all. So we have to shift memory back to a CPU, do some optimization there, shift things back to a GPU, etc. And just another key part is a lot of these blocks of data, they're just enormous. So for instance, the map in Elastic Fusion might consist of 5 million circles. So it's just a huge amount of memory. We're pumping around kind of image-sized arrays and video all over the place. So that's very, very expensive in terms of power usage on computation hardware. So to attack these kind of issues and to get to better efficiency, I think there are two kind of main interesting lines of attack, and both of them we're following in our lab. One is about representation, which I think is mainly about how do we get away from these huge sort of representations towards something that's much more small, abstract, and meaningful. And the other is about computation hardware that I'll talk about second. But let's think about representation first, and we should really discuss the impact here that deep learning has had on SLAM, which has certainly been huge. But as Daniel also mentioned earlier, it's certainly not blown away, all of the stuff that we did before. So unlike I think a lot of areas of computer vision, the classical methods are holding up pretty well in SLAM. So I've got a pretty open mind about this, and actually I like to think that there's pretty much a sliding, almost continuous scale that we can consider here when we're designing algorithms. So at one end, you've got this concept of a pure end-to-end learned algorithm where you literally have the data from your sensors coming in at one end, the kind of performance and the things you want to estimate at the other end that you'll measure it against, and in between some complete black box network that will learn whatever structure it needs in order to best achieve those ends. At the other end of the scale, we've got a fully hand-designed algorithm. So certainly up until quite recently, this is what SLAM algorithms were. So certainly something like elastic fusion, purely hand-designed. Semantic fusion, you know, it uses some CNNs. So there are some learned blocks in an algorithm like that. But I think there's many different points on this sliding scale in between those two ideas. And you know, most of us in SLAM are working on quite modular ways of designing systems somewhere in the middle of that sliding scale. And there are probably two key ways to go about that. One is you start with your hand-designed algorithm, this big kind of graph of components, and you replace some of those designed modules with learned modules. I think the other approach is to start with a sort of end-to-end algorithm, but then engineer structure into that algorithm. So maybe you'll replace some general learned block with something like a spatial transformer, which has a much more sort of human design that's gone into its structure. But you may end up in very similar places in those two approaches. So actually, my main interest at the moment is not so much whether these modules are learned or designed. I think we're going to see great progress in both of those, but how they all connect together, what is the computational kind of layout and structure, how do they communicate in each other, what's really going to lead us to this efficient spatial AI capability that I've been talking about. So just to show you some of our work on representation that we've done recently. So one kind of key area we focused on, I would describe broadly as coded keyframe representation. So one very nice way of going about SLAM is to make a map of keyframes where you're estimating the pose of the camera at various places in your environment, and relative to each of those, you're estimating certain quantities, such as a depth map, such as a semantic label map. And we've shown with a couple of papers recently, so Code SLAM from 2 years ago at CVPR, and then Scene Code from last year, that we can use deep learning. So don't worry too much about the details here, but there's a combination here of something that's like a single view depth or semantics prediction network combined with some variational autoencoders. So the capability that this gives is when you feed an image in, so this is an image from Scene Code, and in Scene Code we're interested in both depth and semantic labels for each of these keyframes in our system. So we get a single view prediction of both a depth map and of a semantic label map, but then we also have available these codes here. So these are part of the autoencoders, which are basically vectors of small numbers of parameters, so typically something like 32 parameters, which are like sliders that then allow you to adjust the depth or semantic map that you've built. So from a single view, you predict a depth map, but then when you've got two views overlapping, you can adjust the codes of these two predictions to try and make them meet each other. But the nice point is that these codes alter the depth or semantic maps in nice, smooth ways that are consistent with things that happen in the data set. So this actually enables us to do jointly optimized dense SLAM, both for depth and semantics, just by optimizing fairly small codes. And if you're interested actually in these methods and playing around with these kind of ideas, I would highly recommend looking at this paper. Let me just quickly show you the video here. So this is work led by Jan Zanowski from our lab, and it's an evolution and a turning into a much more kind of proper SLAM system of the ideas that are in Code SLAM to enable, you know, sequential joint optimization of both camera motion and then dense scene geometry via this code optimization method. And we've also just recently released all the source code behind this open source. So please have a play with that. Okay, let's keep moving. So those methods use deep learning to kind of learn representations of kind of whole frames, but actually, you know, you realize some of the limitations there, that actually 32 parameters is really not that much for describing the variation that can happen in a whole kind of depth map or in a whole image scale scene. I think that where we'd really like to go in general, in terms of thinking about what the representations of these maps should be much more focused on what are really the important things in scenes for robots or other smart entities. And I think that kind of comes down to objects. So a map of where the objects are in a scene seems to be something that you could encode really quite efficiently and might really be the right way to go about, storing long-term information about scenes. And we did some work back in 2013. This was led by Renato Salas Moreno on a system called SLAM++, which was really the idea of, can we directly build a SLAM map at the units of objects? So this was bringing object recognition directly into the front end of a SLAM system. So as we were moving a depth camera around, we would recognize instances of known 3D objects, so these tables and chairs. And then when we'd recognized one, we would populate the map with an object like that. So the map really just existed of a graph of the locations of objects. So each of these objects, we just need one 3D model for each of these types of objects. And then we just need to store the 3D coordinates of those objects. And we can bring all of those things together into a pose graph. So very efficient, but with the limitation that the map can only consist of these specific sorts of objects that we know about in advance. But I think this work has been quite influential and really leading a lot of people to think about this concept of, what's the best way to represent scenes in terms of graphs of meaningful entities. So SLAM++ is about a kind of one-level graph of objects, but you can really extend that in a sort of hierarchical concept. So here's a couple of images from different projects from Facebook Reality Labs or from Luca Carlone's group at MIT. How do you decompose scenes, in a hierarchical way into these sort of hierarchies of objects, which are actually very different, very similar to the sort of scene graphs that, for instance, a computer game designer would be familiar with for designing 3D scenes. So just going back to the SLAM++ concept, let me show you some very recent work. So in fact, we'll be presenting this this week at CVPR. Oh, let me just make sure that's muted. So this is called More Fusion. So this is a system which is very much along the same lines of SLAM++. If we want to build a map of a set of objects for which we have prior CAD models available. And here we're using these YCB objects. And you'll see that we've moved it over to, rather than a kind of room scale setting, this is a kind of tabletop setting, but where we've got now a robot arm involved. So the reason to build this representation of where the objects are in the scene is because we actually want to go in and interact with them. So the kind of extra tricky point about this setup, rather than what we had in SLAM++, is now the objects tend to be very close together. They're lying on top of each other. They're occluding each other. So it's actually quite tough to get an accurate estimate of the relative poses of all of those objects. So here we use multi-object volumetric reasoning to say that we want to estimate a set of 3D estimates of all of those objects, but clearly under the condition that they can't be intersecting each other. So that means that's what gives us the extra information that allows us to, estimate good pose even for objects that are, tricky, that they're occluded. We can only see a small part of them. So we get to these very nice kind of 3D representations of scenes, and then I can show you here how we can now use that for grasping. So in this particular demo, so we were showing it in a kind of 3D visualization on the left, and in the real robot video on the right, the robot wants to grasp the red box and move it into the brown box at the side, but it realizes that there are two objects kind of in the way. So having mapped the location of all the objects in the scene, it can then go and grasp these distractor objects, move them out the way, put them into the yellow bin on the left, and then finally go in and grasp this red box and put it in the correct place. And you'll notice that it's not just dropping it into this box, it's actually placing it quite precisely because it's picked it up with very good, perfect knowledge of its pose. So that work relates to some, some other things that we've done, still very much in this area of object representation. So we had a paper a couple of years ago called Fusion++, which is saying, if we're not in this strong situation of knowledge of having prior CAD models for all the objects we expect to encounter, what can we do? Well, we can use something like mask RCNN to at least identify what the separable objects are in the scene. But for each one, we'll build an individual volumetric reconstruction. And then our total, high-level representation is a graph then of these individually reconstructed objects. Something that we've published very recently is a system called NodeSlam, which I think lies very much in between Fusion++ and SLAM++. So SLAM++, you've got prior CAD models. Fusion++, you have no prior knowledge of objects. In between, I think you have this interesting area where you can recognize an object at the level of its category, but not necessarily in terms of its precise instance shape. So we've got here learned class level shape descriptors. So here we've got 4 classes of objects, bottles, mugs, bowls, and cans here. For each one of those, we've taken a 3D database of objects of that class. We've learned with a 3D autoencoder a shape space for each one of those objects. And then at runtime, we're optimizing a code relative to each one of those shape spaces to then fit the precise model of the objects to the runtime data that we've got. So let me just skip forward a bit. So here's a visualization now of a sort of object level SLAM system using these descriptors. So here it's detecting the objects. Each one, it's then optimizing these shape parameters. And then it's putting all of that into a full joint optimization of camera pose, of object positions, and of object codes. And then I'd show you here, we've also used this system for robot grasping. So here's a situation where the robot's looking at this scene. It's got a number of objects in it. It doesn't have precise CAD models for any of these objects, but it fits these shape descriptors. And then we show that they're fitted accurately enough that then we can then go and grasp the objects very precisely. So what it's doing here is grasping these bowl objects in order of size. So the biggest one first and the smallest one last, and then it's placing them precisely like this to stack them in the corner of the box. So this, I hope, really sort of shows how we're really now trying to go beyond SLAM, where the endpoint goal is just representation and map, but the endpoint goal is actually intelligent action. Okay, so it's just got a few minutes left. But let's just go back to this picture I showed you earlier of the semantic fusion computation graph and talk about the other kind of key approach that I think is very important at the moment, and that's related to hardware. So I mentioned that different parts of this computation graph in the current system are running on different sorts of processors. So mostly some on CPU, some on GPU, and we've really directly experienced the impact that new processing hardware coming into the field has had. So when GPUs became available, we were really able to do new things in SLAM. But we've got to realize that's only the start or an ongoing part of the evolution of computer hardware. So this is something I've been very interested in, particularly since being involved in a project called Pamela, which was a joint project between the universities of Manchester, Edinburgh, and Imperial a few years ago, where we really thought about how do SLAM algorithms relate to the hardware that they're going to run on. And we took some SLAM algorithms and really broke them down into their components and really analyzed how the different parts of those components worked, on anything from a huge desktop GPU-enabled system down to a tiny embedded board. And remember that, the target for the sort of systems we really want to run these algorithms on is much more like this than this, or at least the future version of a low power system like this. So we were trying to kind of open up research on different types of algorithms and maybe how algorithms should be co-designed with hardware. And something that we were always thinking about at the time was could we or should we design a specific chip for SLAM, which would be the most efficient chip possible. And I think the hard thing about that for me was people would ask me, okay, what's the algorithm we should implement? And then we'll go away and design some hardware. But I didn't want to be pinned down because the algorithm space was changing so fast. We had sparse, dense semantic CNNs coming in, and I didn't want to be limited too much. So what is the right sort of hardware for SLAM? And I think that's still an open question, but there've been very interesting things going on recently, which I think are promising. And in particular, a move to a new sort of processing hardware called a graph processor. So this is particularly a visualization from a company in the UK called GraphCore that are actually building graph processors. And they call it an IPU, or an intelligence processing unit, to mean that this is really a processor designed for AI workloads. And I would certainly include vision within AI. So, let's remember that we've done all this work on computer vision and AI using processors that weren't really designed for it. So we've used CPUs an awful lot. They're general purpose processors, they're good at word processing or something like that, but they're not necessarily got the right sort of performance for AI. We've used GPUs a lot. They're designed for graphics primarily. They've been adapted a lot to AI, and for certain workloads in AI, they're very useful, but they certainly don't solve the whole problem. So an IPU is again, not trying to be really specific, but it has certain characteristics that I think make it much more suitable for what we want. So what an IPU actually has, it's a massively parallel processor, a bit like a GPU in that sense, but all of its different processing cores can be running quite different sorts of programs. So whereas a GPU works best when every core is doing very much the same thing in lockstep parallel, an IPU can be much more flexible. And part of the design of an IPU, and this isn't at all how it's laid out, but just to show you the sort of split between logic and memory on an IPU, compared to a GPU, there's much more of the area of the chip is given over to memory. So think of a larger number of processors set into this sea of high performance memory, such that each of the cores has quite a lot of memory to be able to work with, but it can also use that memory to very efficiently store and communicate things to its neighbors. So actually the general class of algorithms that an IPU is really good at is local processing and storage algorithms which compute by message passing. So many independent cores, each computing its own thing, and then sending lots of messages around to all of their neighbors. So if you can make algorithms that work like that, they'll work very well on an IPU. So I've been thinking a lot about spatial AI, and in particular, where are the graphs in spatial AI, and how might we map those graphs onto something like an IPU? So this is a visualization that GraphCore have produced. So when they take a neural network and compile it down to run on an IPU, and that's the main thing they're commercially working on at the moment, they can produce this nice visualization of which parts of the neural network map really sort of geographically to the different parts of the processing and storage array. I've been thinking about spatial AI and what are the graphs in spatial AI, and how might we map them therefore to processing hardware. And parts of this look very much like that yellow graph that I showed you earlier. We've got these graphs of computations and how they link together, but there's a lot of other graphs in SLAM that will be familiar to researchers in SLAM. So for instance, most of the best ways of storing maps in SLAM come down to graph-like representations, which essentially connect nearby places together closely in the graph and faraway places not so much. There's also some very nice kind of graphs you can find, related to camera space. You've got this regular, graph of coordinates in an image, which we use for MRFs and things like that. So a lot of the thinking in this paper is related to that kind of thing. So making that a little bit more concrete, and this is the last slide I'm going to show, but we've got a paper that we're going to present at CVPR this year, so led by Joe Ortiz. It's called Bundle Adjustment on a Graph Processor. So this relates to another one of these very long discussion papers, which is the second in my future mapping series, called Gaussian Belief Propagation for Spatial AI. So having thought about this a lot, I've realized that there are categories of algorithms which we can use in SLAM and spatial AI, which might be very, very suitable for this sort of new architecture. And interestingly, these are not new algorithms, these are old algorithms. So belief propagation is a well-known classical algorithm It's been used various times in computer vision, but not really in SLAM type of problems, because if you want to do something like bundle adjustment, where you want to jointly estimate the positions of a set of points and a set of cameras, there are algorithms that work more efficiently on a CPU than Gaussian belief propagation. But on an IPU, we've shown that you can actually implement Gaussian belief propagation very, very efficiently. So this paper shows that, so we take a kind of reasonable size bundle adjustment problem, we map it in quite a simple way down onto the IPU. So we take the points, the cameras, and the measurement factors in a factor graph, map that down geographically onto a graph processor, and then implement bundle adjustment by belief propagation. And really, in very preliminary results, we're already showing very promising things, like a certain size of bundle adjustment problem can be computed, 20 or 40 times faster on an IPU than it can be on a sort of equivalent size CPU using commercial software like Ceres. So for me, this is very interesting and promising, and it takes me towards larger scale thinking about how we might move towards fully graph-based representations for spatial AI. And the dream is to have this graph living and evolving on something like an IPU. Data gets fed to it, and all the computation is kind of local and in place on an IPU. We've got very general factor graph formulation that allows us to think of all sorts of different measurements, sensors, and priors, all contributing to the same graph, and gradually leading us towards this more abstract and useful representation. So have a look at this paper if you're more interested in the details of that. Okay, I've finished there, so let me just quickly make some conclusions. So I think spatial AI research is very exciting. So some of the key things to work on are efficient 3D scene representations and systems for incremental scene understanding, co-design of processes, sensors, and algorithms, and graph-based algorithms for estimation, such as belief propagation. I'm also very interested in graph-based algorithms for machine learning, but I don't yet have much experience in that area. And just quickly to mention and to thank my colleagues at my affiliations. So the Dyson Robotics Lab that I lead at Imperial College, it's an academic lab funded by Dyson, collaborating with Dyson, where we do academic long-term research on SLAM, scene understanding and manipulation. And I'm also co-founder of the London-based startup called SlamCore, which develops applied spatial AI solutions. So thank you very much.
Thank you very much, Andrew. I'm sure we can imagine over 300 people applauding right now, including me. So thanks again. We have some questions posted. So let me just pick some. There is one that is I find also interesting. Is what are the differences for spatial AI from the point of view of applications like AR indoor or self-driving scenarios outdoor?
What are the differences? So yeah, as I mentioned, so I would hope that there's a lot of commonality between the spatial AI system that might apply to either of those situations, but with certain both constraints and parameters of performance that would differ. So clearly, indoors versus outdoors, there's going to be different categories of objects and that you would need to semantically represent. There's going to be different levels of accuracy needed, maybe different levels of speed of your platform, and different sorts of sensors available. So outdoors, for instance, you've in a driving scenario, you'll probably have some prior maps to rely on. We know the map of a scene. We'd also have strong knowledge, for instance, that cars are moving essentially on the 2D plane of the road and moving in this non-holonomic way that cars drive. On the other hand, there are things that make it very challenging, like extreme safety constraints. Make a bad mistake and it's very serious. you know, indoors, there are other things that make it more challenging. There's a lot more variety of objects indoors. There's often rooms with huge blank white walls that are very hard to deal with. You know, maybe there are people and maybe animals or other things moving in close proximity. So I think that there's definitely going to be different challenges, but I hope that there are core elements of just how you would design the essential, you know, graph-like structure of how to represent that scene to enable useful action, which I think would be common.
Okay, so I have another one in the whole system. As you presented, there are so many components and connect together. So is there one in particular that is holding the rest sort of back in terms of you know, what's required in general?
Yeah, that's a really good question. Yeah, I'm not sure I could really put my finger exactly on one. So I think in terms of a performance parameter where it feels like we're not there yet, it's sort of robustness and the ability to deal with changing situations. So that really involves a lot of the components of the system. But for instance, you know, in semantic labeling and scene understanding, we've probably all had these experiences where you train your system on some particular data set and then you try it. You wave a camera around in the room that you're in, and it really doesn't work that well. So how do we overcome that? I think some of the things I'm most interested in at the moment involve more sort of unsupervised learning type of methods, and this idea perhaps of scene-specific networks. So you might actually expect, you buy a cleaning robot and put it into your home. I think it's reasonable to expect that robot will actually do some quite scene-specific learning within that space and then maybe even ask you a few questions. You know, it needs a few labels probably, but hopefully not too many. But yeah, to what extent can that learning be done in a way that's actually useful to a user? Clearly, what's not going to be available is full, you know, labeled data of every scene that it's going to go into. So what combination of, you know, transferring things from other scenes, using, you know, unsupervised learning just to make use of unlabeled data that it can get for itself, and then I think a small amount of labeling that it could get maybe by, you know, asking questions of its owner or user would enable the right performance.
Okay, so there are also a couple of questions actually related to scene code, and let me combine them. So what do you think is sort of particularly well suited for SLAM in terms of codes in VAE? And what is the trade-off between representation and FE that you have to strike somehow?
Yeah, so I think speaking specifically about, you know, scene code and code SLAM, those kind of methods. So they're really trying to give you a sort of optimizable basis for depth and semantic labels. So we know that single view prediction is quite good. So single view depth or single view labels, but we find that often there might tend to be some quite gross errors. So for instance, if I point a camera at a wall, it will probably do a quite good job of telling me this is a flat region, but it may be that it's, you know, a meter or two off with the absolute depth of that wall or with the orientation of that wall, for instance. And the same with semantic labels. So if I point it at a flat region in my scene, it may not be sure whether that's, you know, part of a floor or part of a table. Those two things are just quite ambiguous. So we want to give the ability to do multi-view optimization, but in a smart way. So compared to semantic fusion, if you want to take single view labels from multiple views and fuse them, you do that just by per pixel averaging the labels. And what that tends to give you is this very sort of noisy type of fusion. So whereas what we do in scene code is we do code fusion by joint code optimization. So if there's one image where a certain region is labeled as a table and one image where it's labeled as a floor, it's not just going to kind of average those things. It's going to find really which of those two is most consistent with everything else. And then, what should happen and what normally happens is the whole of that region will eventually confidently turn to one or other of those classes, which is the most sensible thing to do.
Okay, maybe a final question. In the context of IPU chip, how to deal with a long-term SLAM problem? If there are limits on the chip in terms of memory, of course.
Yeah, no, that's in fact very much something we're thinking about at the moment. So this idea in a on a chip like that, I think what you really want to do is sort of take your factor graph, which is representing your whole estimation problem, and sort of lay it out geographically on that chip, and then do in-place computation. But clearly, it's a problem if your graph just gets bigger and bigger. It's eventually not going to fit onto the chip at all. The chip has limited memory. I think the right route there, and what we're very much working on, is incremental abstraction. So imagine that you'd detected and mapped 100, let's think of just points at the moment, on something like a wall. At some point in time later, you're going to hopefully realize that there's a simpler structure that describes that 100 points. And it could be that there's an external, maybe a neural network has looked at that frame and given you a fairly confident prediction that, this region of the image looks planar. Or maybe just by pure introspection, those 100 nodes, by talking to each other, have realized, hey guys, it seems like we're all quite coplanar here. So I would then think the right thing to do is to replace those 100 nodes by a single sort of supernode with the parameters of a plane, which then connects to all the other things that the individual points were connected to, and you've turned 100 points into 1 point. And if you can then do that incrementally and eventually hierarchically, so maybe you simplify to planar regions, and then different planar regions join themselves up into large planes, and then maybe multiple orthogonal planes join themselves up into boxes and rooms and things like that. That for me seems like a way that you can just keep going. You can keep your graph of a sort of bounded size and keep this purely graph-like operation.
Excellent. Thank you very much again. And let me thank both speakers for a great talk. And I just give a quick applause from everyone in YouTube and Zoom. And so that is the first part of 2 invited talks of this morning. So thank you, Andrew.
Thank you.
And let me hand over to Wenxia Wang that will now present the challenge.
Okay, thank you, Kristen. Kathy,
yeah, I can go ahead. Okay. 1 second. Share my screen. Okay. Can you see my screen?
Yes.
Okay. Hi, everybody. My name's Sebastian Scherer. I'm an associate research professor at the Robotics Institute at CMU. And I wanted to give you a little bit of a background on kind of why we went down this route of creating this data set for this challenge, and kind of give you a little bit of context, and then Wenxia will go and talk more about the details, how we made this challenge, and the data set itself, and the creation metrics and so on. Okay, I think a lot of you know, real-world imagery is challenging and noisy, and so I just want to kind of give you some examples of the kinds of problems that we are interested in looking at, and then some kind of more philosophical thoughts maybe that might bring up some discussion. So one of the problems that we are working on right now is the DARPA Subterranean Challenge. And so this is underground, having a team of robots trying to find objects as accurately as possible. So it's really, it's a lot about SLAM because you have to localize these objects, and you only get a point if you're accurate enough. At CMU, together with Oregon State University, with a Team Explorer running in this challenge. The part that's kind of very relevant here is this problem of degraded sensing. So these environments we're in, the typical environments are tunnels, urban environments like subway stations, power plants, and then caves are kind of the three types of environments. And they're not necessarily lit. Sometimes they're light, sometimes there are no lights. There are fog, dust, lots of challenges in these systems, and you have to make SLAM, and you have to make SLAM robust enough that you trust your robots to run autonomously with it. So our approach right now it consists of two sets of robots: a ground robot, three ground robots. You see one of them here in the picture that have a custom perception payload and some communications nodes that drop, and then a custom drone that's optimized for flying indoors, also with a perception payload on board. And of course, one of the things we would like to do is to remove the heavy lidar on top. I think that would be very desirable. And there is a lot of effort underway for this, but for now we're stuck with what systems that work reliable. Just to give you an idea of the kinds of environments we're testing in. So here's another of our ground robots climbing upstairs. And then here's a quick video to just kind of show you what this kind of challenge looks like. So the beginning is from August last year was the tunnel circuit. So this is kind of how it looks like inside. So you can see is lots of specular reflection from the water, dim light, some fog from condensation. So here's kind of our ground robots going inside the tunnel. Here's the drone. You can see it actually kicks up quite a dust cloud as well when it's flying inside. Then here's some of the fog that DARPA has set up, and this can get quite thick. Something else you can notice here is there's a lot of kind of dust particles that reflect off. And then this is now from February in the urban circuit. So the drone actually takes off from the back of the ground robot, all fully autonomous. And then here it descends down into a shaft and then explores the bottom level. You can see, there's no light here. This is dark, so it's a pretty challenging SLAM problem as well, in addition to the other challenges. Now, something. Oops. YouTube. So some other kind of example of a problem we're looking at is, for example, for bridge inspection, and so this is inside of a bridge, and here is very dim light. And you can see actually the picture is pretty blurry because of motion blur, and so that actually causes lots of problems when you want to try to do 3D reconstruction. And in particular, what we are really going for is one of millimeter level reconstruction of large structures with cameras. So it's particularly we're looking at a lot of stereo data here. And So we've been able to get quite good results, but it's a challenging problem because as the image noise goes up, a lot of these algorithms start to fail. And just kind of like a last example of problems that we're interested in is, this is now a little old, but I think still relevant, was for example, to detect fires inside a ship. Mute this. So this is flying inside the ship using some cameras, downward pointing cameras, forward-looking RGBD sensors. Everything's on board here. This is now 6 years ago, and so there's the ship's on fire, so there's visual images are not very good, but are present. And so we tested this, for example, with oil fire, wood fire, and also we also have a thermal camera on board here, but in this particular example, we're not using that thermal camera. But those are, since our research area focuses a lot on flying, of course, cameras are very desirable because they, in terms of the size and weight, if you exclude the computation, they're very small. So just kind of to give some context here, I think if you look at visual SLAM methods right now, they have a lot of potential, but the success for autonomous systems has been a bit limited. And I think that comes down to part of it is just due to a lack of data sets, and I think that was kind of what drove this. In some sense, if you're doing any, and part of it has been also a shift in terms of methods towards learning-based methods. So if you look at UROC and Kitty data sets, these data sets are very popular, but if you develop a system and only train and test on these data sets, you're really doing the community a disservice, because these data sets are not broad enough that they're really and diverse enough that they really exercise these methods with these large number of parameters well. And the other part that kind of brings out is that it's very easy to measure accuracy, and so a lot of SLAM research has kind of focused, we're more accurate than this and more accurate than this method, but it really comes down to often robustness. And for autonomous systems, you might be more willing to accept drift and less accuracy for a more robust solution. And so maybe so just to kind of highlight this, right? So I think this is where a lot of research is on, okay, how accurate can we be? But actually, for autonomy, this other axis is probably more important. And so this kind of led us to try to design this challenge and put forward this data set to really kind of push and get a good sense of methods, try to include some things like weather and other degradation to make it a more relevant challenge than the kind of data sets that are very popular right now. So we have a total of $5,000 in prize money, thanks to Microsoft, and then Venshan will tell you a lot more, and I hope will convince you to participate in the challenge. I think it will be quite exciting, and we're very curious to see what these kind of different methods trade-offs are, and if you can really kind of get some of these methods out. So, for example, Daniel mentioned this D3VO. I think will be very interesting to see how that will perform on the challenge data set, for example. Okay, should I hand over to you, Venture?
Okay, thank you, Basti. So let me share my screen here. Okay. Sorry. Okay. So my name is Wenshan Wang. I'm a project scientist in Carnegie Mellon University. Okay, I'm going to introduce this SLAM challenge in the CVPR 2020 workshop. So this challenge is a joint work of the Air Lab at CMU and the Area Informatics and Robotics Group at Microsoft Research. In particular, I would like to thank all my colleagues, Dalong Zhu, Xiangwei Wang, Yao Yuhu, Yuhen Qiu for the great work, and the supervisors Ashish Kapoor and Sebastian Scherer for the tremendous support. Our challenge is about the visual SLAM in challenging environments, as Basti just mentioned. So we have a monocular track and a stereo track. So each track contains 16 trajectories, which consist of 8 easy trajectories and 8 hard trajectories, respectively. So this is an ongoing event. The deadline will be on August 15th, which is 2 months away. Please check out our workshop website for detailed information. So as Basti just mentioned, the motivation behind this challenge is to push the limits of the current visual SLAM algorithms in challenging scenarios with degraded sensing. We hope to utilize this challenge to first identify the limitations of the current visual SLAM algorithms, and secondly, overcome these limitations. So how can we do this? First, let's take a look at some of the most popular benchmarks for visual SLAM. These data sets have been around for many years, during which they really push forward visual SLAM research by providing practical testing cases, standard evaluation metrics, and so on. However, each of these benchmarks only covers 1 or 2 types of scenes. For example, the Kitty dataset only contains data collected in the driving scene. The data in Europe is collected in a machine hall and a room environment. And the TUM RGBD dataset is collected in office environment. Besides, they provide relatively small number of data from the perspective of deep learning area. If you look at the motion patterns, they are constrained by the data collection setup. As you can see in at the bottom, we did a principal component analysis on the camera motions. The figure shows the 3 principal components of the translation and rotation motion, respectively. The data from Kitty has 1 dominant axis in both translation and rotation, because we know that the vehicle is mostly moving straight forward combined with small left and right turns, which is like 2D motion. The U-look is collected by a UAV, which is obviously would have less pitch and roll motion. Although the TUM RGBD dataset is collected by a handheld camera, it still shows large motion bias. So we argue that the lack of motion diversity has 2 limitations. First, the simple motion is insufficient for evaluating a visual SLAM algorithm. I'll show some experiments later to demonstrate why motion patterns is important for the evaluation. Second, learning-based algorithms trained on these data cannot generalize to other tasks with different motion patterns and will become biased. Therefore, we'd like to create a benchmark with diverse testing scenarios, with challenging scenes and diverse motion patterns. So, as we can imagine, collecting real-world data and ground truth labels is very expensive. It often relies on an elaborate sensor setup and careful calibration. The ground truth of the SLAM task usually comes from other high accuracy sensors such as LiDAR, GPS, or motion capture system. As I mentioned, the data distribution is often constrained by the physical property of the hardware. With recent advance in computer graphics, many synthetic datasets have been proposed. We also take advantage of this. We utilize the photorealistic simulation environment AirSim, which is developed by Ashish and his group. The simulation provides reliable ground truth labels with very low cost. However, one biggest issue is known as sim-to-real gap, which means the algorithm's performance will drop when transferred from simulation to the real world due to distribution difference. How can we overcome this problem? Our solution is large size and diversity. So this idea is borrowed from the successful story of domain randomization, namely increasing the diversity of the environment. The model learned in simulation could be easily transferred to the real world. In our Titan Air dataset and the testing cases in this challenge, we set up diverse scenes, including urban, rural, domestic, public, and sci-fi. Our dataset contains a large number of label data, which is an order of magnitude larger than the existing dataset. Besides, we lose the motion constraint, which results in an unbiased motion pattern. A spatial focus of this challenge is in challenging things, such as changing light condition, low illumination, reflections, adverse weather, dynamic objects, and so on. Here are more examples of scenes in this challenge, including day-night changes, low illumination and the changing of light, bad weather, such as rain and storm, and moving objects, like machinery and fish and bubbles. So, well, can we really identify the limitation of visual SLAM algorithms use these synthetic data? So we tested ORB monocular and ORB stereo algorithms on the 8 hard trajectories in this challenge. ATE, KT metric are commonly 3 common metrics for the visual SLAM algorithms. We can see the arrow on the ATE and KT metric is very large. But we found these 3 metrics are less distinguishable in our case because the algorithm often lose tracking of the camera poses. So we show another metric called valid rate, which means the percentage of frames that have valid pose estimation. So this evaluate more towards the robustness instead of accuracy. Under this metric, the monocular algorithm only have 50% valid rate, and the stereo algorithm is more robust, over 70% valid rate. As a comparison here, we also show the performance of ORB stereo algorithms on KT dataset. We can see a huge gap, which indicate how they are suffering in our data. Okay, we found many interesting failure cases. The figure shows where the ORB monocular lose tracking. Typical reasons are getting close to an object, moving objects, illumination change, dynamic object in the scene, in this case, a falling leaf, and reflections. In the stereo cases, it's more robust to moving objects and illumination changes. We found many failures are caused by lack of features, also the reflections and moving close to an object. We've spent many efforts setting up the challenging scenes. So the next question is, are these challenging features really matters for the visual slam? So we did this experiment. We turn off the challenging features and collect the data along the same trajectory in the environments as the video shows here. So as we can see from the table, by adding the storm and changing from a day scene to a night scene, the performance of both monocular and stereo methods drops significantly. At last, we show how the algorithm performs with respect to different motion patterns. We set up 3 levels of difficulties. In the easy setting, we only have translation and raw rotation. In the medium setting, we use 6DOF slow motion, and hard setting has a 6DOF fast motion. The experiments show that the motion pattern has a huge impact on the performance of all the 3 methods we tested. The successful rate dropped significantly and constantly with the increasing of difficulty of the motion patterns. Now let's move on to the harder question. How can we overcome the limitations? As I mentioned, using simulation, we can provide multi-modal reliable ground truth labels. If you go to our website, you can download all these data, including RGBD stereo image, depth image, segmentation, optical flow, and camera poses. This allows people to explore many research directions, such as SLAM based on the semantic information or multimodal SLAM. Obviously, people can also explore learning-based methods, since we provide all of these data as a training set. In our preliminary experiments, we trained a simple neural network for the visual odometry task on our large training data. Then, without any fine-tuning, we directly tested the model on the KP dataset. As shown in the green line, the network outputs reasonable results without seeing any of the real-world data in the training time. Our simple model even outperformed ORB monocular without loop closure, which suffers from a big scale drifting problem. At last, I'd like to talk about the hard work behind this challenge. In order to enable data collection in this large scale, we developed an automatic pipeline. First, we implement frontier-based methods, algorithm, which can automatically calculate the next exploration location. So the frontiers are shown as the blue cubes here. So we use RT star planning algorithm to calculate the collision-free trajectory, which guides the exploration in the free space. So then we sample the nodes and edges in the free space, and the nodes and edges are stored in a graph data structure. Then we sample the trajectories from the graph. In the data collection process, we randomize the incremental distance and angles along the trajectory. The poses are then sent to a virtual camera in the simulation, and we record all the data. After we get the raw data, we then calculate the ground truth optical flow by image warping. We also calculate a mask for the occlusion and dynamic objects. At last, we verify the data to make sure the data are synchronized and eliminate missing frames or bad data such as large occlusion. So as a summary, this challenge aims to set up a benchmark for challenging scenes. It provides large amount of training data with multi-model labels. So we hope this challenge could push forward the visual SLAM research, and we welcome both learning-based methods and non-learning-based methods to participate in this challenge. Again, this is information of this challenge. I hope I can see you in the award ceremony. Okay. Thanks everybody for the attention.
Yeah, so there's 2 more months until the deadline. The deadline's August 15th at midnight.
Yes. Yeah, there's 2 months away. Okay. Is there any questions from the audience?
So I think we have a couple of questions in the Google Doc. So I think one of them is about the tunnel exploration. So how do we evaluate which one's better? I mean, the metric for how do we evaluate if it's better to have 2 versus 1 robot for the tunnel? And so it's really the time limitation. So we have 1 hour to find as many objects as possible. And having more robots allows you to cover more space, since the space is a couple of kilometers long. Next question is, which kinds of perturbations are particularly hard to be robust to? What types of perturbations where we may be close to breakthroughs? Wenchen, do you want to take this question?
Mm-hmm. As we showed in the slides, so we found that our finding is kind of consistent with a lot of research, review research. They report their difficulties in the visual SLAM algorithms, like lack of features. Like if you're moving too fast and if you are very close to an object, then the scene changes a lot. Then it makes the visual SLAM suffer. And also for the dynamic objects, if it takes large part of the field of view, then it definitely will be a very hard question, a very hard issue. We also found those storm and rains be added to the scene also create a lot of difficulties. Okay. Right.
I can read the next one. Maybe you can answer that one too. So how do you define if pose estimation is valid compared to absolute ground truth or pose changes?
Mm-hmm. So we trying to eliminate multiple types of invalid cases, like if there's some error in synchronization, then so basically we do this by warping the image using the optical flow. We calculate the optical flow is calculated based on the camera pose and the depth image. Then we warp the right image to the left image using this optical flow. So that's basically include all the data we raw data we collected from the simulation. So if everything is okay, so when you look at the photometric error, that would tend to be low. Yeah. So we will eliminate the unsynchronized image, and sometimes there's missing frames. Also, there will be occlusion, or sometimes the camera goes into an object, will cause some big occlusion, and we will delete those data from our data set. Okay, so I guess that's all for the questions.
Okay, also there's one question on the IMU data. Yeah, so IMU, we're working on adding the IMU simulation.
Mm-hmm.
And there are some more things that we're potentially adding in the future. And then maybe one thing that might be good, Venture, is if you could just show the website, maybe quickly, the AI Crowd website.
The AI Crowd, right?
Yeah. So right now the data set has about 400,000 images. And so trying to increase that in the future.
Mm-hmm. Yeah, if you go to aicrowd.com, so you click challenges here, you can navigate through and find our challenge here. So this is for monocular track. You click here, here's a 0 track. We've already got a lot of submissions. Yeah. Actually, I already saw some submissions that have already outperformed the ORB baseline we put there.
And then, Venture, maybe you could say a little bit about like how many environments and what environments for the evaluation are.
So we provide 16 trajectories for each track, and they are all come from one different environment. So we're using very diverse things as this testing set in this challenge. So there are more information if you just look at the website of this workshop. There are 2 examples of the how the sequence look like. This is one scene, and this is the outdoor scene, and on the right is the indoor scene. Right. Okay. So we provide some tools for the challenge. If you go to the GitHub here, AI Crowd, you can find the what is here? Oh, this is it. Yeah. Okay. No.
Yeah, so we have some tools for evaluating, running the data, and since the data is quite large, one of the things that we're also doing is we kind of have a way to use it easily in the cloud if you don't want to download, I think, what is it, like 3 terabytes of data. You can just use the data in the cloud.
Right, here's the GitHub repository for how you can download and show, display, visualize those data. Yeah, I think it's quite easy. You can also put issues like all questions here. Right. Okay. Then there's no more questions.
There's a question here. Do any of the sequences contain complete loops?
Right. When we sample the data from the environment, we always sample a loop. But in some cases, if there's a invalid data, so we just we will cut the trajectories. So we cannot guarantee every trajectory has loop, but I think most of them will end up to the starting point.
Okay. Any other questions?
Okay. How about
we're a little bit ahead of schedule, right? Like a couple minutes.
Yeah, we can take a break till the next speaker. Or
Luca, are you on the, yeah, you're on the line. Yeah, okay, cool. So maybe should we take a couple minutes break? Maybe okay. Let's see.
10 minutes.
10 minutes. So we'll be back in 10 minutes, and then if you want to set up, Luca, maybe then it'll be all ready for you.
Sounds great. Okay, thanks.
Okay, see you in 10 minutes. Okay, so welcome back, everyone. So let's wait, let's start exactly on time, maybe in 2 minutes. Yeah, I think this virtual format of the workshop has its pros and cons. I think pros is, I think maybe more people get to see this than would have seen it otherwise. Con is maybe it's a little harder to have some discussion and exchange. So I think we'll try to do our best to make that exchange as lively as possible and do our virtual claps. And so it's my pleasure to introduce Luca Carlone. He's an assistant professor at MIT. He got his PhD from Polytechnic University of Turin in 2012, and then he was a postdoc at Georgia Tech, and then went to MIT, and he's also a co-competitor in the Sub-T challenge. So I think it's always exciting to hear what the next thing is. I think without further ado, let's hear from Luca. Okay.
Thank you so much for the introduction. I'm assuming that you can hear me well and you see the slides, right?
Yes.
Perfect. Okay, so I'm really enjoying the workshop. I think it's a great event, very inspiring talks this morning, and I'm really excited to tell you about the work we are doing towards getting beyond SLAM. And in particular, I'm going to cover certifiable perception and high-level understanding, which I believe is a perfect follow-up on Andy's talk. As Basti mentioned, I'm Luca Carlone. I'm assistant professor at MIT. And probably a good starting point for this talk is to have a one-slide introduction about the work in my lab. So I'm the director of the Spark Lab. Spark is Sensing, Perception, Autonomy, and Robot Kinetics. And my lab is working in the broad area of robotics and autonomous systems. And I'm particularly interested in perception for robotics and in computer vision. So over the last few years, we've been working on a number of topics, which I'm summarizing in this slide. We've done a lot of work in essentially making a perception algorithm robust and ready for the real world, ranging from work on visual inertial navigation to work on LiDAR-based LAM, including the one that we are using right now for the DARPA Subterranean Challenge that Basti mentioned. We have a lot of interest in high-level scene understanding and what Andy mentioned and called spatial AI. And I'm going to cover a couple of topics in this domain, including chimera and the notion of 3D dynamic scene graph. The lab is also interested in other aspects which are beyond perception a little bit and are about communication and computation trade-offs and processing networks, as well as more embodied aspects of intelligence, including drones and manipulation, but I'm not going to cover those today. So the plan for today is pretty simple. I want to give you this talk in two parts. First, I want to tell you about how to go from SLAM to high-level understanding, or at least the baby steps you are taking in this direction. And I'm going to cover works which are fairly recent, including Chimera, which is an ICRA 2019 paper, and 3D Dynamic Scene Graph, which is an RSS paper. And then I'm going to mention something that is a new approach, essentially, to geometric perception, which leads to the notion of certifiable algorithms for geometric perception, which again is very recent work, including papers at ICCD, RSS, and recent archive preprints. So let's start with the first part. So the work on high-level understanding is the result of the work from students in my group, including Tony, Marcus Arjun, Yun, and Jinnan. And I want to start with a basic observation. The basic observation is that as a community, we should be really proud of the accomplishment we made in the context of SLAM. So implementations like OrbSLAM or DSO or the variants of DSO that Daniel covered this morning are really like enabling impressive results in terms of reconstruction of sparse and semi-dense 3D environments in real time. And more recent implementation based on event-based cameras like the ones in the group of Davide Scaramuzza are also pushing the boundary of agile camera motion. So very fast and very agile camera motion and 3D reconstruction. I'm not saying that, SLAM is solved. Of course, there are a number of issues and limitations that have been recognized also by the previous speakers in terms of robustness, efficiency, and so on. But the good news is that really the progress in the community, in the research community, is steadily transitioning to products and to industrial technologies. So I'm putting an example here, which is the Skydio one drone, which is using a vision navigation. Of course, products outside robotics like the virtual reality goggles or Pokemon Go are using similar algorithms for visual inertial navigation, visual inertial odometry. And startups are still pushing the boundary in terms of computation, in terms of sensing and sensor fusion. We heard this morning about Artisense and SLAM Core. So we really have to be proud about this progress. Unfortunately, we're not done yet as a community. And to realize that we're not done yet, we have to just put things into perspective. And the exercise that I usually do, which I find really useful for putting things into perspective, is to look at the gap really between robot perception and human perception. So for robot perception, we've been doing great progress in creating real-time sparse and dense point cloud maps. Andy Davison mentioned work and pioneering work on object-based maps. So we're getting very good at creating this geometric representation of the environments, which of course go beyond point and objects and include also lines, voxels, meshes. So I've been getting very good at getting these representations. And of course, I'm not putting references here because probably most of these representations are capturing 80–90% of the entire SLAM literature. This is not quite what human perception is able to do. And I don't have to explain you, I just have you see for yourself what human perception is able to do. So if you stare at this image on the right for a few seconds, you realize that as a human, you have a simultaneous understanding of the geometry of this scene. You have an understanding of the semantics and the use of the objects. For example, you understand that yellow cars are actually special cars, which are essentially taxi with a specific functionality. You can realize that there are multiple people, objects, and you can also understand their relation. For example, you can figure out that this person with the yellow sweater is probably trying to cross the street, or that couple of people are working together. So this is a very, very rich understanding, and with robotics, we are not there yet. Of course, this is not just a matter of an intellectual pursuit of bridge the gap between human perception and robot perception. The fact is that these limitations in robot perception are really constraining applications. I have robotics as my motivating application, and in robotics, it's pretty clear what is the gap, right? So right now, most of the robotics application require really the robot to think about 3D location, X, Y, Z Cartesian coordinates. For example, to assign a location the robot has to reach. But ideally, I would really like to speak to my robot with a very different language. I would like to tell the robot, pick up this coffee mug near the sink in the kitchen. I would like to issue really high-level commands, which right now the robots are not able to understand because of their limited capability of understanding the external world. Of course, this is not a problem just for robotic manipulation and for domestic robotics. Self-driving cars incur in the same issues in which essentially the limited capability of the robot to understand the car, to understand the world, is really limiting the safety and robustness of these systems. Same holds for augmented reality. So in other words, I would really love to see something like an Alexa, which has some true understanding of the environment, for which I can just tell Alexa, where did I leave my coffee mug? And this future ideal Alexa can answer me that I put the coffee mug on the table near the window in the dining room. Of course, answering this kind of queries requires a sophisticated understanding of the environment, which is currently out of reach for products. Probably Alexa would answer at this point, I have no idea what you're asking me, so I have no idea how to answer that. So high-level understanding has the potential really to enable a number of applications and is still out of reach for robotics. And over the last 2 years, we've been really pushing towards bridging this gap and getting to vision system and SLAM system that can reason both in terms of the geometry and the semantics of the 3D scene. So here I'm going to present Chimera, which is a library that we just released, which is capable of doing real-time metric semantic simultaneous localization and mapping. And you can see that you can see on the top left here that Chimera is essentially creating this 3D mesh model in which the 3D geometry encoded by the mesh is also semantic annotations. For example, the green here corresponds to walls, the gray is the ground, chairs are in green, and desks, I think, are in yellow. Okay, so the input to Chimera are images and inertial measurements, and the output is this nice mesh with semantic annotation. So it's this understanding of both geometry and semantics in 3D. So in the next few minutes, I want to tell you a little bit more about the building blocks of Chimera. But I want to stress that everything is open source. We have a very good implementation led by Tony, and you can go and check it out online and just use it for your application. We have also a nice tutorial how to use Chimera with the real sense. So the building blocks in Chimera are essentially 3. The first one is visual inertial odometry and the mesher. Then we have post-graph optimization. The R stands for robust post-graph optimization. And then we have the semantic module. So let me start with the Chimera VIO, visual inertial odometry, and Chimera mesher. We have probably one of the best visual inertial navigation algorithms and implementation out there. So we are leveraging a fairly standard and established idea, which is IMU pre-integration. What IMU pre-integration does is to enable real-time VIO using an optimization-based approach. Optimization-based approaches are known to be very accurate, but without this idea of pre-integration become quite slow. We can do essentially optimization-based visual inertial odometry at 20 Hertz for keyframes and more than 100 Hertz for every other frame. Essentially, we can go at IMU rate for visual inertial odometry. Not only Chimera VIO is very fast, but it's also robust. So there is this idea of outlier robust feature tracking using what are called structureless projection factors, which is again an idea that we introduced back in 2015 and back in 2017 in the journal version of the paper. And I'm going to show you that essentially this VIO solution is achieving top performance on the Euroc dataset. So we have very good and accurate VIO baseline here. Something that you have seen in the video, but I'm not going to discuss too much, is that on top of doing standard sparse visual inertial navigation, sorry about that, Chimera is also able to build a 3D mesh, fast 3D mesh, just based on the landmarks in the VIO. And this is very fast. It's happening in 20 milliseconds or so. So it's a very quick mesh. The second block in this architecture is Chimera robust post-graph optimization, which is in charge of enforcing the loop closures. So loop closure detection here is nothing fancy. We're using just bag of words and VBAU2, which is pretty much a standard choice. It's the same used in OrbSLAM. But the catch, or the new insight here, is that we have a very effective way to reject bad loop closures, which is based on this idea of pairwise consistency maximization, which essentially, when forming the post graph, is looking at pairs of loop closures, which are mutually consistent. And you can see the result here, essentially, on the left. There is what you would do post-graph optimization without outlier rejection. And you can see that the trajectory really looks a little bit messy. On the other side, instead, we have what happens with the outlier rejection. We have a very clean trajectory because we are able to reject bad loop closures. I want to point out that this is an incremental implementation. There are some new ideas. So essentially, the idea was there already in the ICRA 2018 paper from Engel, et al. So on top of the localization part, which is Chimera VIO and Chimera post-graph optimization, there is the semantic part. So after we had the trajectory of the robot, we want to make sure we can reconstruct a 3D mesh of the environment and annotate semantically this 3D mesh. So the dense semantic reconstruction is done using a volumetric approach. And in particular, we're leveraging box blocks, which is a very efficient implementation from ETH. And we're adding on top of that some semantic understanding. In particular, we are back projecting a 2D segmentation like the one that you see here at the bottom right of this slide. So this is the result of a standard deep network for 2D semantic segmentation. What we are doing, we're using ray tracing and Bayesian updates to essentially back project this understanding to 3D. And the very interesting thing, which is really separating this kind of work from works like semantic fusion or like pioneering work from Andy, is that we are really focusing on CPU. We're assuming that we have to run this on a drone, for example. We really want to have something that is very fast and is running in CPU. And currently, this is the case. We're able to get the 3D reconstruction and the semantic understanding on a standard CPU running at 10 Hertz here. So let's be a little bit more quantitative here at assessing how Chimera is performing. I mentioned that we have very good results on the UROC, and I want to give you a few figures to support this claim. So I'm claiming that essentially Chimera VIO and Chimera Postgraph optimization are currently one of the best localization solutions on the UROC drone dataset. And you can find, of course, the details in the paper, but this table is showing the RMSE absolute trajectory error in meters for all the UROC datasets and for a number of techniques. And in particular, we are comparing fixed leg smoothing techniques with full smoothing techniques and techniques without loop closure detection and with loop closure detection. So the interesting thing is that for Chimera VIO, switching from fixed leg smoothing to full smoothing is really a parameter that you can set in the YAML file. So it's really straightforward. And here again, this is the error in meters. And the bold numbers are the one getting the lowest error in that category. So you can see that Chimera VIO is essentially doing very well here across, compared with all the techniques. And this is a drift that roughly is in the order of 0.2% to 0.5% of the trajectory, depending on the data set. The full smoothing, of course, full smoothing is much slower typically, but it gets you an error reduction, which is pretty substantial. So you can see that you can get here into the order of 0.1% error of the entire trajectory. And of course, loop closure helps. And again, we can compete in a favorable way against beans with loop closure. UROC dataset, I will not cover it, essentially Basti and in the previous presentation, we realized that it's a drone-based dataset. I'm going to mention that we did also an extensive evaluation of the semantic reconstruction part. For the semantic reconstruction part, we have a Unity-based photorealistic simulation in which we can get ground truth for all the quantities we want. And visually, Chimera is getting pretty nice, for being real time, is a pretty nice 3D reconstruction with semantic labels, which you can compare visually to the 3D mesh that is behind the Unity simulator. And you see that visually, it's looking pretty accurate. There are numbers in terms of accuracy of the semantic reconstruction and the geometric reconstruction, which essentially are showing that the reconstruction is pretty accurate. I will not go there because I'm running a little bit late on time. So this is Chimera. You can check it out and you can download and compile on your computer. But we realized that after releasing Chimera, we realized that really that was only the first step. So we realized that again, if you do the exercise of thinking about what robots are capable of doing and what a human is capable of doing, we realize that metric semantic SLAM is still less than human understanding. So in Chimera, we get these essentially metric semantic 3D mesh. But again, if you stare at our image for human understanding, we realize that humans are really able to understand the environments at different level of abstraction. So we can look at this image, we can think about objects, we can think about roads, we can think about buildings, cities, and really different level of abstraction of the environment. At the same time, we're also pretty good at capturing, again, relations among objects. For example, the fact that one car is following the other, is on the same lane as the other, or some person is trying to cross the street. Okay. So what we have done in the last few months was really to try to get a step closer to this idea of human understanding. And we did that through a representation which I think is quite powerful and is what we call 3D dynamic scene graphs. So a dynamic scene graph is a directed graph where the nodes in the graph are spatial concepts. So there are concepts which have a grounding in 3D. For example, rooms, people, objects, and so on. And ages represent spatio-temporal relation between concepts. For example, a person I is in room J at time t. So we believe that this kind of representation, first of all, is capturing, we designed this representation in a way to capture a different level of abstraction. For example, in an environment, we have multiple layers in which we capture the low-level geometry, we can capture the presence of humans and objects, structure, places, rooms, and buildings. So you can see really this level of abstractions going up. And also we can capture agents in the scene. So it's really like, an interesting work to bridge the literature on post-estimation for humans with the literature on SLAM and 3D reconstruction. I will get there, but you can see that essentially in this layer, object and agents, there are the red people that we are able to track in the environment. So this representation is also actionable because essentially the robot can has enough information to decide, to do queries like path planning, for example. I also suggest for you to check out a work that was really an inspiration for dynamic scene graph, which is the work on 3D scene graphs from Armenia at ICCV 2019. What we are doing on top of that is really to make these a spatio-temporal representation rather than an instantaneous snapshot of the environment, and to add extra information in the scene graph, which are really able to be useful for a robot to navigate. So we started pushing on this idea of scene graph, and we consider really, really challenging environments to create this representation. So the goal of this line of work was really to create a 3D dynamic scene graph from visual inertial data, sorry about that, in heavily populated environments. And in hindsight, what we are really proposing is a transition from 3D SLAM algorithms to what we call a spatial perception engine, which is able to infer geometry, semantics of the scene, and is able to create a hierarchy of high-level spatial concepts and their relation. So how do we do that? Well, I think this is the perfect follow-up on Chimera, because essentially the output of Chimera provides the first layer of a 3D dynamic scene graph. So the bottom layer of dynamic scene graph is a metric semantic 3D reconstruction. And just as a reminder, Chimera is able to do that with very high rates and is able to do that essentially in real time using visual inertial data. However, essentially here we're moving in a very crowded environment. So we really have to robustify a little bit Chimera to the presence of many, many humans. So what we did is to improve robustness of in dynamic environments by using a 9U-based Luca scanner tracking. And also we use the concept that we call dynamic masking, which essentially avoids to integrate dynamic objects in the map. So if you don't do dynamic masking and you have a person walking in front of the camera, essentially the person becomes part of the map. If you do dynamic masking, the person just disappears because of the semantic label, which is associated to something that is moving in the scene. So this is the result of our reconstruction with dynamic masking. Regarding to layer 2, which is objects and agents, for humans, to detect and track humans, first of all, we have this fairly unique take, which is about getting very dense reconstruction of human meshes over time. And towards this goal, we essentially use an approach for 3D dense shape reconstruction, which is based on a monocular deep learning-based approach from the group of Kostas Danilidis. On top of that, we had a robust post-graph optimization, which is pretty similar to the model we use for the robot, in order to track humans over time. This is for the humans, sorry about that. For what concerns instead the presence of objects, we distinguish two classes of objects. On one side, we use Euclidean clustering, a very simple approach for objects which have unknown shape. And we're going to see these here. So these are objects of unknown shape. We just cluster the corresponding portion of the mesh. And instead, if you have a CAD model for the object, if the object is made of known shape, we use teaser++, which is an approach, state-of-the-art approach for object localization in point clouds, which I'm going to cover in the last part of the presentation. So with the combination of these two, we're able to localize humans over time and to localize known and unknown objects in the scene. And at this point, we can transition to the third layer, which is about understanding places and structure. I will go pretty fast over these. This is essentially something that comes pretty much for free using box blocks, and is about getting a graphical representation of the topology of the environment. So you can see this graph associated with the scene. And the graph is such that each node in the graph is a free space, and edges between two nodes represent traversability. So I can move in a straight line from node A to node B. And as part of that, we can also understand structures, including walls, ground, and ceiling. Moving up in this hierarchy, we can think about rooms. And rooms, we actually have a very nice and simple approach, which is based on graph clustering, which works surprisingly well. So what we do is to have a 3D Euclidean sign distance function, which we get for free from box blocks. We slice it along a horizontal plane, which is near the ceiling, such that essentially we get rid of all the furniture in the room. And using this ESDF and a graph clustering algorithm, as you see in the video, we are clustering the different rooms, and we are also able to establish connectivity among the different rooms. So one thing that I want to remark is that a dynamic scene graph is capturing traversability at different level of abstraction. For example, traversability is of course encoded in the mesh. Traversability is encoded in the topological graph of places, and also at the level of rooms. This is not a bug, it's rather a feature, because essentially what we are thinking about is really hierarchical planning. Depending on the computational resources that you have, you can decide at which level of the hierarchy you want to plan. So this is a pretty exciting vision. Of course, just the first step towards really getting to something that is very robust, is deployable, that becomes a product essentially. But we are very excited about it. By the way, I'm not going to cover the building layer, because essentially we're doing mapping in a single building, so everything ends up being within the building. So that's it's pretty trivial, I would say. So this is a vision towards high-level understanding, but really to build this vision, we need to develop really robust algorithms. And here, besides mentioning a number of contributions to make visual inertial odometry and SLAM more robust, we really need to have algorithms for object detection, which are really robust, which brings me to the second topic in this presentation, which is certifiable algorithms for geometric perception. And in particular, I'm going to call about certifiable algorithms for object pose estimation. So this is very exciting work from Henk, Pasquale, Gingnan, and Vasilis. And I will try to tell you about these in the next 10 minutes or so. So to make things very concrete, let me give an example of application in which you want to detect the pose, to estimate the pose of an object in a 3D point cloud. Of course, there are many approaches to do that, but I would say that one fairly established approach is that we are given a point cloud, in this case, we are given the point cloud of an armchair. And what we do is to do some feature detection and matching potentially. And we detect a bunch of relevant features in the 3D point cloud. Traditionally, has been done using handcrafted approaches, but of course, in the era of deep learning, state of the art is probably going to use a deep network for the feature extraction and for the feature matching. And as a second step, given these features, and given also a CAD model of the object we want to localize, essentially there is a model fitting on estimation part, which is trying to fit the CAD model in a way that is matching the given features, which I'm showing in blue. Okay. So in other words, if you want to localize a known object in a point cloud, we first do feature detection and matching, and then we do model fitting. Of course, this picture is kind of an idealized setup, right? Because what happens in practice is really that I'm given a point cloud. I try to apply the state-of-the-art deep network for feature detection and matching. And what I get is that number of points are actually good. They're the so-called inliers. So I try to detect the bottom right corner of the armchair, and I'm able to do that. The issue is that the deep network will also give me a bunch of outliers. So a bunch of points which are not really what I expect to get. and for which the correspondence with the corresponding point in the CAD model is incorrect. So just to summarize, the first issue that we encounter is that feature detection and matching, both with traditional techniques which are handcrafted or with deep learning methods, can fail in an unexpected way, and is really, if you're working on this area, is really not uncommon to have more than 90% of the detection being outliers, which is a crazy number, but that's what you get. The issue about that is that after you try to use these inliers and outlier to do model fitting to estimate the pose of your object, if model fitting gets like a very large number of outliers, it can essentially fail. So in the presence of large outliers, I try to do model fitting, and instead of getting like a reasonable pose for the armchair, which is fit in the point cloud, I get something that is completely off. So again, issue 2 is that model fitting may fail if there are too many outliers. So in this presentation, this part of the presentation, I want to tell you like some very powerful idea that we can use to improve model fitting. And essentially what these techniques are able to do is to enable effective model fitting in a domain in which you have extreme amounts of outliers. I'm going to talk about model fitting with 99% of the outliers, and I'm going to show techniques which are able to solve model fitting correctly with 99% of outliers. So just to remind you what is model fitting, typically if you're doing like model fitting or standard estimation, we want to search for a variable, the x in this case, and the x in this example is, for example, the estimate of the 3D pose of the CAD model in the point cloud, and we are given measurements. So in this case, the measurements we are given for the example I was showing you are these point features that we extract in the point cloud. And what this formulation is trying to do is to minimize the sum of squared residuals. And the residuals are essentially trying to quantify how well a given x is explaining the measurement yi. Okay, so essentially this optimization is looking for the explanation for the x, the pose of the object, which is minimizing the error with respect to the measurements. And just to essentially be complete about the notation, the M here is the entire set of measurements. So if you worked a little bit on estimation, you know that this is kind of a nonlinear least square formulation. And you also know that if there are outliers, if some of the yi, the measurements, are bad, essentially this will produce a completely wrong estimate. So we'll go back to this kind of wrong estimate in presence of outliers. So what we have been focusing on is really to look at outlier robust formulations. And in particular, we consider a particular powerful formulation, which is called truncated least squares. So if you compare standard estimation with truncated least squares, you realize that there is a lot in common, actually. So the squared norm of the residual errors is also present in the truncated least square in the robust formulation. But in the robust formulation, there is also a theta, which is a binary variable that essentially is deciding whether a measurement is an inlier or an outlier. So what happens is that if the theta I in the optimization turns out to be 1, the measurement is considered an inlier, and the second term disappears, so 1 minus 1 becomes 0, and the problem becomes the same as standard least squares. If instead the theta I is equal to 0, it means that this term disappears, and the second right-hand side becomes equal to bar c square, which is a constant. Okay, so essentially that's the case in which the measurement is discarded as an outlier. So again, like the x is the quantity we want to estimate. The y can be either inlier or outlier. And you can think about this formulation in two ways. You can think about this formulation trying to simultaneously classify inliers versus outliers while estimating the x. Or if you have an optimization background, you can think that essentially while the nonlinear least square is minimizing a quadratic cost function, this truncated least square is optimizing a cost function which is quadratic, but then becomes flat beyond a certain error to essentially minimize the impact of outliers. So we are in computer vision and robotics, we are really used to say, okay, we have outliers, let's just use Ransack maybe. And Ransack indeed is solving an optimization problem, which is consensus maximization, which in many aspects is related to the one I'm showing on the slide. My issue with Ransack is that even in the best case, theoretically, you can just plot for a given number of iterations that you perform the probability of failure for increasing number of outliers, for increasing percentage of outliers. And what you get here is that Ransack is actually great for low level of outliers, but when you start getting towards 80% outliers, the probability of failure increases very sharply towards 1. And if you're working as in point cloud, object detection in point cloud, we're working at 90%, 99% outlier rates, Ransack will fail all the time. So not a great approach. This gets even worse in application in which you have to use 5-point Ransack, 8-point Ransack. So, the failure just starts showing up before. And this is really the reason why we pushed for a different approach. So we pushed for a different perspective, which we call certifiable algorithms. Certifiable algorithm is an algorithm to solve essentially the optimization problem, the robust estimation problem that I was showing you in the previous slide. So the way you have to think about it is that the certifiable algorithm is trying to estimate an unknown quantity, let's say the pose of the object, given some measurement of that quantity, potentially corrupted by outliers, and is doing that by solving this optimization problem, which is indeed very tough to solve. You can show that this is NP-hard, intractable, and so on. And as a result of this optimization, the algorithm is giving an estimate which we call X star. So this is any algorithm for estimation will have this kind of approach. What we mean by certifiable algorithms is that we want to design a fast, meaning a polynomial time algorithm that is able to solve outlier rejection, which is this problem here, this optimization problem, to optimality in virtually all problem instances, or detect failure in worst case pathological problems. Okay. So the second clause about worst case pathological problems must be there. This is an NP-hard problem. For sure, there will be instances in which no polynomial time algorithm will be able to solve it. So sometimes we also refer to this idea of certifiable algorithms as certifiably robust to stress the fact that we really care about robustness towards outliers. So let me just give an example to show what we are trying to do here. Essentially, what we want to do is to move from Ransack, which has a probability of failure that goes to 1 for high-level outliers, to something that is a certifiable algorithm in which the probability of failure stays flat. So we're always able to solve this problem, except in some worst-case instances. But these worst-case instances, we don't want the algorithm to fail silently. We just want the algorithm to tell us, I'm not sure about this solution, this estimate, don't trust it. So in the COVID-19 era, I would say that what we are trying to do really is to flatten the curve. And the good news here is that we realize that for the algorithms we design, the worst case instances that I'm mentioning here in the slides are really hard to find. So the algorithm that I'm going to suggest in the next slide or so are able to solve pretty much any problem you fit to it, even with extreme amounts of outliers, which to me is pretty amazing. So how to design a certifiable algorithm? That's a bit technical, and actually there is much more than what I have on this slide. So I want to summarize this slide with few words rather than getting into the math. But the basic idea is to start with some robust estimation problem. For example, in the case of 3D object detection, this is called a robust registration problem. We massage it into a form which is more familiar, in this case, into a quadratically constrained quadratic program. And while this is still hard to solve, we transform this into a convex relaxation, which instead is very easy to solve in polynomial time. But what we are really doing is to design fancy convex relaxation, which are such that solving the convex relaxation is the same as solving the original intractable problem. So we design convex relaxation, which are tight in the sense that in almost all the cases that you face in practice, the convex relaxation will give a valid solution, will give the optimal solution to the original problem. I want to go, there is much more to say, and I want to mention that this algorithm is called teaser++. There is a lot more to say with respect to what I'm telling you on the technical side, but rather than going on the technical side, I want to show the results, which to me are pretty astonishing. So on the experimental results, here I'm showing a bunch of qualitative results for object detection in large point clouds. So we're trying to detect the serial box in large point clouds. And you can see that visually teaser++ is able to detect the serial box in the right way, and is doing so with an extreme amount of outliers. 90% of the correspondences are outlier, 96 correspondences are outliers, and we can just try to compare visually on standard benchmark teaser++ against Ransack, and we definitely outperform it by a large margin. To be more quantitative here, I'm showing what happens to the translation error. So how well we localize the robot. So the lower the better versus increasing outlier rates. And I'm showing here outlier rates which go up to 99% outliers. And here I'm showing that teaser and teaser++, which are two variations of the proposed approach, have the lowest error. And they outperform standard approaches like fast global registration, and they outperform also variants of Ransack. So here I want to point out that this one in magenta is Ransack 1 minute, which is what happens if you let Ransack run for an entire minute, which is something that you will not do in practice, like millions of iterations of Ransack. So we have extreme robustness, and this translates also on much better performance on real data sets. So for example, here we consider the 3D match dataset, and we use deep learned correspondences using 3D SmoothNet. And what we are showing in the table is the percentage of scenarios in which each technique is able to compute a good estimate for the poses. And you can see that essentially, if you compare Ransack with teaser++, we can get that teaser++ is able to solve 10% more problems, at least than really even slow version of Ransack. So the other good news, and I will try to wrap up after this, is that teaser++ is online. It's open source. There is a very fast implementation. So check it out. We're being pretty impressed by the performance. So this idea of certifiable perception does not only involve pose estimation in point clouds, but goes towards every geometric perception problems. Of course, I will not have time to talk about the work on object pose estimation in images, but the good news here is that this is a CVPR 2020 paper. So check it out. It's a nice paper from Hank, and we also get performance boost and dominate the state of the art in many fronts. So to wrap up, messages of this presentation are pretty simple. There is still a large gap between robot and human perception, and we need to go beyond SLAM and start to think about real-time 3D high-level understanding. And I proposed 3D dynamic scene graph as an expressive and general representation. The second point is that getting extreme performance for geometric perception requires going beyond algorithms like Ransack. And I propose certifiable algorithms as a practical approach to get robust performance. Of course, this is just the start. There are so many questions that we are left to answer, including how to get a tight coupling between metric and semantic in scene graphs, how to include learning as a part of scene graph, and many more. But since I'm out of time, I will stop here and thank the sponsors supporting this work, and thank you all for the attention.
Okay, thank you, Luca. Very exciting talk. So we have quite a few questions from the audience. Maybe we can take 2 or 3 of them since we're a little short on time. Let's see. So one question is, in Chimera VIO, what kinds of outliers will you reject, and what part is most important to improve accuracy and robustness?
So
this slide 10.
There are so let's see if I can get to this part. So outliers show up at very different levels in Chimera. So there is one which is about outliers when you track features. So we use a Lucas Canade tracker, and of course outliers will be failure of Lucas Canade, but will also be dynamic objects in the scene. And the other type of failures is in the loop closure. So if you have wrong place recognition, you will get a lot of loop closures. And we are dealing with these in 2 very different ways. So for the feature matching, the outliers are rejected by what I'm calling here structureless projection factor, which is something that you can find in GTSM. We implemented this in GTSM 4 or 5 years ago. It's been around for a while. This essentially is about doing a sure complement trick, which is very standard in computer vision to get rid of the point, But while doing the Schur complement trick, make sure that the landmark has a small reprojection error. If the landmark does not have a small reprojection error, you just discard it as an outlier. And this works extremely well. It's like, you can lose track a little bit, but then goes back to correct feature tracking. And of course, this kind of outlier is something that you can reduce just by having a faster camera. So the split between frames and keyframes is also something that helps a lot, having good feature tracking. On the place recognition side, we're doing a lot of work actually on robust postgraph optimization. I'm mentioning this idea of pairwise consistency maximization, but actually we also have a paper at ICRA 2020, which is based on graduated non-convexity, which is the best paper award at ICRA 2020, which allow to get very robust performance. So, you can get many bad loop closures, but if you have these robust optimizers, you can get outlier rejection, even in the presence of 90% outliers. So I suggest you guys to check that out. You cannot do without outlier rejection. So it shows up everywhere. Even with the perfect techniques for place recognition, you're going to have outliers.
So I think maybe the second question, I can kind of summarize a couple of the questions that we saw. So this is regarding your dynamic scene graphs and the different abstractions. And by the way, I really like the visualization. It's very nice. So I think there are a couple of questions. So one essentially somehow on the robustness, essentially on the kind of data flow, like what happens if the scene changes, or how do errors propagate from levels from the bottom to the top, or do you use information going top down? And then the other kind of type of question is essentially what would happen if you wanted to go outdoors or have a different, less structured environment?
Yeah, these are great questions. So robustness. So for the robustness bit, we are lucky because essentially we build on Chimera. So Chimera is first of all, it's amazing work from Tony, who is a student in my group, but it's pretty good system. At the same time, when you go to higher level of abstraction, the first failure mode that you encounter is that if the 2D semantic segmentation of the image is very wrong, there is not much semantic, the scene graph can do. Okay, so we already rely on pretty good 2D semantic segmentation. And indeed, I want to stress there is a huge amount of work to be done on this. This is first work to get to a robustness like the one we have for visual inertial navigation. We're talking about years of research here. So so robustness is definitely something that is working pretty well for the Unity-based photorealistic simulation we are using, but you expect there will be work to be done on moving these to very challenging real-world scenes. And this ties back also to the second question, which is about how the different levels of the scene graph are interacting with each other. So right now what we are doing is really annotating, we are creating edges by observing the relation. For example, we are observing a posteriori that a given set of triangles in the mesh are a chair, for example. Okay, so we observe this in the scene graph and we add an edge in the scene graph. But what we really should do is to have a tight coupling between the layers of the scene graph, such that if some layer understand that an object is a chair, we should be able to make information flow towards the bottom level to improve, for example, the geometric reconstruction. So definitely having these kind of processes which are going top down and bottom up in the scene graph to improve robustness and accuracy, I think is the right way to go. And I think is pretty well aligned with what Andy was suggesting in his talk. So how to do that and how to do that with a clever combination of learning and geometry is essentially the question there. And it's a very interesting question, actually. For the outdoor scenes, which is the last question, I don't think there is a substantial difference. The concept here is that a scene graph is a hierarchical representation. And of course, in indoor, the hierarchy will be rooms, buildings, and so on. In outdoor will be streets, buildings, cities, and so on. I don't think there is a fundamental difference. And in many cases, the outdoor setup, may have some advantage. For example, if you have a GPS, can be slightly simpler. They are both interesting, I would say. But at the modeling level, at the representation level, I don't see much of a difference.
Okay. Thanks again, Luca.
Thank you guys for inviting me, and thanks for tuning in.
Yeah, thank you. And then, yeah, it's going to be a very exciting workshop. And then I think next we'll have Simon. I think you're online, right?
Yes, yeah, I am. Yeah.
Okay, so I'm excited to have Simon up next. Simons is a principal scientist at Argo and an associate research professor at RAI at CMU. He's part of the computer vision group. Before that, he was at CISRO for 5 years, and he got his PhD from Queensland University of Technology in 2003. And so looking forward to your talk. And I guess you're on campus already.
Yes, I've decided to set up camp here in the cut. So yeah, yeah. So I've told everyone to freeze behind me. So it's very, very polite of everyone.
Okay.
Yeah, thanks so much, Basti, for the intro. I actually recorded my talk beforehand, but I can just give it live. It might just be easier to do it live.
We get another iteration of practice.
Okay, so just let me bring that up now, and we can start. Here we go. Share. Then.
So we're running about 9 minutes behind.
Yep, no problem. Can you see that, Basti?
Yes.
Great. Okay. All right. So thanks so much for the intro. And I'll try to kind of keep this short and sweet so people can go have their lunches or teas or coffees and things like that. So the topic of this workshop is fantastic. I think it's sort of touching upon all things of SLAM, deep learning, geometry, all these wonderful things that are sort of exciting in the world of robotics and computer vision and learning at the moment. So one thing I'm going to talk about today, we're doing a lot of work in this space in a number of different problems, my lab, but one thing in particular I want to talk to today is about doing geometric reasoning using learning algorithms where we only have 2D supervision. And I'm noticing there's a couple of people working on this now, but I'm going to define what I mean by 2D supervision, and we can kind of go from there. So essentially, say like one problem that I'm really interested in is problems associated with autonomous cars. So you have an autonomous car, it's driving down the street. And what's really important is it needs to have a good understanding of the other vehicles coming towards it. So it wants to know sort of the 3D position of those vehicles coming towards it and the 3D spatial extent of those vehicles. And so obviously there's a couple of different ways to solve this problem. Probably the most obvious way is through hardware. And we kind of see a lot of these autonomous cars driving around various cities here in North America and Europe and in Asia as well. And what we oftentimes see is this sort of little device on top of the car, a LiDAR, and it's shooting out lasers and using time of flight to determine depth. And it's really good. It's really, really useful. And people are doing a lot of work now on these LiDAR sensors. They have some drawbacks, but so one primary drawback is the density of the LiDAR returns as a function of distance. So the further out a vehicle is or an object is, the harder it is to see with a LiDAR because you just don't get that density of hits. Other issues are like black bodies. So the black bodies LiDAR really struggles with. Glass reflectance and also inclement weather can really affect this whole pipeline. So increasingly, we're kind of turning to deep learning to help us. And so we're like many problems in robotics and vision. And so one thing we've been turning to is actually, let's go back to just visible cameras. So on an autonomous car, you'll have like a ring camera around the car, and you can get very dense measurements. But obviously the drawback to this type of measurement is that it's lacking any sort of 3D measurement. So it's obviously a projection from 3D down to 2D, and you're only really capturing the reflectance of light, not the depth of the object. So one thing we like to do is we like to basically come and essentially run this through a deep network. So we'll go and take our image, we'll run it through a deep network, and what we'll spit back out is the 6th degree of freedom of the object with respect to its coordinate frame, and also will output the 3D spatial structure. And when I mean the 3D spatial structure here, I'm not talking about dents. So I'm actually talking about a core set of points, say a core set of points that are common to that object category, say car, table, chair. I'm keeping the CAD model there so you can kind of interpret what the points are. And we are indeed doing things in dense reconstruction too. But here we're just talking about sort of getting the coarse 3D structure as well as the 6th degree of freedom network. And obviously this should be something simple that deep learning would be really good at, provided that we give it enough labels. And therein is the rub, how to provide enough 3D labels to train such a system. And it turns out that this is really, really hard to do. It's tedious and difficult. So here's an example from the Beyond Pascal benchmark at Silvio Savaresi's group. And you can kind of have a visualization here of what they do. They go through and you get an image, you have to go through a dictionary of CAD models, choose what CAD model you think is in the image, and then you go through this laborious task of determining whether points are occluded, where they're located. And it's a very onerous and error-prone task. So it's a hard thing to do. And so kind of to express this more formally, what we're trying to do with 3D supervision is we not only label the image, so we label the image with these 2D landmarks, and that's what we're going to call here in 2D supervision. But what we're also trying to do is we're trying to associate these 2D landmarks with 3D shapes from a dictionary. And so for instance, like we select one here, and then through simple PNP, we can then recover the 6 degrees of freedom such that we now have our 3D labels. And this is basically how it's done. If you want to do it with real world images, obviously you can do this with synthetic rendering, but you then have this render gap between real images and synthetic images. And so that's oftentimes not a great idea. So doing this with real images is really important. So, and if we're doing this all correctly, then the theta, the 6 degrees of freedom that we're estimating, should then basically match the 2D projections. So we're kind of arguing that this is not a good idea. And this is not a good idea for a couple of reasons. One major reason is that for specific object categories, say car, but many other object categories, the type of variation we see in the image is perhaps not going to match the variation of shapes we have offline. So that's really hard to do and anticipate beforehand. The other thing too is, so obviously like many of you, I love driving around town using a stretch SUV. It's something that I enjoy to do, a very, very common thing. But this is sort of an extreme example of this instance, but it does come up, especially when you sort of branch out to many, many different object categories where you perhaps don't have really good 3D shapes to use. So the question sort of we've been exploring in my group is how far can you go with just 2D supervision? If you've just got the 2D labels in the imagery, how far can you go? And that's sort of the topic for today's talk. So what we've been exploring is, and so if we kind of do a good job on that, we could perhaps go and just basically get this type of labeling and then infer all that 3D structure. And this image is actually taken from the Apollo Car 3D data set. It's a paper and a data set that was released at CVPR 2019. So could we just use these types of 2D labels to automatically lift out the 3D structure from this type of 2D supervision? So let's set up the problem more formally. So what the problem kind of looks like is we have our landmarks, our 2D landmarks, and we have a bunch of images, perhaps millions of images. And we are going to assume that all the images come from the same object category. So it could be chair, could be car, could be table, any type of object category we like. And what we're trying to do is we want to basically lift out this 3D structure. And the only supervision we have is the 2D labels. But the extra constraint we have is that we have lots and lots of them. So lots and lots of them stemming from the same object category. So rather than just one image, we have many, many, many images stemming from that same object category. Now, some people in the vision and robotics community are referring to this as unsupervised 3D lifting. And so this is a term that from Jim Regg's group from their CVPR 2019 paper. Another term that we kind of like to use is something called structure from categories. That's something that we're trying to kind of get the community to perhaps use. Again, it's tomato, tomato, same principle. You're trying to kind of lift the 3D structure out from the 2D labels. And it's very much related to the problem of structure for motion. In particular, non-rigid structure for motion. So that may seem weird to many listeners. They're saying, well, how can a chair be non-rigid? Well, the instance of chair is obviously rigid. So I've got a rigid object like a chair or a vehicle, it's rigid. But the object category chair is non-rigid. So chairs can have many different shapes and forms. And so what's cool with that is that we can then bring to bear all the excellent work that's been done in non-rigid structure for motion to this problem. So let's kind of formalize the problem a bit more. So what we're wanting to recover is X, Y, and Z for the ith index in our 3D structure. And what we have is U and V, just the 2D projection. So probably annotated by a human. And we are relating this 3D unknown 3D coordinate to the known 2D coordinate through a camera projection. And basically it can be a perspective or an affine camera, and it's related by 6 degrees of freedom. And so obviously I can concatenate all my points together, P points, into a matrix, which is P by 2. And obviously the unknown 3D structure then is a P by 3 matrix. And I'm trying to then basically have the two things that are unknown are the 3D structure and the camera, and the thing that is known is the 2D correspondences. And obviously for each image, we have a number of unknowns. So 3P plus 6. So the 6 is there because of 6 degrees of freedom, but we only have 2P knowns. So this is obviously a heavily under-constrained problem. So what to do? So one simple thing to do here is basically to constrain the problem. And an obvious thing to constrain is that, all right, well, we know that our camera matrices have to be SE3. So that's something useful, but it's not that useful. It's definitely a useful constraint, but it's not terribly useful when it comes to this non-rigid structure for motion problem. Something that's perhaps more important is if we can actually constrain S, the unknown 3D structure. And so we want to constrain S to lie in a space omega that is somehow constraining this problem. And so the big question that we've been asking my group is, could we somehow learn omega? So we could do a good job of this for different types of object categories. But when we're learning omega, we only can learn from the 2D correspondences. We can't have some offline 3D data set to learn from. We only have the 2D correspondences. So it turns out that there's a couple of different ways to attack this. So one way to attack this is basically to get our 3D structure, so our P by 3 matrix, and simply vectorize that matrix so that we have a 3P by 1 vector. And a very, very simple idea is to assume that for that object category, this 3D shape lies in a low dimensional linear subspace. So we can kind of see here, and we can visualize this sort of simply, and we refer to this as our low rank shape prior. And we can visualize this instead of the D1, D2, and D3 are our dictionary vectors, and B1, B2, B3 are our unknown coefficients. And so we can kind of visualize this in sort of matrix form that makes things a bit simpler. And this idea was made popular originally through a quite famous paper by Chris Bregler back at CVPR 2000. And in follow-up work, probably quite a famous paper from Hongdong Li's group at CVPR 2012 kind of demonstrated how you could use convex relaxations to optimize this easily to determine the rank. So using trace norm and things. And I believe that paper won best paper at CVPR 2012. So some neat work in that space. So let's apply this idea to 3D lifting. And we've got an example here of applying it to the object category chair. And unfortunately, it does not do a great job. And one of the reasons it doesn't do a great job is for many objects that we're interested in nowadays, the amount of shape variation we have to deal with is substantial. And so the low rank assumption is poor in that regard because we can't handle large amounts of 3D shape variation for an object category. So, but what we're trying to kind of argue here is actually we have made a bit of a breakthrough recently in our lab, something that was presented at ICCV 2019, something that we call deep non-rigid structure for motion, which is able to do a really good job at this type of 3D lifting for a number of different object categories. And we're going to kind of walk through now how we do that. But if you kind of turn off after this, this is the main result. We can actually do a really good job now of just working with 2D labels and lifting out this 3D structure and camera position. So how do we do this? Well, the central idea comes from the realization that if we want to model more 3D shape variation, we need to add more columns to the matrix D. So this seems kind of obvious, but problematically, if we add more columns to D, it makes it overcomplete. And so we need to then add an extra constraint to the B vector to make it unique. And so a common constraint is essentially sparsity, okay? So we try to enforce sparsity to make things unique. And in fact, our lab sort of pioneered some work in this space, something that we call compressible structure for motion. And it actually works really nicely. It's theoretically very elegant, but there's an issue. One of the issues is if you encounter more and more shape variation, you need to make your D matrix have more and more columns. And as you add more and more columns, you get this really kind of problematic issue of essentially having to have the column vectors get closer and closer together. And because they're closer and closer together, that can form instability. Okay, so we can actually get, so if there's annotation noise or other types of confusion, it can get confused over which dictionary elements should be active and not active. And so that can make the reconstruction or the lifting process very, very noise sensitive, which is something that we don't want because you've got people there clicking on points and there will be noise. So what to do? So one thing that we've sort of been exploring is intuitively, we've sort of noticed that, well, if you want to have your system more robust, you want less columns. You kind of want your D matrix to be more square, right? So more square, the number of columns and rows to be about the same. If I want to be able to model more shape variation, I want to make D more rectangular. I actually want to kind of make it more rectangular, adding more elements in there. But that comes at the drawback of making it less robust. And in fact, I've got a little bit of an advertisement here. We are exploring this connection actually generally with respect to deep learning in an oral we have here at CVPR. So if you're interested in sort of this trade-off in a more general sense, I'd encourage you to kind of come check out that paper that's going to be happening this week. So we've got this trade-off. And so the question that we've been asking ourselves is, can we do better? We want to be able to be robust, but model a lot of shape variation. So what could we possibly do? And so one idea that's sort of interesting here is the idea of employing what we refer to as a hierarchical sparse shape prior. Okay, so what do we mean by that? Well, it's actually pretty simple. We basically want to make D artificially more square. So how do we do that? Well, one really simple way of doing that is to actually synthetically or artificially add zeros to S. So make S longer. Okay, and so by making S artificially longer, we make D more square. So we're not actually reducing the number of columns. We can still have a lot of columns, but we just add more zeros to the bottom to make it more square. And sort of basically what this does intuitively is you can actually think of this is actually allowing the dictionary to spread out in more dimensions. So that if in a lower dimension, two dictionary elements are close together, by adding extra dimensions, it gives you more opportunity to kind of spread them out to make the reconstruction more robust, but also allowing you to have extra capacity to model shape variation. Now, this seems like a bit of a parlor trick, but what's really cool is recently there was a couple of neat papers put out by Michael Elad's group, a very well-known guy in sort of sparse coding and signal systems, showing that there's actually a direct connection between the problem of sparse coding and a single layer of a neural network using ReLU, so a feed-forward network. And you can actually show that a feed-forward neural network using ReLU can approximate the sparse coding problem. And so what's more interesting is that if we include our hierarchical sparse prior, so kind of adding this element, it's equivalent, if we structure things properly, to adding layers to a deep network. And so this approximation can hold under certain circumstances. And so as I make my D more and more square, as I add more and more capacity, it actually can be computationally efficiently realized as a feed-forward neural network. And if you're interested in the details of this, again, the details of this will be sort of in our up and coming oral, but this is a core insight that we utilize for our 3D lifting process, because then we can kind of jump backwards and forwards between treating the 3D lifting process as a factorization problem and actually implementing it efficiently using modern deep learning frameworks. So what's neat there then is we can actually essentially set up the problem as this sort of 3D lifting autoencoder. So the 3D lifting autoencoder kind of runs through and it kind of projects through to these different layers, D1, D2, D3. And D1, D2, D3 are actually submatrices of the larger matrix D. And if we factor things properly, we can then actually separate out the 6 degrees of freedom through the autoencoder. So we, in an unsupervised way, just like we do in regular structure from motion, split out the 6 degrees of freedom from the 3D structure. So we can then basically recover the 3D structure. And again, if you're interested in the details in this, it's up on our paper, Deep Non-Rigid Structure from Motion, which was published in ICCV 2019. And, but what I'm going to advertise for you guys are the results. So what we did in this paper is we compared our approach to all the known approaches at the time of publication for non-rigid structure from motion. And so we did this on the IKEA data set, and we had different object categories, say bed, chair, sofa, table. And the main thing to pay attention to is basically the error rates here on the y-axis. And the error rates here are in logarithmic scale, okay? So, and so what's interesting is our approach not only outperformed all these other techniques, it outperformed them by an order of magnitude. So not just slightly, by a dramatic amount. And so what's really cool here is it really opens up the opportunity to apply structure from motion techniques to these 3D lifting problems where you couldn't do it before because of the inability of the techniques to handle large amounts of shape variation. What's also neat too, so this is an example of ours versus sort of the closest competitor. What's also really neat too here is that our approach can handle large amounts of annotation noise. So what we have here is our approach on the yellow line here in terms of error. And then the black line here is the lowest error made by baselines that we compared against without noise. And we're substantially better, even in the presence of large amounts of noise, which is important because you will have human annotators clicking on points and they will make mistakes. They will not be reliable. Finally, in any type of 3D lifting process, there will be self-occluded points. So chairs, vehicles, there'll be lots of points that you will not be able to see. So our approach is also, because it's based on factorization, easily able to handle large amounts of missing points. And again, when we compare our approach to the next kind of best method at the time when this was released, we were able to kind of outperform them dramatically, even when those methods had no missing points. So the x-axis here is determining the number of points that we're missing. And then finally, we have some examples here of reconstructions. Hang on, we can split that out of this part, sorry. So here we have some real world image reconstructions. So we have sort of the reconstruction of the object category plane, just from 2D annotated points. We have reconstructions of the object category bike. Again, the red points are what you should pay attention to. The white here is used to kind of make sure that the red points have some sort of semantic meaning. And then also what we've done is actually we've extended this framework now, and this is an archive paper that we recently released that is now able to handle perspective geometry. So we can do a really good job now on, say, things like the Apollo car 3D data set, where human annotators are going through and just clicking on points, and a lot of points are occluded. And we can do a really good job now on just being able to kind of reconstruct these things really, really accurately. And our older method wasn't able to handle the perspective geometry as well. So our new method is able to do a really good job on this. We also have some really neat results for other types of data. So on the human 3.6 million data set here, we've got reconstructions, and we're using no time information here. Okay, so we're just using it for the object category body. And obviously there's a lot of techniques out there now for 3D lifting, but ours is completely generic, uses no time, and we're actually able to get very good results. And what's also kind of cool is we're able to compare our method against a number of really recent techniques. So there's another 3D lifting technique that's become quite popular now, and it was released just late last year. It's called C3 DPO, and it's from Adrian group at Oxford. And that approach actually works pretty well, but our latest work is that are actually able to kind of overcome some of the poor reconstructions that they're seeing in their approach. So we're really excited about what this approach can do. We've also got other results on more general object categories. So Pascal 3D, here's an example. We've got occluded points. We're actually able to do a really good job on this for chairs. And also for buses. And obviously there's some limitations. So one of the limitations is that because we're not using any temporal information, it's all kind of just, because there's no structure oftentimes to these data sets in time, we are oftentimes not able to handle inherent ambiguities, so like whether our hands forward or backward. That's something that there would be an ambiguity over. And we've actually got some work where we're using appearance to kind of condition on that to try to kind of overcome this issue. And another thing is there is sometimes confusion between deformation and perspective effects when the data set is limited. So essentially in summary, what I've been able to kind of show here is we presented a new approach for 3D lifting that uses only 2D supervision. So hopefully you guys have got a better sense of what we mean by 2D supervision. We're actively pursuing strategies where this theoretical connection between sparse coding and deep learning can be leveraged. And so another advertisement is we've got a paper here at CVPR where we're actually able to show when you can use sparse coding to solve inversion problems that CNNs can't do a good job on. So I'd encourage you guys to maybe check that out if you're attending the conference. And we're also able to show how 3D lifting can help train appearance detectors to handle geometric ambiguity. So it was something that we presented at ICCV 2019. And we are actively, like a lot of other groups around the world, working on how to leverage some of these results for dense 3D lifting using only 2D supervision. So instead of perhaps landmarks, if you have 2D silhouettes plus landmarks, can we lift out the dense 3D geometry without any other 3D supervision? So that's about it from me for now. So hopefully we have a little bit of time for questions. And again, thank you so much for the invitation.
Yeah. Thank you, Simon. That was a very exciting talk. And I think it's very interesting to see this 3D, 2D connection. And then, so I think, so one question we have from the audience is if you have compared the learned omega with the pinhole projection from model.
So the omega we're referring to there is basically the constraint on the 3D structure. So once we have the 3D structure, we then project it. We can project it through with a pinhole camera or a perspective camera. So it's really about basically the constraint on the 3D structure. So, and a classic constraint, like I was saying earlier, is say the 3D structure has low rank. That's like a classic one. And some of the more recent work now is sort of, instead of low rank, let's model this as an autoencoder or model it using sparse coding. But the trick here is that you don't have the 3D data to learn the omega. You can only have the 2D projections. So you got to factor in the camera when you're doing that omega learning. And that's really what makes this hard. Otherwise, if you had the 3D data, you could just sort of go through and have at it with your favorite sort of manifold learning technique.
Okay, let's see. Do we have any other question? Let's see. So I think one question that I was thinking about is, so when you do this variation on the 3D structure, I think you showed that before to try to generalize it. So this is a certain model. So you're trying to actually fit a more robust and general model by doing that, right? Like I think you showed that.
Yes. So are you referring to kind of making? Are you referring to kind of like making the matrix more square? Is that what you're referring to?
Yeah.
Yeah. So and this is something that we've been thinking a lot about. So yeah. So essentially, in all these systems, a really simple way to think about it is you can model more shape variation if you add more column vectors to your D. And so D is that dictionary. And so you can model more shape variation. But the drawback is, and the classic example is, say, a nearest neighbor classifier, for instance. If you have nearest neighbor, if things start getting really, really close together, you can easily confuse between which one you're going to be using because they're too close together. And so what's neat here is it gives you, and so for a long time, 3D lifting literature has been held back by this. So they've always said, well, we need it to be robust. So we're going to be low rank. So low rank intrinsically means that you can't model a lot of shape variation. So the neat insight here is that if you sort of artificially sort of append zeros to your shape, and again, because of the lack of time, we couldn't get into sort of the mathematical motivations here. But what it allows you to do is to make your D more square. And because it's more square, you can still kind of model all this shape variation, but you are separated out a lot better in this high dimensional space. And so, and what's really elegant too, is that for sparse coding, this can be cumbersome to solve, but because of this theoretical connection, we can approximate this well using just a deep network. And so actually, when we actually solve this, it can be done really efficiently, say in PyTorch or TensorFlow, and it literally is just sort of an unsupervised autoencoder. And but we have some special components in there for separating out the camera components from the other components. And but what I think is interesting here with the square matrix is it gives a motivation for why does it work so well? Why is it so robust to noise and yet able to handle all the shape variation? And so that's one thing sort of our group has been sort of latching onto, sort of like, well, why does this work so well? And so we think this is a good theoretical explanation for why.
Okay, so I think we have a maybe slightly more general question. It's like, how do you overcome snow and rainy situations for autonomous driving?
So that's a good question. And again, that's sort of like why we've been investing a bit of time in this research direction, because as probably the person asking the question is sort of alluding to, is that when you rely on sensors like LiDAR, they almost basically shut down in the presence of sort of snow and rain. And so again, cameras can do, visible cameras can do a lot better in those circumstances. Obviously, they do suffer from deterioration as well, but that's why we think these 3D lifting techniques are sort of so important, because you can actually kind of at least label up a lot of data, 2D image data in these conditions, make detectors sort of do a good job in reconstructing the 3D position just from the 2D input. There are obviously issues. No sensor is impervious to problems. Obviously, kind of visible cameras have issue in low light at night. So I do believe fundamentally any solution in the sort of practical sense there will have to be a multimodal solution. But that's why we're sort of trying to push so heavily in this type of direction, because we need to be utilizing other sensors other than LiDAR.
Okay, thank you, Simon.
No problem.
And so, yeah, I think it's been a quite exciting talk and also exciting workshop so far. And so I think the plan right now is that we'll take a break right now till 1 p.m. Pacific time, 4 p.m. Eastern time, and 10 p.m. Central European Standard Time, or 4 a.m. Beijing time. And so, if you're from the part of the world where the times essentially 12 hours opposite, for like Australia or China, Japan, this is pretty tough. But so thanks everybody for kind of staying up or dialing in for wherever you are. So we'll be back at that time with an invited talk by Tomasz, and then some contributed papers, and then a couple more invited talks. And so thanks everybody for being on Zoom and for being on YouTube, and we'll talk to you soon. Thank you.
Thank you. See you later.
I do have one recorded in case something messes up in the middle, then I'll push the pre-recorded one for the website. So the rest of the world will see the better one. But I think everything will go well.
Yeah, it should be all right. Yeah, so far it was all right. So I think, but I can see audience is quickly growing.
So just a quick notice, Tomasz, if you want to go a little bit longer, and it's okay, because the first speaker will just play the video, and so there is no need for question for him. And so there are about 5 minutes left in this case.
Sounds good. I gave this version earlier. It's going to be about 32 minutes. So I think that's going to be pretty good.
Okay. So then that leaves Kristen. And if Kristen, if you have more questions, feel free to ask more questions from the audience.
Perfect. Do we have, again, people looking through and putting on Google Doc?
Yes.
I think so.
Yeah, we have Yao here working on
Excellent. That was very helpful.
Questions. Okay. So I also start to record the presentation in the Zoom. Does everybody okay with that?
Sounds good.
Okay.
Okay, so are we ready to start?
Yes, please.
Excellent. Okay, so I hope Google, YouTube audience can hear me. And I have a pleasure to introduce our next invited speaker. It's Tomasz Malisiewicz, and I'm quite sure I pronounced that right. And Tomasz did his PhD at CMU and has now close to 15 years experience in computer vision, I guess, in robotics. So he also worked at MIT, set up his company, Vision AI, and now works for Magic Leap as a principal engineer. He's very well known for his recent work on SLAM and combinations with deep learning, as well as 3D reconstruction. So really excited and looking forward to your talk, Tomasz. So over to you then.
All right, Christian, thanks for the warm introduction. So I'll say again, my name is Tomasz Malisiewicz, and the title of my talk today will be Deep Visual SLAM Front Ends, Superpoint, Superglue, and Supermaps. Now, for those of you turning in on YouTube, this talk is being delivered at the joined workshop on long-term visual localization, visual odometry, and geometric and learning-based SLAM at CVPR 2020. Let's first take a look at some of the problems that can benefit from advances in visual SLAM. In the first row, we see mixed reality applications. Those are consumer devices that you wear on your head, and they have to localize themselves in space, and they enable a next generation of experiences by blending digital items together with physical real-world items. In the second two rows, we see robotic applications, such as self-driving vehicles and autonomous carts. In all of these problems, cameras are heavily used to make sense of the world around you. And that's the crux of the visual SLAM problem. In today's talk, I'll be talking about three different things. First, I'll talk about superpoint, and that is my team's attempt to bring convolutional neural networks into the world of deep learning. Next, I'll talk about superglue. That's very recent work that we will be disseminating at this year's CVPR. That's about using graph neural networks and attention to further improve the correspondence or the feature matching problem. And then finally, I'll talk about supermaps. Those are just some ideas on how we can move beyond pairwise matching and finally fulfill this dream of end-to-end deep visual SLAM. Let's begin with the first part about superpoint. Visual SLAM can be decomposed into two parts. First, there's the front end, whose job is to extract features and associate them. And then the second part is the back end, whose job is to take 2D quantities and upgrade them to 3D. Now, the front end deals with image inputs, and it makes sense to use convolutional neural networks here because we've seen lots of successes when we had to apply convnets directly to images for classification and object detection. And in this case, the back end will be an optimization procedure. And the optimization is typically done over poses and map quantities. This is done by solving nonlinear least squares problems. It's typically known as the bundle adjustment procedure. So let's take a look at how we tackled first the front end problem of visual SLAM. We introduced a network called superpoint. A superpoint is just a code name for this simple network. It's a convnet that has two different kinds of outputs, the key point 2D locations and the key point descriptors. It's a powerful, fully convolutional design. Everything is standard vanilla deep learning components. The points and descriptors are computed jointly. It's important to note here that unlike earlier systems, you don't have to first extract interest points, then crop little patches around them, and then send them to a machine learning system. Everything here is done directly by the convolutions inside the network. We used a VGG-like backbone for our experiments in order to make it not too big, but there's no reason why you can't take today's most recent backbones and even modernize this approach. We designed superpoint for real-time processing with the GPU. That means we did not on purpose make our backbone very large. We wanted to make sure that this can go into real-world products. We designed the system so that the key point description and the location estimation share most of the weights. 90% or more of the computation is shared by the standard backbone. And we used sparse outputs so that this system can be used inside something that is fit into embedded computers. So yeah, here the front end will be the superpoint, and the back end that we'll use later will be some other geometric module. Very quickly, I want to point out that the reason why this works is because the key point or the interest point decoder performs a classification problem. We realized that the goal of this network will be to just classify which pixel is interesting and which one isn't. We made the assumption that within an 8x8 pixel neighborhood, there can only be one interest point. So for the 8x8 patch, that corresponds to 64 possible locations and a dustbin. Those are 65 values. So the goal is to create a distribution over those 65 values. The benefit about using distributions here is that we can then reshape everything and we get nice heat maps. So let's now look at the question of how do you train such a superpoint network? Remember, now the goal is to go from images to key point locations and descriptors. The training is relatively straightforward. We designed our system to work on a large collection of image pairs, where here are image pairs where one image sampled from a data set and then warped by a homography. By warping images with a homography, we know exactly where the pixels go. So the correspondence is then known. So training the descriptors is relatively easy via modern metric learning techniques. We use the contrastive loss in this case. The remaining question is, where do the key points come from? If we know where the key points are in one image, with the homography warp, we know where they go in the second image. But where do we get these points initially? If we take images as the ones I'm showing on the slide and you send them on Mechanical Turk, to other countries and ask people to label interest points, you will get answers all over the place. The reason is because the idea of an interest point is not something that exists in reality. It's a convenient creation that we engineers and scientists created to cope with the image matching problem. But this is too hard to have humans label. It's nearly impossible. So we devised a self-supervised training procedure that would allow us to bypass this problem. So the goal is to first train something on a simpler world, one where we can define what things are interesting and which things aren't. We use a world of synthetic shapes where we use a non-photorealistic renderer with lots of noise, and then the corners in this world are interesting points. After we've trained on our synthetic shapes, the goal is to transfer this information to a real data set of images. Here we use the MS-COCO dataset, and the MS-COCO dataset has no interest point labels. So we invented a procedure called homographic adaptation. Homographic adaptation lets us first train on one data set and then transfer results to the second data set. Here are just some examples of some more of the synthetic images that we sort of train on. Notice there's nothing fancy here. This is not an OpenGL renderer. This is something very simple where you have 2D rendering programs that can be used to show the shapes. Our earlier part of SuperPoint was just the interest point detection bit, and we called that magic point. Our earlier experiments comparing magic point to other well-known techniques like fast, Harris, and Xi interest point detectors showed a big performance gap, particularly when the images are affected by lots of noise or they're darkened. Let's now take a look at the homographic adaptation procedure and see how it works. The goal is to simulate planar camera motion using homographies. This is a self-labeling technique that can be used to suppress spurious detections and enhance repeatable points. You might think that you can just run at the detector, the magic point, save the output, and use that for training, and that's generally not good enough. So let's see how homographic adaptation works with this following illustration. We start with an unlabeled input image. We then synthetically warp the image, create different homographies, and then we run the interest point detector on each version of the image. This gives us multiple different sets of detections. We then warp them back and aggregate them to create a superset of detections. The reason why we called our final system SuperPoint is that this homographic adaptation procedure allowed us to generate a superset of magic points. So superpoints for us are a superset of what we could get with an earlier technique. Let's take a look at some examples of what it looks like to run SuperPoint on a pair of images. In this example, SuperPoint is in the top left and the green lines show correct correspondences. In the top right, we see Lift. That's another deep learning based system, slightly predating SuperPoint. In the bottom left, we see SIFT, which is one of the most well-known local feature matching methods. And in the bottom right, we see Orb. Notice that SuperPoint has the largest density of green matches in this example. Also note that in this particular pair, the orb tends to not have many detections, and it seems to have many that are clustering around the small number of high feature reach regions. This is not good if your goal is to later estimate a relative pose between the images. You would like to have points that are detected around the entire image. Here's another example that also shows a nice density of points being able to be aligned by SuperPoint. And also it shows the deficiency in orb by focusing too much on texture-rich regions. In this last example, we see a different relative rotation between the images, and we see Lift, the other deep learning-based system, struggling. In this case, SuperPoint works. But I want to let everybody know that based on the aggressiveness of the transforms, you get to train for this effect. If you use all possible rotations in your training, you lose a little bit of the power. The VGG backbone is not able to be fully rotation invariant. So we tend to train with about 15 to 30 degrees rotations maximum. But Lift here we see is not able to get enough matches. So far, everything has been 2D based. And you might wonder, will this 2D based training recipe work in the 3D world? What we did is we ran a simple connect the dots algorithm using nearest neighbor matching, and we applied Superpoint to a large number of videos. We were pleasantly surprised to find Superpoint working on lots and lots of different data sets. This was a nice benefit. These videos are showing the tracking mode of Superpoint, where all of the correspondences are done in a frame-to-frame fashion and then stitched together very simply. We released our pre-trained Superpoint network based on PyTorch with only 2 files, very easy to run. This came out in the first Deep Learning for Visual SLAM workshop at CVPR 2018. We recommend people go to our GitHub page if they want to check out just the Superpoint component. So now before I go and talk about kind of superglue and the more ambitious sort of project, let's very quickly study that robustness property of Superpoint. We asked ourselves, can we apply Superpoint to another task? Maybe one where we could highlight the robustness of Superpoint. We decided to take a fiducial pattern, that is the Chiruko pattern. Chiruko pattern is an Ruko patterns embedded inside a chessboard. You can see this pattern in the left part of the slide. We took the exact Superpoint architecture. The only modification is we replaced the descriptor, the real value descriptor, with now an ID classifier. In this case, our pattern has 16 different kinds of points that need to be detected. So this network has a 16-way classifier that chooses which of those points is being detected. We observed that this kind of training with data augmentation and this kind of architecture, when applied to this Chiruko pattern, allow the system to effectively see in the dark. Going from left to right, we see the image is being darkened. The top row shows the raw image. The middle row shows the output of a classical OpenCV system for this Chiruko pattern. This classical system is relying on lots of image processing operations, and those operations break down as the images get darker. With the deep Chiruko system, you can see the detection of the interest points even when the images are so dark a human can't decipher what's going on. So here are some videos showing this deep Chiruko system juxtaposed to the traditional OpenCV system. Every time the frame turns red, that means the system was not able to detect enough key points or there was some issue with the estimation. Notice that the deep Chiruko system is able to continue detecting the pattern even when there are strong cast shadows, when the lighting is sort of very low. And this is really an amazing property of using deep networks for local feature detection. Next, we wanted to see if Superpoint can be improved if we train it with real sequences, real data, and use some kind of backend in the training loop. So this is going to be Superpoint VO that I'll talk about in the next minute or two. If you take Superpoint and you run a simple visual odometry backend, it's not that difficult to upgrade everything to 3D. Here's a very simple point cloud recovered from the Freiburg TUM RGBD dataset. Here's another simple example that shows what happens when you take the Superpoint system and then you put it together with a VO into a reconstruction. We realized that the benefits of a VO-based Superpoint training is that we can establish correspondences across time. We saw earlier that the Superpoint tracker worked quite well, and this is what this training regime exploits. Also, using VO-based training allows us to determine which points are stable and which ones are not stable. So let's take a look at the VO-based training procedure for Superpoint. We start with an input monocular sequence. We have the intrinsics for this sequence, but we do not have depths or poses. We run Superpoint on this sequence on every frame. We do the correspondences. We get our point tracks. And then we perform in an offline fashion and upgrade to 3D. I guess in this case, you could just call this SFM. The difference between VO, SLAM, and SFM is less important as this is done offline. But after you upgrade everything to 3D, you get your labeled point tracks, and then this is the data you can use for training. So how can we define stability? When you get a point track and then you upgrade it to 3D, you can look at the reprojection error. If the point has a low reprojection error that is less than 1 pixel, we call it stable. If the reprojection error is larger than 5 pixels or some other large threshold, we say it's not stable. Otherwise, we ignore that stability classification during training. Here's an output of the labels on some video sequences. These are held out video sequences, and the colors depict the different stability labels. Green are stable points, red are unstable points, and black is this larger class of not entirely sure. Once you have these stability labels, training superpoint VO proceeds like the original system. We generate extra random homographies to create more difficult correspondences. And you have an architecture now that looks just like superpoint, but it was trained using sequences. Let's see how this performs compared to superpoint and other systems. We evaluated the superpoint VO system on a pose estimation task on ScanNet. The left plot will show the rotation error and the right the translation error. The higher you up on the plot, the better you're doing. The dotted blue line is our superpoint VO system. And the next two closest lines are superpoint, the original one trained on Coco, and we also ran an experiment. We trained our superpoint system just on ScanNet images without sequences. But when there is only 30 frame difference in our videos, this corresponds to 1 second of motion. There's only a small benefit in using VO. Very hard to tell apart which system is truly better. Was it really worth using VO just to get that small benefit? We repeated the experiment with a larger frame difference. Now, frame difference of 60 corresponds to approximately 2 seconds of motion. We start seeing now VO starts helping. And in the final experiment, we looked at the largest difference, that is frame difference of 90 frames corresponding to 3 seconds of motion. Now the gap between the VO-based training and the other methods is significantly larger. By doing these experiments, we realized that wide baseline matching is really what we should be after. If you're going to be tracking images that are just collected 1/30 of a second apart, you don't need lots of complexity there. Things tend to work quite well. When you have larger and larger differences between the images and the two images have smaller visual overlap, you need wider baseline matching. So now onto the second part, I'm going to talk about superglue. And superglue is our recent work on applying learning to the problem of finding correspondences. Superglue, learning feature matching with graph neural networks, is presented at this year's CVPR 2020. This is work that was done by Paul Edward Sarlin, Daniel Detone, myself, and Andrew Rabinowitz at Magic Leap. Paul is a PhD student at ETH Zurich, and he received his master's thesis for doing this work with my team at Magic Leap. Superglue is a graph neural network and an optimal transport procedure. Superglue is a system that uses superpoint and this extra mechanism to perform wide baseline matching. It works on image pairs, it works in real time using a GPU, and it gives us state-of-the-art results on both indoor and outdoor matching. Superglue can be trained to work with SIFT or with superpoint or just about any other system. A key thing to note here is that our goal was to design a matching system that would be better than motion-guided matching without any motion model. In our earlier work on integrating superpoint with SLAM fundamentals, we saw that motion-guided search does help a lot. However, when the motion estimate is bad, it can be catastrophic. We wanted to design a system that had no requirement to have a motion prior and was just trained on all of the hard stuff we could see in the world, and it just works without manually engineering little tricks. Superglue has two parts. The first is a graph neural network with attention. And the second part is the classical optimization procedure that we solve with the Sinkhorn algorithm. Superglue requires both sets of local features to go into the attention mechanism. This is very different than how we had previously thought about matching, where earlier we were designing networks to do all the processing for each image independently, and then only at the end do some kind of simplest nearest neighbor matching. Here, the super point outputs get fused with their locations in the key point encoder. They go into one network that's solving the two image matching problem. It goes through many layers of attention, and the final descriptors are fused together into a partial assignment matrix using the Sinkhorn algorithm. These details will be discussed later at the CVPR. Let's take a look at some videos of superpoint and superglue in action. These are some results on held out sequences from the ScanNet dataset. Notice in the top right, we have many, many more green lines showing correct matches than red ones. This is a very difficult sequence where the interest points on the floor have very similar descriptors, and superpoint has problems disambiguating which tile is matching to which other tile. We also repeated experiments with superpoint and superglue on outdoor data, and we compared it against the best that we could find in terms of inlier classification, and also works extremely well. From the evaluation slide, the most important thing to take home is that superpoint and superglue is the best recipe that we could find sort of today. If you look at this evaluation, you can also see in dark blue SIFT and superglue. This is a different superglue trained with SIFT, but it does seem to benefit the original SIFT. So if you're interested in training your own superglue for your own input features, feel free to get in touch with the first author. Superglue is also released as a demo. You can go to the website, the project website, or directly to the GitHub page, and you can check out this repository. You can run this on a GPU laptop or a GPU desktop at about 15 frames per second for approximately 512 key points on a VGA-sized image. It's a pretty amazing demo. Now, rather than me showing you more empirical results, I want to give you a slight little snapshot of what it's going to look like if you get this code up and running. I ran some simple experiments last night just in my spare bedroom by moving checkerboards around, occluding patterns, messing around with the camera focus. And in all cases, the demo continues to impress me. If you're a researcher yourself, I recommend you take a look at the paper, you look at our experiments, but all these things will take you 10, 20 minutes, hours to decipher everything. If you just get the demo up and running, get your webcam plugged in, point it at the world, try to break it, I think you will be impressed, because I was. So before I wrap up, I want to outline a little bit, what comes next. Now that we saw the front end, that features being replaced with superpoint, we saw superglue, another important mechanism for even getting better matches. What's next? So rather than describing how what next works, I want to describe at the high level desiderata. What do we really need to do to superpoint and superglue in order for it to become something like supermaps? So superglue works with a pair of images, and I believe it'll be important for us to think about alignments between sets of images. That is, when you have a map of the world collected as a sequence of keyframes, how can you then align a new incoming image to this set of images? Or how can you align two different maps that were built? That is, aligning a set of images to another set of images. Also, our superglue system only solves the correspondence part. It then uses a classical pose estimation system. What really is necessary is an estimation module to exist inside the network. In addition, the superpoint and the superglue system has made matching even more expensive than what you might have been accustomed to. And it has no loop closure mechanism. You will not be able to run superglue on all pairs of collected images, as it's relatively expensive. There needs to be a way to determine very quickly if these two images should be processed by something more complicated or not. That is, I believe keyframe embeddings are necessary to be there to close loops. And keyframe embeddings can be extended with superpoint, just another head that creates a single global image level descriptor. In addition, superpoint and superglue, those modules, they were separate techniques, and we trained them independently. And I believe in the future, we're going to see more joint end-to-end training. However, I don't think this joint end-to-end training is as important as other people believe. I believe that kind of getting real world products and getting this out in the world is more important than just having a single train button where everything works magically. And finally, superpoint and superglue is the fusion of a convolutional neural network and a graph neural network. The convolutional neural network has its own notion of a receptive field. And then the graph neural network part has a very different notion of the receptive field. I believe more work needs to be done to investigate these two receptive fields working in tandem, as in how do we have to improve the graph part or the low-level part? So I think that in order to make these techniques sort of work better, we need to have a conversation about which neural architectures give us different receptive fields and splice together how should they work in unison. So let me finish up by saying some open problems at the intersection of deep learning and SLAM that I believe will continue to drive innovation. If you are a student in this field looking for high-level goals to attain in your research, please listen. First, multi-user SLAM. I believe that creating representations or maps that work across a large number of agents is very important. I think this idea of a single SLAM system is used to build a map, and then it's thrown away, and then a new map is built, has to go away. We need to start thinking about scenarios where person A goes into a room, they build a map, they're effectively done mapping it, and then a second person comes in from a very different door into that room. And they immediately see the space and are able to align what they see with that prior map. In addition, I believe integrating object recognition capabilities into SLAM frontends will be important. I think a real-world product using SLAM will have to do several other things than just the localization and mapping. Getting objects recognized, getting semantics in there is going to be an important future direction. And finally, enabling lifelong learning, letting the system automatically improve over time. My entire adventure in Deep Visual SLAM started with this idea. I really want SLAM systems to go out into the world, perform a task, enable robots to be successful, and then let that data come back in so the machines improve over time. Humans, when they go out into the world, they're able to get better at repeatedly doing similar tasks or even navigating the same environment. I believe we need this property in our system. So to summarize my presentation today, I talked about superpoint. These are pretty old ideas now on using convolutional neural networks for replacing the front-end part of SLAM. We saw self-supervised learning, training, paradigms using homographies and using visual odometry backends. I also showcased the robustness of superpoint and its sister method ChirukoNet and its ability to see in the dark. I discussed superglue, and I do believe it has that amazing success because of the graph neural networks and their newer notion of receptive field. It works extremely well on wide baseline image matching problems. And then finally, I discussed some ideas for how to go beyond pairwise matching on what needs to be done to get end-to-end SLAM working. Superglue will be discussed tomorrow at this workshop by Paul-Edouard Sarlin. In addition, on Friday, at the Image Matching Local Features and Beyond workshop, Paul will also be there to defend the winning entry of using superglue. For those of you that are interested in learning more about our superglue method, there are multiple opportunities this week to come and learn. There will be 2 short presentations tomorrow at this workshop. There will be the main CVPR oral presentation on Wednesday, as well on the last day at the Friday workshop at the image matching workshop. Finally, this is my last slide, and I want to thank everybody for your attention, for coming in here today, checking out our great talks today. And with that, I'm here to take any questions that you might have. Thank you very much.
Thank you, Tomasz, for this great talk. So we have some questions from the audience collected from YouTube. There is a number of questions related to the invariance of superpoint and superglue. When you sort of train it, or you achieve some robustness, but you do not explicitly address the rotation or more significant scale problems. Do you have any ideas how to do it? Whether also the spatial transformer could be used in this case?
Yeah, I think this is a really good question. And I want to point out here is that we train our method to be robust to these transformations. It's not really invariant as in a mathematical property. You can even play with the systems and break them on extreme rotation. So we strive for invariance, but all we really get is robustness. We've really found that heavy data augmentation makes things work better. I do think we need to have a discussion and think about the representations. If we're training everything with extreme data augmentation, maybe something's wrong with how we're training in general. The fact that if you have 10 images, it's better to heavily manipulate them than just train on those 10 suggests that long-term, this might be an issue. We can't just data augment everything. But I think as of today, that is still the key secret. I think you want to do the data augmentation that is more aggressive than what you're accustomed to. Generally, I found that adding extreme noise to the images, making them extremely difficult and dark during training is very important if you're then going to just be able to take the demo out any time of day and have it not break on you.
Okay, thank you. And similar, but related question on superglue, actually, how far you can go in terms of wide baseline? Because we know that something that is not too far from homography can be handled well, I think. But if we start to have close objects that with extreme camera position change significantly the location of points, everything so gets mixed a lot. So how do you deal with that?
I think you can go with superglue significantly farther than you could with superpoint. And that's why I really encourage everybody to just get the code up and running and just see it for yourself. But it's still not big enough. There are still examples of images I can create where a human would say, well, that's clearly you just rotated a little bit and you moved a little bit. There's still ample images that I could find that superglue does not work on. The reason is because it still uses superpoint. It inherited some of the mistakes of the earlier system. And in addition, during training, and we train on ScanNet and we train on sequences where there isn't as much variation as we would like. I really wish there was a data set that would have the same physical building remapped, once a week for a year. And then you could see the variations across the days. We don't quite have that. So while superglue continues to impress me, I can just as easily break it and bring tears to my eyes and say, SLAM is still years sort of away. It's a little bit of both. I have to say that playing with it is really just the best way to see what happens. But look, extreme scale, extreme rotation, I have not seen anything work in those cases yet.
Thank you. And one more question about the training process. So you do use a lot of homographies and synthetic data in this. Have you noticed actually any significant difference if you start using 3D data, like the points that have really low projection error that you can get from 3D?
So when dealing with the reconstruction part, or when you have the 3D data, suddenly things can go wrong in that procedure. The reason why the earlier training worked well is because we kind of trained on a surrogate problem. COCO and homographies is not quite what we want, but we could do it at scale, a much larger scale than previously we had from any labeled data set. So I think what really we want to do is in practice is use our best SLAM techniques to create an offline SLAM system that can then be used to reconstruct sequences. That is effectively treated as ground truth, and then everything repeats. That's also how ScanNet was created, how a lot of data sets are created. There is a a system used sort of in the loop. So maybe the way to kind of move forward is to just keep making better SLAM systems that can be used to supervise the next generation after it.
Okay, thank you. There are, I think, more questions on YouTube, and we probably should invite all the speakers also to check. Maybe they can directly answer there to all audience. So thank you again for a great talk. Let me clap for everyone. And then I hand over to our host, Wenchen, to present the contribution papers.
Thank you very much.
Thank you, Kristen. Thank you, Tomasz. I think Guoyi can go ahead with the contributed paper.
Okay, sure. Yeah. I want to double check whether the first paper, dynamic attention-based visual odometry, whether the order is here. And I have the recorded video, but I want to double check whether the orders are here. Okay. If no, I will play the video. Okay. Share screen. Wenchen, can you? I can see there is an error. I cannot share the screen while other participant is sharing.
Okay, I think now you can try again.
Okay. Okay. Can everybody see the slides right now?
Yes.
Okay. Okay, we'll play the video. Okay.
Guoyi, we can't hear the sound. Maybe when you share the screen, there's two checkbox at bottom of the window.
So where?
So
Where again?
can you stop the sharing?
Sure.
And make a sharing again. Then at the pop-up window, you can see two checkbox about sharing the audio or something.
Okay. Oh, okay. Okay. Share the computer sound and share. Okay.
Right.
Okay. Got you.
Great.
Thank you. Sure.
Hello everybody, my name is Guo Xingyu. I'm with ELSA Lab Hsinchu, Taiwan. I'll present the framework.
Does it work right now?
Maybe the desktop. Are you showing the right desktop? You can hear the sound now, but the
okay, interesting. Okay.
The slide is gone.
Stop sharing again. Sharing.
Dynamic attention-based visual odometry.
Does it work right now?
Yes, perfect.
Okay. Okay, good.
Hello everybody, my name is Guo Xingyu. I'm with ELSA Lab Hsinchu, Taiwan. I'll present the framework Dynamic Attention-Based Visual Odometry to show the new concept for improving the accuracy of VO works. Let's get started with previous works. We summarized deep visual odometry methods into two categories, flow-based approaches and attention-based approaches. A significant portion of research works, including LSVO, Deep VO, CLVO, have introduced optical flow estimation into their VO models in recent years. Instead of feeding consecutive RGB frames into VO models, flow maps can be used as input for the VO models, as displacement of pixels between two frames can be better employed in the process of equimotion estimation. LSVO introduced the famous FlowNet in their VO module with an autoencoder in their network architecture to enhance the flow representation. DeepVO and CLVO are another FlowNet-based framework employing recurrent memory shells to learn sequential dependency motion of an image sequence. The other researchers attempt to introduce attention techniques to enhance the accuracy of their post-estimation DCNN. These techniques fall into two categories: heuristic-based and feature-based attention methods. In the first category, attention masks to the input frames are defined based on human knowledge. In mask SLAM, the semantic objects such as cars and sky are manually selected to filter out feature points extracted from input frames. On the other hand, in dynamic SLAM and movable object aware SLAM, predefined dynamic object regions are removed from input frames. For feature-based attention methods, attention models are incorporated for addressing the relative weightage of feature representation in the post-estimation DCNN. In SRNN channel, a Gauss attention model is separated applied to the feature representation of the translation and rotation estimation networks. The primary contributions of our works are, first, a learning-based DAVO framework that fits RGB input frames and flow maps both weighted by the generated attention maps to the post-estimation DCNN. Second, a concept of using flow maps for generating dynamic attention weighted for semantic segmentation channels. Third, an approach that enables derivation of attention weighted without human supervision. Here is our proposed DAVO framework architecture. DAVO is a learning-based framework based on DCNN without using depth map or recurrent memory shells. This framework includes the optimal flow estimation DCNN, which is called FlowNN, and the semantic segmentation DCNN, SegNN. In our DAVO framework, FlowNN and SegNN are implemented based on FlowNet2 and DeepNet3+, respectively. When two RGB frames I1, I2 input to the framework, the FlowNN takes them to generate the flow map F2, which means the optimal flow from I2 to I1, and the SegNN takes I2 to generate the semantic segmentation channels Sn to be the two inputs for attention NN. There are two primary components, attention module and post-NN in DAVO. Attention module includes attention NN, which takes flow maps to generate attention weighted AN. This module takes AN to multiply to the semantic segmentation SN channel-wisely to generate the weighted semantic segmentation to imply which semantic segmentation category needs to be attained. There is the animation to show the process. Attention module takes the flow map and employs an attention network, attention NN, to generate attention weight for the segmentation channels. Next, attention module generates the attention map by multiplying weights with the segmentation channels and then performing channel-wise addition of them.
The generated attention map is then applied to both the input RGB frames as well as flow maps. Then they are concatenated and fed into a post-estimation module. The post-estimation module is also called as post-NN, which contains two branches, a translational error estimation branch and a rotational error estimation branch. They are called as trans-NN and rot-NN respectively. Please note that in post-NN, we additionally use dilated convolutional layers to enlarge the receptive fields of the network. I would like to quickly show you an example of Deva with a video demonstration. The animation on the left-hand side shows the trajectories, the ground truth level, and Deva. The videos on the right-hand side show the RGB frames, optical flow maps, semantic segmentations, and attention maps of Deva from the first person's perspective. Please note that for the attention map, lighter colors correspond to higher attention weights. You can see that the attention weights of Deva change over time and are different, especially when the camera is making turns. Let's compare the effect of the attention module in our Deva design. The figure on the left-hand side shows the result of the Deva variant without the attention module. while the figure on the right-hand side corresponds to the result of the proposed stable architecture we just discussed. This can be seen that when making a 90-degree turn, the attention module has able to correctly capture the turning angle. Without it, the accuracy of the estimated turning angle degrades considerably. Next, I would like to discuss 3 sets of ablation studies that we have performed for Deva. The first one is Deva with and without attention module. Second, a comparison of dynamic and static attention weights. And third, a comparison of Deva with the variance architecture that employs feature-based attention mechanism. Let's begin from our first ablation study. Here we compare Deva with a variant that does not use the attention module. You can see from the picture that for this baseline, the attention module has been removed. We would like to see if the attention module is really important for our Deva design. In our second ablation study, we would like to see if our Deva is superior to the feature-based attention mechanism. In order to validate this, we created a variant that puts the attention modules inside the trans-unknown and rod-unknown branches, which are highlighted as the light green block in this picture. The attention module is implemented as an SE-net, which uses a global pooling layer in dark green, followed by 2 convolutional layers in orange color to generate attention maps. In our third ablation study, we compare the difference between dynamic attention and static attention mechanism. This figure shows how we implement the static attention variant. As you can see, the dynamic attention weights have been replaced with static weights. These static weights are treated as learnable parameters and are optimized in advance for the dataset. Here we compare the flow maps and feature maps of Deva with the 3 variants we just discussed in different rows. We show a video clip of them from the Kitty dataset, including the original RGB frames, their flow maps, and the feature maps. In the feature maps, red regions are where the pulse unknown is concentrated on. For Deva, it is observed that the proposed attention module enables the focus regions of trans-unknown to become steady and concentrated on straight rows. When the attention module of Deva is removed, the focus regions become unsteady and are scattered to multiple uncorrelated parts of the input frames for both trans-unknown and rod-unknown, leading to a degradation in post-estimation accuracy. For the static attention case, the focus regions of trans-unknown are widely scattered within the rod areas, as well as several other regions of the input frames, rather than concentrated on one or more specific regions or semantic categories as Deva. Besides, the focus regions of rod-unknown consistently fall on the bottom parts of rods, no matter the camera is moving forward or making turns. For the feature-based variants, the focus regions of trans-unknown are also not concentrated and scattered to multiple parts of the input frames, and the focus regions of rod-unknown nearly fall on an even narrower range of the bottom parts of rods than the static attention variants. Now, let's take a look of our experimental results. We perform our experiments on the Kitty dataset. We train the models on sequences 1, 2, 8, and 9, and evaluate the models on the remaining sequences. The top rows show the results of non-learning-based molecular BO, including OBSLAN2 and MESO2. The middle rows are the baselines we considered. The results of Deva and its variants are shown at the bottom. In this table, we compare the translational and rotational errors and denote them as T_real and R_real, respectively. Let's first take a look at the results of Deva, which is shown on the bottom right. You can see that the translational and rotational errors of Deva are much lower than MESO2, OBSLAN2, and most of the baselines. The average translational error of Deva is slightly higher than that of Bayesian et al. By 12.70%. However, Deva delivers a much lower average rotational error than it, without using any recurrent memory cell, as the main contribution of Deva is the introduction of dynamic attention. It is not surprising that the average rotational error of table is lower than all of the baseline methods. If you still remember, table uses optical flow maps as the inputs to its attention module. You may wonder what will happen if different input sources are used instead for generating attention maps. Here we show 3 separate implementations that use semantic segmentation, depth maps, and RGB frames as the inputs to the attention module. As you can see from this table, the errors of these 3 implementations are all higher than table. An interesting finding from the results is that these 3 implementations are still better than most of the baselines, indicating that the proposed table framework is effective even if the attention module is changed. Now let's compare table with the 3 variants for our ablation studies, showing on the 3 rows highlighted by the red rectangle. For all of these 3 variants, the translational and rotational errors are higher than those of table. This validates the design of table. When the static weights are used, or when the attention modules is removed, the error rate increased immediately. When the attention mechanism is changed to feature-based, the error rate also grows. Besides the error rates, we now illustrate the difference in attention weights of table and the static attention variants using histograms on the left-hand side. The top 2 histograms correspond to the attention weights of table for straight roads and turning things. It can be seen that attention weights of table are different for these 2 scenarios, showing that the attention weights are dynamically changing for different task categories. On the other hand, the static attention variant uses the same set of attention weights no matter the scenario is, leading to a higher error rate than table. Now let's use a timeline plot to illustrate the comparison from another perspective. The top figure shows the ground truth of the rotation angle, which is highlighted as the red curve. The figure in the middle shows the attention weights of table. We can see that the changes of table's weights align perfectly with the ground truth, which is highlighted as the light gray regions. Please note that the noisy regions of the table attention weights between the 650 and 730 frames is caused by the traffic flow in front of the camera when it is waiting to make a turn. Lastly, we also plot the weights of the static attention variant here as a reference, which are maintained as constant no matter what happens. Let's also take a look at the trajectories generated by table and the static attention variants. The ground truths are plotted as dashed lines. For sequences 14, 16, and 22 in the KT datasets that does not have ground truth labels, we use the trajectories of option 2 as references. It can be observed from the figure that the trajectories of table, which is shown in blue color, align closely with the reference dashed lines. On the other hand, the static attention weight variant, which is drawn as red lines, often deviates from the dashed lines. These figures therefore qualitatively validate the accuracies deliverable by table. In summary, table is a learning-based framework for estimating the equimotion of the molecular camera. To validate the proposed framework, we examine table as well as its variants and compare them with the other contemporary BO approaches on the KT STEM benchmark suites. In our experiments, table demonstrated superior performance to the baseline method, both quantitatively and qualitatively. In addition, we provided a set of questions analysis, validating each of our design choices adopted in the proposed framework. As the proposed mechanism that leverages dynamic attention weights from different semantic categories have been validated effectively and beneficial in our work, table thus offers a promising direction for future attention-based neo researchers. And finally, thank you very much for the attention.
Okay, we have the first paper presented, which is attention-based BO. double check whether the order is here. So if the order is not here, we can go ahead for the second paper. And for the second paper, so right after all the 4 talks, all the 4 contributed papers, we will have a short 10 minutes. And at that time, if we have the authors here, and we can ask him the question. If not, and we can go ahead. Okay, for the second paper, that is Hunter. Is Hunter here?
Yes, I'm here.
Okay, so you prefer to play the recorded video, or you want to?
I think playing the recording would be easier.
Okay, okay. But after, then we can play the video, and after the video, we can have the QA session.
Yep.
Does it sound okay? Okay, let's play the second video. Share presentation.
Hello, my name is Hunter Blanton, and I will be presenting.
So double check whether it works.
Yeah, it's working.
Okay, cool. So we got started from the beginning.
Hello, my name is Hunter Blanton, and I will be presenting our work titled Extending Absolute Pose Regression to Multiple Scenes. This work was performed in collaboration with my colleagues at the University of Kentucky in Design Technologies. In this work, we focus on the task of single image localization. This is the process of determining the precise location and orientation of the camera with respect to a fixed global coordinate frame. Traditionally, this is performed by finding feature correspondences between the image and a known map of the scene. For example, a common approach is to determine 2D, 3D correspondences between pixels in the query image and points in the scene, and then using the perspective endpoint algorithm for final pose determination. The difficulty of this approach lies in how the correspondences are determined. A popular approach is to first find similar images through image retrieval. The known poses and 3D information of the retrieved images can be used with pixel-level correspondences to find the required 2D, 3D correspondences in the query image. Another method involves directly matching pixel-level features against point cloud features in the scene map using a shared feature space. More recently, direct regression approaches have become popular. In scene coordinate regression, a machine learning algorithm is used to map images from a known environment to a dense scene coordinate map. Absolute pose regression with the CNN is an alternative to these correspondence-based approaches. Instead of performing correspondence matching, absolute pose regression requires training a CNN on labeled data to directly predict the position and orientation parameters of the camera pose. Once trained, these parameters can be applied to new images to directly compute camera pose estimates. Since the introduction of CNN-based absolute pose regression with PoseNet, absolute pose regression has been an active research area. Most work focuses on modifying the network or training process in order to improve pose accuracy. For example, learning the optimal loss weighting during training has shown to improve accuracy as well as reduce the need for hyperparameter tuning. Also, there has been success in using different feature extraction architectures such as LSTM PoseNet. Additionally, using a relative pose constraint during training, like in MapNet, improves pose accuracy as well as improves the correlation between feature vectors and ground truth poses. There are several practical advantages of absolute pose regression compared to traditional methods. They typically run in only a few milliseconds on modern hardware, as opposed to the potentially hundreds of milliseconds for high-quality feature matching and the use of a robust estimator such as RANSAC required for accurate final pose estimates in 3D geometric approaches. Also, because the CNN is a fixed computation pipeline, the complexity of the scene has no impact on inference time. Lastly, given the availability of sufficient training data, they are simple to train and easy to use. However, these benefits come at the cost of significantly worse performance in terms of pose accuracy, and unlike most correspondence-based approaches, results in scene-specific networks. That is to say, you must train a new network for each new location in order to perform accurate pose estimation inside it. While most work focuses on improving pose accuracy, we instead focus on the problem of needing scene-specific networks. Because these networks are deep CNNs, they are composed of hundreds of megabytes worth of weights, which becomes expensive to store as the number of scenes increases. We propose a method that greatly reduces the number of weights needed to be able to accurately localize within one of several scenes. A recent paper by Sadler et al. Goes into detail about the intuition behind and the limitations of absolute pose regression with the CNN. They factor absolute pose regression into 3 stages: feature extraction, a nonlinear embedding, and finally a linear projection onto pose space. The first stage is composed of the convolutional filters of the CNN. The second stage is composed of some number of feature transformation steps, such as a series of linear layers or LSTMs. Finally, the embedded feature vector is used to compute pose. This is computed using the final fully connected layer of the network. The weights learned during training act as a set of base poses, and the projection is expressed as a linear combination of these base poses. The motivation for our work is that while the final stage requires unique base poses for the specific coordinate frames of the scene, the first 2 stages are not strictly dependent on the coordinate frame and can be applied in general to several scenes. Here we show an example of applying PoseNet for localization within n different scenes. As we just discussed, we divide PoseNet into the feature extraction, embedding, and final pose regression stages. We combine feature extraction and nonlinear embedding into a single block for simplicity. Because each scene is a unique environment with a different reference frame, a unique PoseNet is trained and used for each scene. Alternatively, we propose to share the feature extraction and nonlinear embedding stages for multiple scenes. This significantly reduces the number of parameters required as opposed to using a unique network for each scene. An overview of our approach is shown. We use a single CNN feature extractor and use a database of scene-specific weights for the final pose regression layer. Like all absolute pose regression CNNs, we first extract an f-dimensional feature vector from the query image. Given that we know the image is located in one of n scenes, we extract the f by p weight matrix, where f is the dimensionality of the CNN feature vector and p is the dimensionality of the pose parameters. For example, if we use the 3 xyz components for position and the 4 components of a quaternion for orientation, then p would be equal to 7. This weight matrix corresponds to the trained base poses for the given scene. Once this weight matrix is extracted from the weights database, it is used as the final layer of the network, just as in PoseNet. To allow for completely automated use of our approach in the case where it is unknown in which scene the camera is located, we also use the CNN extracted feature vector for scene classification. In this case, we predict an n-dimensional probability distribution over all scenes and use the most probable scene to index into the weights database. In this way, our approach can be thought of as a coarse-defined localization approach, where we first identify the coarse scene location and then perform precise camera pose localization. For this work, we make use of the common Microsoft 7 Scenes dataset. This is composed of 7 indoor scenes of varying complexity. We also use the Cremers landmarks dataset. As opposed to 7 scenes, this dataset contains 6 outdoor environments, each at the scale of hundreds of meters. We first evaluate our method for pose accuracy. We report median translation and orientation error in meters and degrees. We compare our multi-scene PoseNet method, denoted as MSPN, to PoseNet and MapNet, 2 state-of-the-art absolute pose regression methods. These methods are trained for a single scene at a time, while ours is trained on all scenes of the dataset. This means 7 total for 7 scenes and 6 total for Cremers landmarks. We also compare to a naive baseline approach in which we train a single PoseNet for all scenes simultaneously with no modification. For 7 scenes, our method is competitive with and sometimes outperforms the single scene approaches. To highlight the advantage of our method, we mark in red the cases where we significantly outperform the naive multi-scene baseline. For Cremers landmarks, our method does not perform as well. We discuss this on the next slide. In the next experiment, we evaluate our method for training on different subsets of scenes. Specifically, we train on all but one scene from each dataset. For example, the line labeled without fire means we trained and evaluated on all other scenes from the 7 scenes dataset. Because we did not train on the fire scene, we cannot evaluate and this cell is left empty. For 7 scenes, we see that performance is more or less constant regardless of which subset is used for training. However, we see a significant difference in performance for Cremers landmarks when not using the street scene. In this case, we actually begin to see position error on par or better than the single scene methods. This is interesting because the street scene is very complex and difficult even for traditional methods. We believe the difficulty of this scene is expressed in the impact that it has during training of the other scenes. We next evaluate the impact of scene classification in our network. To test this, we perform localization in two scenarios. In the first, which we call the scene oracle approach, the scene of the query image is known, so the correct final layer weights are always extracted from the weights database. The second approach, labeled end-to-end, is the case where we have no prior information about the location of the query image. In this case, the network must first perform scene classification in order to determine which weights to pull from the database. For both datasets, we use all scenes for training. We report both median position and orientation error, as well as top 1 scene classification accuracy. Note that even in the cases where the scene accuracy is 100%, the metrics differ because each experiment was trained separately. For 7 scenes, there is not a significant change in performance between the two experiments. For Cremers landmarks, however, we observe more varied error metrics. The position error is typically better in the end-to-end case, but orientation error is typically worse. For all other experiments in this presentation, we report metrics computed using the scene oracle approach. Next, we investigate how well the learned features from the CNN generalize to novel scenes. In this experiment, we pre-train our network on 6 of the 7 scenes and use the CNN as a starting point for transfer learning to the held-out scene. The scene-specific final layer is randomly initialized. We compare to the normal ImageNet initialization after training for only 1 epoch. After this short training period, the CNN pre-trained on other scenes produces much lower median error across the board. We also show the same experiment extended to 10 epochs for the fire scene. For both initialization methods, we show median position error in meters on the top figure and median orientation error in degrees on the bottom figure. The x-axis is the training epoch. Initializing from multi-scene PoseNet training on other scenes not only converges to lower error, but reaches the minimum much faster. Finally, we evaluate the impact of training not only with multiple scenes, but with multiple scenes from 2 separate datasets. For this experiment, we train our network for 3 scenarios. First, we do single scene training. Next, we train with all scenes from within the same dataset. And finally, we train with all 13 scenes from both the 7 scenes and Cremers landmarks datasets. We plot the median position and orientation error of each training scenario for each scene. Single scene training is denoted by the blue bars, single dataset training by the red bars, and multi-dataset training by the green bars. Note that even in the single scene training case, we train the networks ourselves, so this does not correspond to the reported PoseNet or MapNet metrics. Overall, we observe that performance is relatively stable in most cases, regardless of the training setup. Thank you for watching.
Okay, thank you. Stop sharing. So Hunter, are you here still?
Yes, I'm still here.
Okay. I got a question from the audience. The audience is asking a question regarding extending the absolute pose regression to multiple scenes. And here, the audience is asking, do you decide one scene for an image where had association? And the follow-up question would be, would a probabilistic scene assignment could be better in the scene selection in your pose estimation?
Could you repeat the first question?
Oh, so it's mainly about whether when you train the multiple scenes, do you decide one scene for one image where had association?
Yeah, so each image is assigned to a single scene.
Okay, and a follow-up question is, do you think a probabilistic scene assignment could be better in pose estimation when you're training?
So in this case, I think the a non-probabilistic approach would make more sense since we're doing this fixed like final linear regression into the pose. But there is work such as ESAC from, I think it was published in ICCV last year, where they do a more probabilistic like scene prediction, and then they factor that into their like ransack based approach for the final pose determination.
Okay. One question for me is, in post-night, the post-night authors claim in their paper, their size, their network size is always kept to be within 50 megabyte. And do you have the number for your network size? And when you run this network, do you have do you have the number for the speeding? For example, how long it takes to localize one image?
Yeah. So for the networks we used, I don't remember exactly, but it was around 150 megabytes per model.
Okay.
And for speed, it was about 5 seconds on is a 1070 GPU.
Okay, 5 seconds.
Or, 5 milliseconds. I'm sorry. 5
oh,
milliseconds.
okay.
Yeah.
that makes much more sense.
I'm so used to working at the scale in milliseconds.
Okay, great. Okay, so right now the network size is becoming bigger than the post-night. Where do you think it mainly increases the size from post-night?
I'm actually not sure. I would have to go back and look at it. It may be that the way I'm saving the weights.
Okay.
So I'm just looking purely at like when I train it in PyTorch, the model that gets saved is on the order of hundreds of megabytes. It could be that the actual necessary parameters in there are closer to 50 megabytes.
Okay, cool. Yep. Yeah. Okay. I don't see any other question. And thank you again. And there are about another 170 people and watching you talk. So I would say I'm the representative of all the audience. Okay. So let's go to the next. The next would be, let's stop sharing first. Okay. The next would be Aniket. Is Aniket here?
Yes, I'm here.
Okay, so you will give a live presentation, right?
Yes.
Okay, please go ahead.
Yeah, just a second.
Sure.
Yeah, so hello everyone. I am Aniket Pokre, author of the paper Reconstruct, Rasterize, and Backprop, Dense Shape and Pose Estimation from a Single Image, along with Aditya Agarwal, Krishnamurti, under the guidance of Professor Madhav Krishna from International Institute of Information and Technology, Hyderabad. We propose a method of obtaining dense object shape along with the 6 DF poses from a single monocular image. So what we are aiming to do, our task is, given an input image, we estimate a dense shape of the object and its 6 DF pose. This would be very much essential for an object-based SLAM. That is, if we wish to do SLAM or ego motion estimation using objects, we would want to know their 6 DF poses with respect to cameras. So how do we generate 3D meshes? There have been many recent methods which estimate dense shape from images in the form of meshes like occupancy networks, 3D voxels like 3D R2 N2, and point clouds like the point set generation network. As will be explained in the later sections, we will be using occupancy networks for generating meshes for our pipeline. Each method has its upsides and downsides, but generally speaking, voxels need a large memory footprint. Point clouds methods don't really have the connectivity in the structure as compared to a mesh and require further post-processing steps to generate surfaces. Meshes, on the other hand, tend to give good quality surfaces, which tends to be useful in further image rendering applications. So for our case, we used occupancy networks to generate 3D meshes. We further render the mesh onto the images and then use them for our pose estimation. So what is the task of 6th degree of freedom pose estimation? It is the estimation of the rigid body transformation, that is rotation and translation of an object in a known coordinate frame. There have been several methods catering to the above task. I would like to mention a few examples like key point based methods, in which the key points are detected in monocular images using deep learning, and models like wireframe models are fit using PNP techniques. 6pack tracks a set of geometrically consistent set of key points on objects in RGBD videos, in which it finds the relative pose changes of the object over time, which enables to give a 6DOF pose. Dense fusion uses an architecture that processes color and depth information differently, and then fuses both of them using a dense pixel-wise fusion network. In post-CNN, an end-to-end 6DOF pose estimation network has been trained with an additional pose refinement step. The 3D reconstruction methods that we have gone through cannot be straight away used for downstream robotics tasks, since we need to be in the camera frame. That is, we need to know the scale and pose of the mesh with respect to the camera. So this 3D reconstruction methods from monocular images reconstruct objects in canonical frame and has no notion of pose. Hence, to be usable, we need to couple 3D reconstruction with 6DOF pose estimation so that we get the 3D reconstruction in the camera frame. So in this case, what can be used? We use the idea of differentiable rasterization. So what is differentiable rasterization? When we project an object onto an image, we project the vertices of the mesh onto the screen coordinate system, and then we generate the image through grid sampling. The latter process is called rasterization, which is not differentiable. There are quite a few methods which deal with differentiable rasterization. First is neural 3D mesh renderer, which proposes an approximate gradient for rasterization, which can help to pass gradients through the process of rasterization and enables further optimization tasks. Soft rasterizer views rendering as a soft rendering process in which all the mesh triangles have a probabilistic contribution to each rendered pixel. The interpolation-based differentiable renderer views foreground rasterization as weighted interpolation of local attributes and background rasterization as distance-based aggregation of global face information. But for our purpose, we use the neural mesh renderer by Kato et al. So this is our complete pipeline. Given an input image, we pass the image through the 3D reconstruction network, which gives a mesh of the object. In order to get the scale of the object, we assume the camera height is known. We do this by projecting the mesh onto the image and iteratively solving for the scale of the mesh by comparing the bounding box of the projected mesh and the reference mesh. We also pass the image through a pose regressor network, for which we use render for CNN, which gives us an estimate of the viewpoint of the object. We get an estimate of the translation of the object by using the given camera height. We take the pose from the pose regressor and use it as an initialization for the neural mesh renderer to optimize for the 6DOF poses. So here we show some of the qualitative results of our method. We take the output pose of the pose regressor and reproject the mesh onto the image, which is used as an initialization for the neural renderer. As can be seen, the neural renderer then optimizes for the 6DOF pose by comparing the reference and the reprojected images using simply the pixel-wise intensity difference as loss and gives an accurate output. So we also showcase our method for an object-centric ego motion estimation on a synthetic dataset, and we can see that our method gives better results as compared to OpsLam. In this dataset, we generate the trajectory using only a single chair. Note that we have used only the chair and no other feature to generate the poses. We obtain the camera to object poses and then convert them to a camera trajectory. In this case, we have used multiple chairs to generate the trajectory, and here also it outperforms OpsLam. We see that OpsLam doesn't perform as well since the environment is quite textureless. In our case, the objects are used as features, and we estimate the camera track using only the objects. So our method can be used to aid SLAM and improve SLAM or odometry results. So to summarize, we propose to generate the 6 TOF poses from a monocular image. That is, we construct a dense mesh reconstruction from a single image and then estimate the pose of the object in camera frame. We also demonstrate results on a monocular object-centric ego motion estimation setup using only 3D objects as features. Future works can focus on obtaining object reconstructions on images with background. We can also replace the iterative optimization with an end-to-end neural network. So thank you. Thank you for the presentation.
Okay, thank you, Aniket. Okay, we have a couple of questions, and the first question would be, so here you use one image as the input, and you can get the 3D reconstruction and as well as the camera pose. And I would assume for those images, you already get the silhouettes, and which means the background and foreground. And in real applications, and in this case, in real applications, you need to do the segmentation. And have you ever come out with any solution if your segmentation is not perfect for silhouettes, or it's just you have tested on real images?
We have tried to test on real images, like we used Detectron 2 from Facebook to give us a segmentation mask, and then we tried to train the occupancy network in order to get the occupancy net meshes. But we used after training, we got occupancy network meshes given the segmentation mask. But then, in order for the neural renderer, we take the silhouette loss and we backpropagate that loss. So in that case, the segmentation that we got from Detectron was not good enough to give a good pose. So that is a problem that we were encountering. We did try it for real works, but it wasn't working as well as we expected.
Okay, got you. Okay. And another question is, we'll try to do the reconstruction, and in your last several slides, actually show the trajectory around the object. Do you have the mapping result for that one? You show the trajectory around a virtual object, but do you have the 3D reconstruction for that virtual object?
I do have the 3D reconstruction. And it is a good reconstruction. So the trajectory, the more accurate the 3D reconstruction, the more accurate the trajectory is. So
okay.
Yeah.
Okay. Is there any other question? I don't have any other question right now from my side. Okay. So okay. Thank you, Aniket, and special thank you to you, because right now the timing in India is somehow very early, right? What is time in India right now?
Actually, I'm in Tokyo now, so it's 6:30 a.m.
Oh, okay. 6:30. Okay. It's still pretty early. Yeah. Anyway. Okay.
Yeah.
Okay. Thank you very much, Aniket.
Thank you so much.
Yeah. Thank you. Okay. Let's come to the last contributed paper talk. Is from Felix Ott. Is Felix Ott here?
Yes, I'm here.
Okay,
Can you hear me?
Okay, we can hear you. So we are a little bit ahead of time, but please feel free to go ahead, and you could have actually a little bit longer time than for presentation and the Q&A.
Can you see my screen?
Not yet. Yeah, right now it works.
Okay, perfect. So thank you all for participating and your interest in my presentation. My name is Felix Ott from Fraunhofer IAS in Nuremberg, Germany, and I'm going to present Viper, Visual Odometry-aided post-regression for 6 degree of freedom camera localization, which is based on a postnet-like architecture for absolute post-regression and a visual odometry-aided relative post-regression based on optical flow, and which uses these two modules based on LSTMs. Motivating for our paper, we want to localize autonomous robots and objects in large-scale indoor industrial environments, for example, warehouses with high-level racks. As shown in the test and application center at the Fraunhofer IAS in the figures below. As such warehouse environments typically include a costly infrastructure with radio, LiDAR, or radar bus-based systems, we wanted to use a single, inexpensive monocular camera for inside-out self-localization. As visual odometry accumulates a positional drift and long-term navigation tasks, we use convolutional neural networks as it showed to improve visual odometry in various aspects. We wanted to use to stabilize the long-term drift and reduce the short-term error of post-prediction by introducing optical flow for relative post-prediction into the absolute post-prediction module. For evaluation, we analyzed environmental influences such as large and small-scale areas, ambiguous and volatile elements, but also separated ego from future motion, for which the test and application center at the Fraunhofer IAS perfectly allows to create a dataset that covers all these aspects. SLAM-driven 3D point registration methods enable a precise self-localization even in unknown environments. SIFT-like point-based features for the localization from landmarks require efficient retrieval methods, use VLAD encodings such as dense VLAD, use anchor points such as AnchorNet in the figure right, or use RANSAC-based optimization such as active search by settler. Visual odometry has made remarkable progress over the last decade, but it still suffers greatly from scaling errors of real and estimated maps. Visual odometry primarily addresses the problem of separating ego from feature motion, but it suffers from area constraints, poorly textured environments, scale drift, and also from the lack of an initial position. Hence, we wanted to use a postnet-like architecture for absolute post-regression module that are more robust, less compute intensive, and can be trained in advance on application data. Related work for absolute post-regression is, for example, RelocNet, KMNet, and NNet. These methods learn metrics continuously from global image features or use a database, as seen in the figures right. The key idea of PostNet and its variants is BranchNet and Hourglass uses convolutional neural networks for camera relocalization. They seem to be partially insensitive to light changes, occlusions, and motion blur. PostNet 2 learns the loss and architecture parameters of the network. PostNet plus LSTM, DeepVO, ContextualNet, and Whitlock exploit the time context that is inherently given by consecutive images. The key idea is to identify temporal connections in between the feature vectors with LSTM units. Related work for hybrid methods are, for example, VLogNet, TGRNets, and MapNet that use the absolute post-regression techniques and combine it with visual odometry, for example. The related work for optical flow-based visual odometry was very rare. To the best of our knowledge, there exists only flow-odometry and LSVO. To address robot self-localization in industrial indoor environments that was not covered from these methods before, we introduced visual odometry by optical flow into our absolute post-regression technique, here a postnet-like variant. That's why we introduced 3 different modules for absolute post-regression. Furthermore, we can easily replace each module with a different technique. The whole pipeline we call Viper, Visual Odometry Aided Pose Regression. So we have a absolute pose regression module, a convolutional encoder, a relative pose regression module that's based on optical flow and LSTMs. And we put the absolute and relative poses into the fusion module we call pose estimation, PE, that regresses the absolute pose. And our goal was to optimize the absolute pose from the PE network to the absolute pose of the APR network. In the following, I go more into detail of these three modules. The input of the APR network was 3 input images. As data preprocessing step, we center cropped the images to size 224 times 224 and subtracted the mean of all images. As we have 3 input images, the model is time distributed and we use the convolutional encoder GoogleNet. Similar to PoseNet, we replaced the softmax layer with a regression head. With 2 fully connected layers, we regress the absolute pose P in Euclidean space and the absolute orientation Q as quaternions by minimizing the loss function given below. We set alpha 1 to 1 and we search for the optimal hyperparameter beta 1. The input to the relative pose regression network RPR are now 4 input images, as we have to calculate the optical flow between each consecutive image pair. We use FlowNet2 as FlowNet2 has a very high frame rate of 120 Hertz, and it showed to have a very high accuracy. We put the optical flow into the recurrent unit. We use here 3 stacked LSTM layers. The regression head is again similar to the APR network, just that we regress the relative pose, so the displacement and the rotation of the camera. So the loss function is again similar, just that the poses are relative, and we first have to transform the ground truth absolute poses, so the global coordinate systems, to the relative poses cameras. So we have the absolute positions and orientations of the APR network and the relative poses, so the displacements and rotations of the RPR network. We concatenate these features and have an input size of 3 times 14 to the PE network. We put this tensor into the recurrent unit that consists here of 2 stacked LSTM layers. The regression head is exactly the same as the regression head of the APR network, just that we use different hyperparameters for the loss function. We again set alpha 3 to 1 and search for the optimal hyperparameter beta 3. And we get the complete pipeline Viper. So again, we have data preprocessing with center cropping and mean subtraction. We compute the optical flow with FlowNet2, and we have the 2 modules APR and RPR. The absolute and relative poses is the input to the PE network. And for evaluation, we compare the absolute poses of the PE network with the absolute poses of the APR network and report the improvement. For evaluation, we need a suitable data set. There exists currently many different data sets, but for our industry scenario, they weren't really suitable. So we decided to use the Microsoft 17's dataset, as it was the most used dataset. As heard in the previous presentations, the 17's dataset was recorded in indoor office scenes, several 10,000 images, and the spatial extent is very small, so we are below 4 meters. Current methods achieve good results on datasets for autonomous driving, for example, on the Kitty dataset or on the Microsoft 17's dataset. Here, FoulLogNet achieves the highest accuracy. These methods are optimized on such datasets and do not cover our aspects of Rotobot self-localization. Hence, we require a novel dataset that addresses large-scale indoor industrial environment. And for that, the Link Test and Application Center at the Fraunhofer IAS in Nuremberg is perfect. because it models indoor industrial environments with 3 high-level warehouse racks. The link center includes ambiguous and untextured elements, and we can model small and large-scale areas in the link hall. For data recording, we use the 3D positioning system that can drive through the complete link hall and automatically records ground truth labels with sub-millimeter accuracy. So we have a higher accuracy of labels than, for example, the Microsoft 17 dataset. The positioning system can drive through the link hall with up to 0.3 meter per second, and we place the cameras at the bottom of the positioning system. And then we record the industry dataset that consists of 3 different scenarios. Scenario number 1 consists of several 100,000 of training and test images. Example images you can see in the top right at 1 time step from 8 cameras that were placed on the bottom of the positioning system. In the 2 figures left, you can see the trajectories of the training images that were recorded in a horizontal and vertical manner. And the 8 testing datasets are perfect to evaluate for different aspects. For example, the cross dataset has a large-scale area in the middle of the link hall and a small-scale area in between the warehouse racks. These areas also cover the small and large-scale datasets, but here are also the ambiguous elements included that were represented by the big black walls here. In the figure, you can see this. The volatility dataset contains elements that were not included in the training dataset, so we can test here for volatile elements. Scenario number 2 was recorded also on the positioning system, but with 3 wide-angle cameras. It consists of more velocities and different variations than scenario number 1. And the size of the area is also smaller. The challenge here for example, visual odometry is that the movement direction of the testing dataset was different than the movement direction of the training dataset. And to have a more movement-like scenario that simulates an autonomous robot, we recorded scenario number 3, also with wide-angle cameras on a forklift truck. The forklift truck simulated putting in or removing elements from the warehouse racks. The camera movements are now at a varying fast and dynamic speeds, and so scenario number 3 is the most challenging dataset of the industry dataset. We train now the APR model, the RPR model, and the pose estimator. And we present here the results of the APR only network, the APR plus LSTM network, and Viper. We present the results for the Microsoft 17 dataset and for all scenarios of our novel industry dataset. And we show the positional improvement of Viper against APR. All results are in meters for position and in degree for orientation as median errors. We go more into detail of the mostly significant results. For the Microsoft 17 dataset, Viper improves only from 0.33 to 0.32 meters. That's averaged over all scenes. As this dataset contains much motion blur and the relative position between consecutive image pairs was very small. So the RPR module has only a small impact to Viper. So the positional improvement is only about 3%. The average for scenario number 1 is for APR only 2.82 meters and for Viper 2.53 meters. So we improve about 12.3% in average. For example, the cross data set improves from 0.61 meters to 0.46 meters. And here, as I said, is the large scale area in the middle of the link hall, and the small scale area in between the warehouse racks. Also, the large scale and the small scale area covers these areas. You can also see here the improvement about 10.7% and 40.4% in position, but the improvement is smaller than the cross data set because here the ambiguous elements were included. For these positions, the error increased. So from these data sets, we can say that Viper is more robust against differently scaled areas. For the volatility data set, Viper improves from 2.1 to 1.96 meters. That's an improvement of about 6.4%. The improvement is only 6% as in this data set, volatile elements were included that were not included in the training data set. But RPR has a positive impact, rather it is small. You can also see that the orientation error increases here as also the APR network is not robust against these volatile elements. So the orientation error increases here. For scenario number 2, Viper improves from 0.2 meters to 0.2 meters. From 0.27 to 0.2 meters. That's an improvement about 30% in position, but the orientation error decreases. That's because, as I said, here in the test data set, relative movements were included that were not included in the training set. So RPR cannot fully generalize to new movement directions, and hence the orientation error decreases. For scenario number 3, that was the most challenging data set, the varying and high dynamic ego motions were included. But Viper improves from 0.32 to 0.27 meters. And the orientation error is unchanged. Into detail of the RPR network, for example, for scenario number 3, we get an average error in median for X direction in about 2.5 centimeters and in Y direction of 4.1 centimeters. That's pretty good, but RPR is unrobust in cases where optical flow is computed by FlowNet2 wrongly. That happens, for example, if the camera is very close to the warehouse rack and the movement direction was not clear. If I compare APR and Viper, I can summarize for scenario number 1 that Viper is, through RPR, more robust in small and large scale areas. If I compare the trajectories from scenario number 2 here in the left image, we can say that Viper compensates the long-term drift and smooths the short-term errors. For scenario number 3, that were where fast and large scale and high dynamic echo motion was included, also Viper smooths the trajectory and reduces the short-term errors. And in conclusion, we introduced a novel data set that was not covered by different methods before. We tuned our method on this data set to address challenges of large-scale indoor industrial environments. We increased the accuracy by introducing optical flow for relative post-regression, and we addressed different aspects. And in future work, we want to evaluate different available methods on the industry dataset and show the applicability of self-localization of robots in industrial environments. And if you have now any questions, I would be happy.
Okay, thank you, Felix. We have a couple of questions. And first, for your own data set, how did you get the ground truth?
In the link hole, there are 10 Nikon IGPS systems included. You can see this here, that's very small, and it delivers a accuracy below 1 millimeter.
Okay.
So we can cover here the whole link hole.
Okay. Okay. So those markers around, I can see the markers around. It seems very small though. Okay. And when you do the localization, does those markers still those markers in the images when you do the real testing?
Sorry, which markers?
So for those, I can see them. So I can see those markers on the around the scene. Seems like, is it some markers there?
The QR code node that is not used. That was for a different project, yes.
Okay, for those you get ground truths from those, but when you do the testing, are those kind of QR codes still in the testing images?
We record ground truth labels for training and testing dataset, but they are not used for testing, only for training, and we use the ground truth labels for testing.
Okay.
Yeah.
Okay, and another question is, when you show the APR and the RPR, and it seems like they are in parallel, and finally goes to the the final loss. I forgot the name of the final loss.
PE network, yes.
Yeah. And when you do the testing, when you last a couple of experiments, and you show just using APR and the final VIPR, and what is the improvement, and later you show the RPR and the final experiment. And have you seen somehow when you do the testing, you use the network trained on the complete network, and to finally get the camera pose, or you just remove one APR or RPR and train on a separate branch, and which way did you do for that testing?
So we trained each module separately. We first trained APR and RPR, and we also tested it separately. And then for training the PE network, we predicted the poses with APR and RPR. That was the input to PE, and trained it with that. And testing of the PE network is the same. So we predict the poses with APR and RPR and test the PE network.
Okay. So for you show the position and you show the rotation, and do you have some conclusion whether it's your current relative you added the relative pose regression, and the relative pose regression improves position more or rotation more in accuracy?
Sorry, I think I did you answer.
So you should after you adding in VIPP compared with post night, and here you increase the position and the rotation accuracy, and which aspect in position and the rotation, which aspect is improving more from the relative post regression net?
So we increased the accuracy of APR more, but that also depends on the movement patterns and the ambiguous elements, for example. So how exact APR and RPR is, and on the accuracy of the single networks depends also the improvement of the PE network. So we can't really make a general statement about how position and orientation exactly improves with PE, because it also depends on the scene and on the movement pattern.
Okay, and do you have the speed about your localization?
Yes, so APR is the Google net that I think is below 21 million parameters, and for comparison, RPR has about 200,000 parameters for training, and PE below or approximately 100,000. So the RPR and PE network are very high to predict and to estimate the pose. So the speed is just a bit slower than the APR network.
Okay, I can see you are using optical flow in the RPR and optical flow. It depends on what kind of optical flow neural network you are using. You are using neural network or traditional optical flow here.
Yes, we use FlowNet 2 to predict the optical flow, and that we use for the RPR network.
Okay, and FlowNet, I remember that is pretty large, and here I can imagine, and your network will, by adding the relative, by adding RPR, would also increase the size of your neural network significantly. Is it true?
Yes, but FlowNet 2 was, when we developed Viper, the fastest network for optical flow, I think 120 hertz. And so the impact of predicting the optical flow was not high.
Okay, but I can imagine you can optical flow, you are just using their existing network here, but you can replace it with any other things that could still work for your RPR.
Yes, we can replace FlowNet 2, and we can also replace RPR. So I think we could also replace it with flowdometry that directly predicts with FlowNet the relative position. That could also be an option, but we did it that way to better evaluate it for every detail.
Okay, great. So is there any other question from the audience? Okay, if no, let's thank to Felix again. Thank you very much, Felix. And I can imagine, I can imagine it's also very late in Europe. It's 12 o'clock, right?
Yes, almost 24 p.m.
Okay, so this is our last contributed paper talk. We will probably will take. Is there any other question from the audience for any of those papers? The first paper's author is also not here, right? Okay, then we can have about 15 minutes coffee break, and we will come back at 6:10, and we will follow up with Dr. Shichao Yang's talk and Kristen Grauman's talk, and later is Shuxue Quan's talk, and finally that is Pierre Moulon's talk, and we will follow up with another 4 exciting keynote speakers. Okay, we will have 10 minutes break, 10 to 15 minutes break. So I can see Shichao is here.
Yeah, yes.
Oh, yeah. Okay. What about we just wait another 1 minute and then we can get started. And I will introduce you. And
Sure. Thank you.
Okay, what about we get started? So let me first introduce Dr. Shichao Yang, and it's my pleasure to introduce Dr. Shichao Yang, and we invite him to give a talk here. Dr. Shichao Yang is a research scientist in Facebook Reality Labs, and before that, he received his PhD degree in robotics in CMU, and his research is mainly on SLAM, visual geometry, semantic scene understanding with applications to AR, VR, and robotics. And he has published papers in top conferences and journals, for example, Journal of Field Robots and Acro Eros, those kind of top journal and conferences. And he has quite a lot of interesting work like pop-up SLAM, direct monocular odometry using lines and points. And I believe he will give a fantastic talk to introduce more details about his outstanding research. Okay, let's welcome Dr. Shichao Yang to give us a talk about his research.
Yeah, okay, thank you. Wait a minute, let me share the screen. So can everyone see the screen, see the slides?
Yeah.
Okay, cool, thank you. Yeah, hi everyone, I'm Shichao Yang, and thanks for the great introduction. I'm very honored to present in this workshop. I was previously a PhD student in Carnegie Mellon University in Pittsburgh, and now a research scientist in Facebook Reality Lab in Seattle from last year. So today I will present some work on the visual SLAM with objects and planes. And so it's mostly from my previous PhD work and also some new work in the Facebook Reality Lab. So the work has been working jointly with the Sebastian Fischer and Michael Case, and also the colleagues in Facebook like Jakob and Richard. So as we know, like SLAM stands for the simultaneous localization and mapping, and it has been used in many applications like robot inspection, autonomous driving, and augmented reality. In this talk, I will focus on the monocular camera case, and two representative visual SLAM like OpSLAM and DSO, which both use points and maps as map representations are shown here. And also there's some other paper using lines. From this video, we can see that the classical visual SLAM can work pretty well in like general normal environments. However, there's still some challenges with current point-based SLAM. For example, when it may not track well in low texture scenarios with few feature points, and also it's difficult for like lifelong localizations applications, especially when there's, for example, sunlight, weather changes. And also for other applications, we need just point-based map is not enough for many applications. For example, for AR, if we want to enable the physics-based interaction, and we need to detect objects and the planes and treat them as an identity so that to interact with them. And also for the like autonomous driving and so on, we need to explicitly detect these objects. So actually, for human perception, when we look at these images and scenarios, we focus more on the objects, planes, and also the general environment layouts. So to address these challenges, we want to build a SLAM system like similar to this kind of human perception. Basically, we want to, like for example, the input is a sequence of image. We want to estimate the camera pose and also build a map of 3D objects and the planes instead of just pure point-based map. And this map will have many more advantages. For example, it's dense, it's more compact, and also semantically more meaningful. This whole problem is actually a combination of the SLAM and the scene understanding, basically object or plane detection. And we will demonstrate that actually these two tasks can benefit each other in one system. So there are many related work about these problems. I will first review the literature from different perspectives. The first one is the optimization pipeline or optimization method. I mean, the easiest way to think of this problem is a decoupled like sequentially SLAM optimization problem. Basically, we first build the you first use the classic point-based visual SLAM to estimate the camera pose and even point position. And then based on this camera pose and point position, you do further detection or further refinement. And but this kind of approach also has one drawback, that if the SLAM fails or point cloud is low quality, its 3D object detection or plane detection will be difficult. And the other method in contrast to this is the tightly coupled way, which you try to optimize the camera, object, and plane together, and you hope to get some benefits of combining them together. And there are many examples here using either planes or objects. And then we can look at how to represent these objects in the SLAM optimization problems. The left column shows the simplest case, which you don't have any shape prior. So basically, then we have to modify the object just as a geometry identity, for example, cuboid, sphere, or ellipsoid. And then on the right side, that is more when you have an accurate shape model like CAD model or point cloud model, you can just use this model, and you only need to estimate the 60 pose for it. And in the middle column, that's the middle column is in between is the weak prior case. For example, a car can be represented by a few key points, and then we can only use these key points to represent a car. You can do like PMP from it. And for more general case, like other objects in addition to car, we have to use some like learning-based method to represent it. For example, you have shape encoder can be used to represent an object by high dimension like vector, and then after decode it, you can get a like mesh or point cloud from it. These are all the different ways of representing objects in the optimization problem. And lastly, I will list some commonly used cost functions to optimize the object. First is object to camera measurement, like 3D measurement. For example, in each camera view, you can detect the object pose. And then you have a relative pose measurement for it. Basically, it's a 6DLF SE3 pose. And then you can build a like object pose graph, similarly to commonly used the camera pose graph in the SLAM system. But this kind of method is easy to implement, but it requires each detection to be accurate. And so usually this method applies. Usually this method is adopted for this depth sensor, for example, RGB or later. And the other measurement is more complicated. We want to measure the object from the 2D image observation. For example, this 2D image, in a simpler case, it could be a bounding box or semantic segmentation. I mean, for the more complicated, it could be like photometric error or silhouette error when you have a dense 3D model for this object. And the last one is also commonly used, which is the object to point measurement. For example, you have a prior 3D model for this object, and you have some key points for it. Then you associate key points accurately with your image. So this is more like a PMP associations. And after talking about these approaches, and I want to highlight my contribution in this presentation. We propose the first molecular object and plane SLAM without shape prior model, without a dense shape model. And we also demonstrate results in large scale environments from indoor, outdoor, and to kitty like different objects. And more importantly, we show that scene understanding like 3D object detection, plane detection can benefit the pose estimation and vice versa. So basically, like when you have objects and planes, it will predict provide additional geometry or semantic constraint to your SLAM optimization. And SLAM on the other side, since it has multi-view information, it will further refine your object detection. So that's how we demonstrate this in one system instead of like decoupled way. And this is a diagram of a whole system. So the input image used for camera tracking. And meanwhile, we also detect 3D object and planes from it. And then this object plane will use together, will be optimized together with points and camera. And they have some communication between each other. For example, like camera tracking can provide a camera pose in order to have better object detection. So here are some preview results video, like demonstrating like object-based SLAM and object and plane SLAM and dynamic objects. So all this can be found in the two paper and also the code at the top right corner. So now I will explain more details how this happened. So it basically composed of two parts. One is a single image, understanding how to detect the object and plane, and then on the multi-view, how to optimize them. So for the single image detection, I think there's already some presentation before this talking about 3D detection. So I just very briefly go through this. So there already been 3D detection has been a hot topic in vision, and deep learning approach usually can directly regress the pose, but this is usually assumed to have an object shape model, so you can directly regress the pose. And just for car, there's also some work of using cuboid to represent it. Basically, you don't have to have a prime model for it. But this usually only applies to a very simple geometry like car. And however, in our system, we want to make sure the algorithm can generalize pretty well to diverse objects or never seen objects. Therefore, based on the existing approach, I modified the code and algorithm to adapt to the more general object detection. So basically, the input to our 3D detection is, okay, you have 2D image and also have a 2D bounding box which from the detection pipeline. And then you also have a camera pose, basically an initial estimation of your camera pose respect to the ground, which could come from the SLAM pose estimation. And then we generate many proposals to score the best one. I think this is similar to to the common used object detection. So the contribution here is how to generate these good cuboid proposals for 3D objects. And we propose a way to efficiently generate good proposals and also without shape priors. So I will just briefly go through this because it has already been in the paper. So this slide shows how to get the cuboid proposals. So as we know that vanishing points, a cuboid has 3 vanishing points on the image. And if we have so basically that means if we have 3 vanishing points, and then if we know a point like a corner image, cuboid corner on the boundary, then we can find all other corners through this kind of point intersection, because the vanishing point is computed from this edge intersection. And by doing this, this approach is efficient and high quality because all the 3D proposals you can will fit the 2D bounding box after projection, because this is guaranteed when I generate these proposals. So with these proposals, we can further score them based on the image view, based on the image measurement. I mean, I just implement a very intuitive way to score them based on the edges. So I want to find cuboid proposals, the cuboid proposal which align with the image line segment better. For example, the image here shows some good proposal and a bad proposal, and a good one aligns with the image very well. This kind of cost one is easier to implement and also has few parameters. Few parameter means it can generalize well to different objects, and I think pretty sure that this can be extended to use deep networks to automatically score them, similar to current 2D object detection. So we show some results of 3D detection. Basically, we want to enable to have more we want to robustly detect more objects and more accurately on the data set. Since we don't have the prior model as shown in the image, we are able to detect different kinds of objects. And for the outdoor kitty data, our method is worse than the deep learning approach. I think this is also understandable because on the kitty you only have one object. If you use many data sets to train it, it's likely to have better performance. So, and actually I mean, just for this single module and also my later plane detection, it can be directly plugged in by other kind of deep learning based approach detection. So my way of plane detection, and the plane I mentioned here is just the room layout. It's not, for example, it's not like table surface because I don't have, at that time I haven't figured out a way to detect it robustly from image. So here for the this is also called like layout prediction and vision. And the early works are usually model based. For example, you have a cuboid room, then you have like vanishing points as mentioned before. So basically this kind of approach we usually, and also deep learning based approach to predict this, but they usually have the structure assumption, for example, a cuboid room or its own defined structure. Then it may not satisfy, for example, you walk in the corridor, it doesn't satisfy this kind of assumption. That's why I want to propose a way that could generalize well for indoor environments. And also for this kind of learning-based prediction, since they predict the layout in each frame, so this kind of prediction may not be consistent in each frame. However, for SLAM, if you want to directly use SLAM, it's better to let the detection be invariant, just like, for example, a feature point. You can always find a feature point in different views. So therefore, we propose to use like edges because edges is also sort of consistent in different views. If you have perfect detection detection algorithm, you can always see this line. So we want to find this kind of ground edge to represent these walls. And so we first use some like segmentation to generate some proposals of these planes, which are likely to be wall plane. And then we will select, then with these many proposals of object in the plane, we will jointly optimize to select the best one. And so the way we select them is from like a CRF optimization. Basically, we want to find the planes and objects with some, for example, the unitary energy and also the pairwise energy. We don't want them to intersect with each other. We want the object plane to match the segmentation and so on. So with this kind of optimization, we are able to select the proposals that best fit from the image. And we also show that, okay, this kind of joint reasoning improves the 3D detection on the image, because if you only predict from image, detect 3D object from image, with plane, you will have more constraints. For example, this object should lie inside the room, right? Should not go outside the room. So with this kind of constraint, it's able to improve the 3D detection. And then with after finishing the single image part, so the single image part is basically just outputting the 3 object and plane position. And with this result, I will plug this into the second part, which is the SLAM optimization part. So the SLAM optimization part is essentially like factor graph optimization, and we define the vertices of the variable to optimize, for example, camera points and planes and so on. And for camera and points, we have used a lot. And here I explain the planes and cuboids. So planes we represent as an infinite plane without boundary, just infinite plane. So it has 3 degree of freedom. And also for cuboid, we just mentioned before, it could be represented by a cuboid, 6 DLF for pose and 3 DLF for size. But actually for some applications, for example, for a car, you could also fix the size. So then just use a pose for it. And for the optimization, I explained the measurement. Actually, some of them already explained in the literature review part. So we adopt 2 measurements in our system. One is a 3D measurement, exactly the same as mentioned before. You measure the object a pose from each camera view. And then is the 2D detection. We project the cuboids onto the image and you compare with the 2D bounding box. Generally, we prefer to use a 2D measurement because it's more robust, and because 2D detection is generally more robust compared to your 3D. And similarly for plane, remember that our plane is generated from the ground lines. So the measurement we get is you store your line in your system. Then every time you want to compute an arrow, you unproject it onto the ground and then compute a plane and compare with your current plane position. And actually, we also have some other kind of semantic and more intuitive measurement. For example, the objects should not be occluded by nearby planes. And also, if planes belongs to an object, I mean, basically in the bounding box of the object, it should also lie inside the 3D space of the cuboid, and so on with this kind of constraint. So I think the final part of the SLAM system is data association. Basically, you want to find the object. You want to associate this object in different frames. And from my experience, I find that a good way to solve this is based on the shared point features, because we already find association between an object and a point. So then with point, we have this kind of good feature checking, like epipolar checking for the feature point detection. Then we can also find object association based on this. From our experience, this works pretty well for clutter and repetitive occlusion, this kind of objects compared to the standard like object tracking and the template matching. Okay, now we finally come to some result videos. So this video shows the object SLAM in different environments. Since the algorithm doesn't require a prior object model, so we can easily test the algorithm in different data sets. So with this, this is the QT sequence. And then, so at the end, there's almost no scale drift. And also, since during this process, we don't have any loop closure, and also we don't have a ground, we don't have a height assumption, like camera has a fixed height to the ground. We only use the fixed object size assumption. And in the second video, it's actually very challenging because it has very few feature points. If you just use standard like OpSLAM or this kind of visual point SLAM, it's likely to fail. And this video shows that how object and the points are. For example, if we detect that this point belongs to an object, then in the optimization, it should also lie inside this cuboid. And in the last video, it actually shows that, actually in the last video, we can find the object and object position is actually not very good because they are supposed to be parallel to the nearby wall. So that's why we later add the object and the plane in our system and to better refine it. So here are just more quantitative results. And for all the quantitative results, we have the two parts. One is the evaluation of the 3D object detection, like basically 3D intersection of union, IOU. And we also evaluate the camera pose accuracy. So here we show that it improves both the detection accuracy and compared to single image detection, and also improves the camera pose estimation compared to other SLAM, especially in more challenging environments. In the bottom right, we show some 3D, sorry. In the bottom right, we show some 3D object map visualization. Actually, we only optimize only the cuboid is optimized in the SLAM system, and the mesh model is only for visualization here. And similarly, on the KD object sequence, we evaluate two parts. And the visualization of all this car position and orientation are showing on the bottom image. Basically, there's very few, very small drift at the end. And also on a standard KD odometry benchmark, which many SLAM algorithms has evaluated on this. And we show that it's better than other molecular SLAM algorithms, which typically use a constant ground height-based approach. Basically, it assumes the camera is fixed height, fixed offset compared to the ground. But this kind of approach actually, where this kind of ground scaling approach sometimes it's not robust because the ground may be invisible. For example, in this kind of in the image shown now, the ground is not easy to detect because there's very few feature points on the ground now, and but for we also know that like for object it may also not be robust because you may not see object for some time. So then we combine them together. I mean, get the best accuracy at that time. And here are the more result. Okay. And this video is a joint object and the plane estimation. So we can see that the object orientation are better aligned with the wall because we have this kind of constraints in the camera, in the optimization system. And actually the dense map is actually just the post-processing. We back project the pixels onto the plane to get the dense map. And I would say that planes are especially suitable for this kind of indoor environments. For example, this kind of long corridor environments, because you can observe a plane for a long time so that it can provide you better constraints for your camera system. So especially when you come back to your same position, even without explicit loop closure, image-based loop closure, you are still able to associate back the planes. And here are more result examples from different scenarios. For example, corridors and rooms, and also with objects. And also like different viewpoints, because in some of the data, in some of the sequence, the camera viewpoint changes a lot. It's not just always like looking forward. And the table also shows improvement of existing methods because due to the new constraints from objects and planes. And so last part, I will talk about the dynamic scenarios. As we know that most of the existing SLAM algorithms assume the environment to be static. Then it discards the features from the dynamic scenario. However, this may not be applied for the very highly dynamic environments. So we still want to utilize this kind of the dynamic features. So but from human perspective, we can also observe that this movement actually comes from the dynamic objects. So instead of random pixel movement. So therefore, the object is actually an ideal representation to solve this problem. But we need to have some reasonable assumption, for example, position and rigid body position, a rigid body assumption, and also a motion model. So then we will come up with more complicated graph, which you need to because we need to estimate the camera posing each object posing each frame, and also have velocity estimation. And this video shows the result that it can estimate both the ego motion and also the nearby dynamic objects. So lastly,
to achieve this, Live Maps uses machine perception to construct multi-layer representations.
So lastly, I will show some result in the related work in Facebook Reality Lab. So we are aiming to, I will briefly talk some related work here because actually I just want to clarify that all information here are already public online, so you can see it online. And tomorrow, actually, Jakob and Engel will also, in the same team as me, will give a more complete picture of what we do in Facebook Reality Lab relating to SLAM problems. We aim to build a map that contains both low-level geometry information and also high-level structure, semantic, and object dynamic information. And with this framework, we hope to share the AR content to others in building scale or city and or even planet scale. And we have built the state-of-art geometric SLAM here. But in today's talk, I will list 2 examples that more closely relate to the semantic 3D reconstruction side. So one is the first one is a dense and photometric realistic dataset called Replica. So this kind of dataset can be used for your machine learning and object detection and even SLAM research. It's already online now. So the last one is also this year's CVPR, and it's called Frodo. And as mentioned in the introduction, it uses like a shape encoder vector to represent objects. So it's not the same as our object, because using this kind of encoder actually generalize well to more diverse objects. And also it can has a dense representation, for example, a shape, a point cloud or mesh model. But in their system, the camera pose is actually decoupled from your object mapping part. The camera pose is fixed during optimization. Yeah, so just a brief summary of today's presentation. The first part is a survey of different algorithms of object SLAM, including whether they are coupled or decoupled, and also different object representation and the cost function and optimization approach. Then I present my previous work of like, for example, efficient and generic single image direct 3D detection, and also joint object plane inference, and then extend them to object plane SLAM in both static and dynamic environments. So there are still more challenges to solve. For example, how do we get more dense and realistic reconstruction from images? Because that's more useful from user perspective. And also, how to deal with more general like cluttered objects and planes. For example, there are many objects on the table. And also like for new objects, and also like more high-level reasoning about property and concurrence about these objects. Because this might be useful for some other tasks. Yeah, that's the end of today's my talk, and I'm happy to answer more questions.
Okay, thank you, Dr. Yang, and for your great talk. And we have several questions from the audience. The first question would be a general question. So what are the major handles that prevent AR or MR, mixed reality, augmented reality devices from being used widely today? And I guess this question is asked because you are working in a Facebook reality lab.
Yeah, you mean what are the blockers, right?
Right, yeah.
Okay, I think right now I don't see many devices which has already shared this kind of dynamic and objects representation in their product, because most of them are still using just geometric SLAM to give a pose. And I think the key challenge is how to make it. One is no computation, but because we don't want if we use like deep learning to predict this kind of to do many predictions, how do we make sure it's low computation? And the other thing is how to make it more robust, like how to generate, for example, how to adapt it to more diverse object. And we have in Facebook, we are aiming to do that, but we haven't really integrated into the actual products which is on the market yet. Yeah.
Okay. Another question. So for object and the planar information, would that information help in the loop closure?
Yeah, sure. That's definitely, because as I mentioned in the beginning, right? So the like long-term live localization, like lifelong localization, I think that's a very challenging problem. So at that time, if we only use point or point descriptor, it's very difficult to generalize to different views, right? For example, descriptor may change when it's, for example, from like sunlight to at night. So then, but using object and the planes, I think it's more easy to generate, to get this to recognize different scenes. For example, there's already like some, I think, global descriptor which capture the overall layout. But I think using objects or planes, I think is more, I mean, I think from my perspective, it's easier to debug, okay, what is actually recognized in different scenes, right? For example, if it is a unique object, people may, if people see it like at first glance, we will recognize, okay, it's in this position, right? So then I think this kind of object is a good object, and the plane is a good way to for this kind of lifelong localization.
Yeah, I believe so, because even for points, that is more confusion compared with planes and lines. And I believe using lines and planes could help in resolving the loop closure problem. Okay, and one more question is, have you fused MU to improve object plane SLAM?
Yeah, just for my today's presentation, I didn't use IMU. I think this is a very good question, because I think IMUs can definitely improve your object detection. For example, just for my problem, if we want to detect the objects in different view, for example, if your camera are not are pointing differently compared to the ground, I think I have IMU orientation can give you definitely better detections. And even in the, I mean, of course, in the SLAM part, there have been many people of the visual inertial stuff. But even for object detection, I think it can also improve the detection.
Okay, one more question from the audience. In slide 6, and are the mesh and the voxel grids considered as accurate prior models?
Wait, sorry, let me.
Slide 6.
6, let me.
Yeah.
Okay, so what's the question?
So the meshes and the voxel grids considered to be accurate prior?
Accurate voxel.
Prior. Yeah, voxel and the mesh.
Oh, okay, voxel and mesh. Yeah, for say from my literature review, the point cloud model and this kind of CAD model can directly be used for to align with the image, but they need to have for example have a color for it so that we can directly align with the image, and also it has to be exactly aligned with your object. If they are different, then it will be much difficult to align them. And also for mesh and for meshes, there's also as I said in the later, right, you can optimize the silhouette, this kind of error, so it can also align to some extent because if you optimize them perfectly. So that's what I said. So if you are sure that the actual object is the same as your prior model, then you can directly align them, right, based on the edges and image or even pixels. If you don't have it, then you have to for example, use this kind of shape encoder, which can allow you to adjust the match. For example, you change some encoder, then the match format, match shape will change. Then this allows you to better align with your object. But in my case, just for my work, I didn't use any this kind of meshes. I just use a general cuboid to represent it.
Okay. We have a question. We have time for the last question, and for the when you get the 3D bounding boxes, the 3D proposals, and I assume you are using you have some prior assumption that the object has parallel lines, and in this case, they can generate the vanishing point so that you can generate the proposals and finally score the proposals. So have you tried with different shapes? For example, you are using chair, and sometimes you are using computer boxes, and sometimes you are using cars. And I used to solve one of your result is from the round table. And have you tested for different shapes of the objects? And how does this 3D proposal generation differ?
Yeah, that's a good question. I think that's a many drawback of the 3D detection. The reason why I propose that is to generalize it to general environment without shape model, but it also has drawback. For example, even you can, the proposal you generate are pretty, even you generate many good proposals, but if you cannot score them, for example, they don't have the object is like cylinder, it doesn't have very good, very clear edge, and even for the car, they don't have very strong edge because most of the surface are it's not like a plane surface. So as I said, it will have some problem for those cases. But I mean, since I later used the planes, the SLAM optimization to also to adjust, to fuse their positions from different views. So at that time, I think the position should be easily constrained from your multi-view observation, but the orientation is definitely is difficult. For example, you have car. If your object is cylinder, then we should not use the object to represent the cylinder, right? So at that time, the orientation will have some issue, but you cannot figure it out from your SLAM system. But I think the position can still be constrained in your later SLAM problems. And yeah, that's what because the main goal of my project is to have a better 3D, better like object SLAM and object mapping results. So sometimes, yeah, for the single image part, it may not work perfectly well for some cases. Yeah.
Okay, that's fair enough. Thank you very much, Dr. Yang. And I think there are more questions from the audience, and you can interact with the audience on YouTube channel. And let's thank Dr. Yang again. And so representing about 200 people, 200 audience. Okay, the next speaker is Dr. Kristen Grauman. I think Dr. Kristen Grauman is here. I can see her.
Yes, I'm here. Hello.
Okay. It's my great pleasure to introduce Dr. Kristen Grauman. And Dr. Grauman is a professor in UT Austin and a research scientist in Facebook AI research. And her research on visual recognition and search is well known within the community, and especially for the work of pyramid mesh kernel, hashing algorithm for large-scale image retrieval, relative visual attributes, which has won Computer Vision Test of Time Award, CVPR Best Student Paper Award, and the MAR Prize. Her incredible research has been recognized by many other awards, like Microsoft Research New Faculty Fellow and the NSF Career Award, ONR Young Investigator Award, and the Presidential Early Career Award, Hami Young Investigator Award, and the Ichikai Computer and Thought Award. And she is also IEEE Fellow, IEEE Fellow, and Stallone Fellow. One special award, UT Academy of Distinguished Teachers, recognized her outstanding teaching effort. Even myself was influenced by her teaching in a very intensive one-week class that raised my interest in computer vision back to almost 10 years ago. And even right now, when I teach computer vision classes, for some concepts I don't know how to explain, I go back to see the slides that Kristen explains that. I believe many of the audience here will benefit from her talk today, like me. So I will let Kristen begin her talk. Thank you.
Hi, I'm Kristen Grauman. I'll be talking about audiovisual navigation. And this is a project that's done with a number of collaborators that you see here from Facebook AI Research, Facebook Reality Labs, and UT Austin. So to set the stage, we are thinking of problems with embodied agents that are learning how to move around even in unmapped spaces. So we want agents that can, for example, enter a new Airbnb and just by the looks of what it sees from an RGB image, start to have intelligent motion decisions about where to go in order to answer questions like, where would a telephone likely be? Where do you think the TV sits? Or how could I get to a given displacement within this environment, given that it's unmapped? And we've seen a lot of very exciting work in the community happening around this challenge. Problems like visual navigation and visual exploration, where you can have systems learning from the bottom up, even how to map the space and how to encode not just where things are, but also semantics that help an agent intelligently move. Now, at the same time, there's a salient missing ingredient for these agents. They live in silent environments and they are deaf. And so this is the thing that I want to zero in on in this work, looking at how to instead consider the world as an audiovisual place for our agents, and in particular in the context of navigation. So why do we want to do this? What will sound inform our agents about? There are a number of different important things that we can expect. One, it will allow an agent to hear something that is itself the target. For example, the phone ringing in another room, or the baby crying, or some window breaking. This is something the agent should be able to move to even though it can't see it yet. There's also possibilities for safety, like places that should be avoided based on the sounds that are coming from them, or other dynamic object occurrences. Furthermore, we have semantics in sound. If the agent at the bottom of this scene were to hear water running from a given direction, that's a sign about what possible objects or scenes or rooms might be there. And finally, sound gives us information about geometry and materials. So knowing what we can hear and understanding the link to spatial characteristics of the environment gives us a richer perception in for this audiovisual observation. So I'm going to touch on a few of these cases in this talk today, and starting with the one of audio goal. This is where, say, there's the phone ringing in another room and the agent needs to navigate to it. And what's really important to notice about this challenge is that the audio is going to allow us to sense the target before we can actually see it. For example, here on the right, if the phone is near that couch and the agent is down outside of both of those rooms, but can sense the sound intensity coming and bleeding through the doorway, this will be a signal that we should be able to learn to send the agent to the proper place. Now, this is the first time to our knowledge that this problem has been tackled for agents working in photorealistic environments with 3D settings and real sound. So to do this, we first needed to establish an audio simulation platform. We want to be able to hear proper sounds for our agent as a function of the geometry and materials of the environment. So to do this, we started with the publicly available replica environments, like one that you see here, and we used an audio ray tracing approach in order to render and pre-compute the sounds for all parts of this environment. In particular, you store the room impulse response for every source and receiver coupling of locations. And that's what these yellow positions are here in this environment, places at which there would be room impulse responses measured. Now this RIR is the transfer function saying how sound is transferred from the source to the receiver as a function of the geometry, as a function of their relative separation, and a function of the materials in the space. Now, once we have these functions, we can convolve with the appropriate one in order to hear the agent's sound at any given position for any given source. So for example, here, if the source was at that red hotspot, then the agent would receive the appropriate binaural sound when we pull it from the given receiver location anywhere else. Okay, so this is a general rendering of the sounds now computed for all. Now let's look at the task. Here I'm going to play a video and we're going to hear the sound and see what the agent sees on the left-hand view. The top-down map in the center, not available to the agent, but it will start to discover it as it moves. There's a phone ringing, it's coming from another room, and the agent's job is to go find it. And you can see as the trajectory goes that the agent could tell as it exited that first room that it wasn't in that direction. And then as it moves down closer, it'll start to hear that the phone is getting louder, and furthermore that it's coming from the left side. Now keep in mind, to hear this, you'd need to listen to our original video with headphones. And so then it approaches the target and it reaches it and stops. This is the task of audiovisual navigation: find the sound source and use both sight and sound to navigate to it. So the first model that we propose to tackle this problem takes a reinforcement learning-based approach in which we'll learn a policy for how the agent needs to move given what it's hearing and seeing from these multimodal inputs. And this framework is very much related to others that are now common for treating purely visual navigation. And it looks like this. So we have as input the visual stream, and then we also have, in our case, this audio stream, which is coming as input in terms of two spectrograms, one for the left ear, one for the right ear, and optionally, there will be GPS sensing. Now, the multimodal inputs are aggregated over time with this sequential model, and we use an actor-critic approach for learning this policy in order to generate actions that the agent will take. And these are actions in the space of move forward, turn left, turn right, stop. Okay, and having sampled an action, then this loops back because the environment changes, the agent sees and hears something different as a function of its movement. And what it'll learn is, well, by us rewarding it for navigating quickly to the target, it will learn a policy to use all these cues in order to find this sounding object. Now, importantly, we consider both the case with all three of these modalities, as well as the case where, in fact, the task is simply audio goal, meaning there's no pointer at the onset, like in the so-called point goal task, telling us where the target is. And I'll come back to that in the results. So first, let's look at what the audio features learned within this model have captured. These are T-SNE plots showing projections in 2D down from the CNN encodings that were learned for those spectrograms. And on the left, they're color-coded according to the distance to goal, and on the right, they're color-coded according to the angle to goal, which of course is not directly known by the agent, but what we see here is that, as exhibited by the clustering of similar colors, meaning similar distances or angles in these plots, that the features learned have managed to capture this automatically. Now, what about actually executing on some episodes of navigation? Here, I'll first show you an example, and then we'll look at some numbers. So here is a baseline. This is a point goal agent that does not have a sound and is trying to navigate to the target, which is yellow on the bottom of the screen, using just vision as well as GPS. And what happened in this particular case is, though, while there is a shortest path there in pink that would require going outside the door and then around to the other room, the agent ran out of time in this episode, kind of stumbling around at that bottom mid-wall. And that's because the point goal signal from the onset was telling it very strongly to go in that direction to get to the yellow target. And this will give you the kind of success rates you see here. This is the success rate normalized by path length, or FPL, the common metric for navigation, and higher is better. Now, if instead we use our agent and treat this as the audio point goal problem, where we do get that pointer towards the goal in this case, but we also can hear that sounding target, we get a much closer path to the shortest path. And the numbers as well go up significantly. So this is great news, as we would hope once we are incorporating audio into the framework as part of the sensing to find this goal, the accuracy of the navigation is much better. The next thing I want to show you, we think is even more than that. So here, when we treat this task of point goal or audio point goal, we're saying that at the onset, the agent has a vector telling it where is the goal. And this is very commonly the way the task is posed in the navigation literature today. However, we also know that having that information is extra, right? And furthermore, if we rely so much on that information to get us there in combination with a GPS sensor, we'll be in trouble if the GPS is not perfect. And so what this chart does is look at success rate on the vertical axis as a function of adding more and more noise to the GPS sensing. And first of all, what you see here is the good news that because our agent with audio can still hear even in the presence of noisier GPS, its accuracy rate stays relatively stable as that GPS gets noisier. So this is important. Furthermore, if we think about the task, which is audio goal, meaning we do not get that displacement vector at the onset telling us where is the goal, then in this different task, we can still be completely immune to any problems with GPS. In fact, we're not using it, right? So the agent is able to find its way to the goal at a steady accuracy rate without needing this direct pointer to it. And I think this is an important suggestion about where audio can play a role for this real-world task of moving towards sounding objects. And by the way, even if we do add noise to the audio stream, we're seeing relative robustness to that. Now, in every case, the environment that the agent sees during navigation is new. Now, we're also interested in seeing what happens if the sounds are new. So this is a set of experiments where from left to right, we made more and more challenging sounds in terms of whether the agent had heard them during training or not. And the short story is that if GPS is also available, the performance is quite stable with respect to unheard sounds. If it's not, it does get more challenging. And I think we can improve these quite a bit once we're training on a much wider array of sounds. Now, the model doesn't always work, of course, and some of the failures we noticed are things like you see here, where the agent may start oscillating around an obstacle or choose a path that is kind of a long way around it. And we can attribute this to a couple things about the current model. One, this action space is very step-by-step, and so there's a lack of abstraction or sort of myopic choices are being made. That's hard to do in a very long string of actions. And secondly, we have a memory that's rather simplistic so far, simply aggregating state through this GRU. So, in our next steps in this research, we've looked at how to overcome these limitations and really enhance the model that we're putting forth to do audiovisual navigation. And there's two important things in this new model. So in this picture, on the right-hand side, you can see occupancy map, acoustic map. Now these are new grounded spatial representations that we add to the model beyond what I was showing before, which is the egocentric view in RGB or the binaural audio spectrograms. And this will give us a multimodal spatial memory in which we record as the agent moves in this space, both where obstacles are in its occupancy map, but also the history of what it's heard as it was moving in different positions, what we call the acoustic map. So that's the one key new ingredient that we want to explore. And the other that we propose is audiovisual waypoints. So we'll make this architecture more modular so that we're not confined to these step-by-step actions of the agent as before, but instead the agent can set for itself waypoints that it should travel to with, in our case then, a planner to get to each intermediate point. Okay, so we're going to learn audiovisual waypoints, and we're going to incorporate an acoustic memory to make this model much richer. So let me show you what the model looks like then. Now we have as input the RGBD, so here we'll take the depth image, project down to the ground plane so that as we accumulate these observations from the egocentric view, we get more and more of the occupancy map filled in. Secondly, we have the audio input, and now rather than only using those raw spectrograms for learning that you see on the left, we'll also have this spatially grounded acoustic map, which in this case is encoding the audio intensity at the egocentric positions and accumulating those over time in concert with the occupancy map. Then we'll have this important module which does the audiovisual waypoint prediction. And so now this policy is generating the waypoint. Okay, so given the maps that it's discovered so far, as well as the raw visual and audio inputs, it will select for itself a sub-goal. And if intuitively, as some of my images before showed, audio is strong as a sub-goal creator because, again, before we get to see something, we can hear it coming from certain directions, which suggests the kind of intermediate goals that might be useful to set. So in fact, we're going to learn to set these goals end-to-end within the navigation policy itself, or for the navigation task. And so having selected a waypoint, then the inner module of the system will plan a path given the partial map that's been reconstructed so far by the agent in order to meet and find that waypoint. Then the environment will update and the agent will see something new, hear something new, and this process continues. So the key new ideas in terms of the technical approach here is first that we're inferring sub-goals via the policy. And we think that this is new with or without the context of audio-visual. Traditionally, sub-goals are set in this navigation space based on intersecting the intended goal with the frontier of exploration, or by learning to map to shortest path waypoints. And instead, we're letting the policy learn to set these goals. And then the second key idea is the acoustic memory. Right, so let's look at what this, how this looks and sounds for an agent now, exploring another space. And when I play this, again, the goal is in the red, the agent's this blue arrow, and as we go, it'll set waypoints for itself in yellow, and the purple will illustrate the acoustic memory. So let's play this example. So it's starting to record its audio history in the acoustic memory. The yellow is the waypoint that it's setting for itself next. Phone is getting louder, the new waypoint set near that doorway. Enter the correct room, it's louder, the waypoints are getting closer. then once the waypoint gives back a delta x, delta y that's 0, 0, the agent will know it has reached, believe it has reached the goal, and will issue the stop action. So this was just one sample showing the agent at work, leveraging this grounded, spatially grounded acoustic memory together with this ability to set waypoints on its own directly in concert with this navigation task. And we found quite good results when doing this. So here I'm reporting results on those same replica environments from before. And here are an array of metrics. SPL is the first column there. The others are success rate, normalized distance to goal, the number of actions, and the success rate weighted by the number of actions. And our result for a full model is shown here, highlighted in yellow, whereas the model of the previous version of our method that I described earlier is shown here in blue. You can see right away these new additions of automatically learned waypoints as well as the richer acoustic memory are responsible for a big jump in the success rate and the SPL. Furthermore, there's also some concurrent work coming at ICRA 2020 from Gan and colleagues, where the audio and the visual streams are treated separately, and the audio gives a beacon from which to predict the final goal location, and then the visual stream is used to navigate and plan to it. And we're seeing good results with respect to both these existing methods. Furthermore, you can see the impact of the acoustic memory in the ablation on the bottom, where the model here, ours AV WAN, without the acoustic map, AT, loses about 4 points in SPL. Now, to give a qualitative sense of what these agents are doing, the three I was highlighting on the previous slide, we can see example trajectories here. Now, remember that each of these agents has no pointer to the goal. They do have clean odometry, but there's no pointer given to know where the goal is. And we see on the left, with Jana and colleagues' approach, there's quite a challenge because the method requires predicting where the final goal location is based on audio and then navigating to it with the visual map. But this, because of the difficulty of finding that final goal prediction correctly, there's a lot of backtracking. In the middle, our previous model with pure RL and the step-by-step actions is better, but still doing some unnecessary motions thanks to that more myopic view of the action space. And then finally, the current model I just described with waypoints is getting a much more efficient path on the right. All right, so I've been talking about this problem of audiovisual navigation with a target location, the ringing phone. And now I want to shift to an example from our work, trying to tackle the use of audio in a 3D space for semantics and geometry. And for this, we'll introduce our work on visual echoes. This is work done with the people that you see here, led by Rohan Gao. Now, we've been looking so far thinking about audio as something the agent hears from a distance. You know, there's some sounding object and it experiences it. Now I want to shift to the flip side where the agent itself is emitting a sound in order to learn about the surrounding environment. So what will happen is the agent's going to emit a sound, and when it does so, then the environment will bring sounds back to it in terms of the echoes. And this is what we want our agent to exploit in order to learn about the geometry of the space. Where are the major surfaces? How are they oriented? Okay, so this is the main idea, and what we're headed towards is a new self-supervised image feature learning approach that is trained based on how an agent can learn the connection between what it sees and what it hears from echoes. So we'll return to the simulator that I described from our work earlier today. And in this now, we'll let the source and the receiver be at the same position. So the agent is somewhere in this environment and it emits a sound and also listens to the response at that position. And we'll emit a sweep of frequencies in order to get a rich response from the environment. Furthermore, we record these echoes from the agent's point of view. It moves in a few different orientations. So here we're looking on the left at a top-down view of an apartment. The agent is at that crosshair arrows. And if it looks in a certain direction, say forward, it will see the RGB in depth and receive an accompanying set of echoes, one spectrogram for the left and right ear. And similarly, as it rotates to different orientations at the same position, it will see something different and will receive these different echoes. Okay, so imagine capturing these kind of paired data between the audio and the visual anywhere in this environment. Now, before I get to the self-supervised feature learning, let me show you first a case study we did to see how much power rests within these echoes. And the idea is, first, can we predict from the echo response alone the depth map for the agent's egocentric view? Call this echo to depth. Furthermore, how would this compare if we were to instead learn a similar model for RGB to depth, which is the traditional way one would tackle monocular depth estimation? And finally, if we put these together, can we augment monocular depth estimation by using echoes? Okay, and we looked at these three models. Here I'm showing you just two examples of what you get if you try to do this prediction from RGB echo or RGB and echo to the depth map. And the ground truth you'll see is in that second column. Now, we do see that, yes, from echoes alone, there is a signal about the shape of the scene around this agent. Okay, and you can see that compared to the ground truth, it's certainly blurrier and less complete, but it's getting the main shapes of the space, which is what we expect to get from emitting sound and listening for the echoes. Furthermore, doing so with both RGB and echoes is stronger, measurably so, than using RGB alone. And in this example, gives you a hint of why, because here in the back of the room in the top left scene, there's a strong texture change from this slight lifted part of the back wall, and the RGB alone sees that as a strong depth change, whereas the RGB plus echo sees this more correctly as smooth, thanks to the complementary information from the sound. Now we've tested this on data, quantified all of the above, and we do see that, as you might expect, bringing both these modalities together is stronger for depth estimation. However, that's not our endpoint. That's just to see, what's this data holding for us for learning. The real idea here that we call visual echoes is to learn a visual representation that is aided by the sounds and echoes experienced during training only. And in particular, the objective we put forward for learning this is to require the visual representation to capture whether the sensed echoes and RGB view were congruent or not. So it looks like this. The agent has the RGB input. We'll learn a visual echo net for those visual features. The agent also has the echo response experienced with binaural sound from the left and right ears. But here, during training, the echoes that are received are going to be aligned with the visual stream or not. And if they are aligned, they'll be in the same orientation as the agent's current view. But if they're not, there'll be an echo that the agent would have heard had it been turned 90 degrees to the right, behind, or to the left. And so the self-supervisable task here is for the agent to learn whether the thing it's seeing is aligned in space with the thing it's hearing. And that we can cast as a four-way classification task to the directions you see on the right. Okay. So why would this be a good task for the agent to self-supervise? The idea is that if the agent is able to look at just RGB and get from the RGB whether the sound is in agreement with the shape of the scene, it means it's forced to pull out those elements of the shape of the scene, like the relative depth, in order to see if that agreement is present or not. Okay, so we take the visual model here, the visual echo net, as the visual encoder. So again, I'd stress that now at test time, we want to encode a new image, but we have no audio. And that this is where we leverage what was learned with audio now to handle images that don't. And just to give you an example, an NYU data set for depth estimation, here we're applying the model I just described using a state-of-the-art framework where we replace the backbone model with our pre-trained visual echoes net. And we get results like the ones you're seeing here that are much better than those you can get just learning from scratch with the same exact model. So that shows you transfer then from replica, the synthetic environment in which we learned, to real-world images in which this visual echo features is having a good impact. And furthermore, we've done this not just for monocular depth prediction, but also for other downstream tasks that can benefit from this pre-trained spatial encoding, like surface normal estimation and visual navigation. And in these cases, what we're seeing is that we're competitive or even better than the supervised, heavily supervised ImageNet or MIT indoor scene pre-trained models. Okay, so for the last few minutes of this talk, I'm going to shift gears from audiovisual navigation to tell you a preview about our new work on occupancy anticipation, which is for visual navigation. Here's the motivation. So in current state-of-the-art models for visual navigation, there you will often find, just as you saw in the model earlier in this talk, an occupancy map that encodes the spatial representation of where obstacles are on the ground for this agent. So it can start to build up a map of the environment and then plan through it. Now, the limitation that we see in these models is that the assumption is that the occupancy represented will be limited to those regions that were visibly detected. In other words, it's very literal. You see the depth map, you project it to the ground, and those are the places at which you know there are obstacles. Our key idea is to rethink this assumption and attempt to anticipate occupancy even in unseen regions. So if we have an agent like this one looking at the RGB ecocentric view shown in the center, as well as the depth shown just to the right, rather than restrict its map from that snapshot to only what would be visible from that depth map in the middle, we want to extrapolate and anticipate portions of the map that are predictable given the semantics in the RGB view, as well as the prior over how these occupancy maps are typically laid out. And this, if done well, will very much map what the ground truth occupancy would be, even though we haven't seen from the egocentric view all parts of that map. Now, why should this work? Well, this example gives you some intuitive sense. In this particular view, if you look at the RGB picture, there is a clear floor, wood floor, a corner of it visible, which suggests that more of the space in front of the agent may also be free space. Furthermore, just to the left, there's a hint of a hallway, and so that could allow, based on some learned prior, to anticipate that there is a hallway extending from it. And finally, seeing the wall just to the right of the agent may suggest that that wall is likely to continue, at least for some distance to the right. And these are exactly the kind of things we learn. I'm not going into details of the framework in this talk for time, but we have a model to learn how to predict these anticipated occupancy maps, and then we inject it in two ways. First, within the model to extrapolate the encoding of the current map, and second, as a reward to the agent during exploration, in which we give reward for moving to places in the unmapped environment at which the agent is able to achieve greater anticipation. You can think of this as a new way to get better coverage, where coverage is not limited to being able to see more, but it's saying coverage such that you are able to anticipate more. And in the end, this could allow to a more frugal use of the agent motion to get a fuller map. And we can see this happening in these qualitative examples for instantaneous occupancy maps that are predicted, with a baseline being the state-of-the-art active neural SLAM approach, ANS, which is limited to the visible occupancy map, and then you see our approach, occupancy anticipation, towards the right there. So we're getting fuller maps, and if we put this into play with the navigation policy itself, we'll see here in the center what the map looks like restricted to the visible map, or the current approach, and with our anticipated map on the right. For example, in that dining room, it could anticipate that the space behind the table was free and make the map fuller as a result. Similarly, in this example, the agent keeps navigating and sees just portions of the scene that hint at what probably other nearby portions are like, and so it more quickly is mapping it. Okay. We have applied this for exploration, and here are results from Gibson and Matterport 3D, where you're looking at the map accuracy in the vertical axis as a function of episode steps or time. And we can see that the intelligent anticipation that we're proposing leads to more efficient exploration. So better map in less time, and this is compared to both the ANS mapping as well as a view extrapolation baseline. And finally, in the Habitat Challenge this year for the point goal navigation task, the occupancy anticipation is among the top performers. And I'm showing here the final leaderboard for the public-facing site for the test standard set. Okay, so I will close here, and to summarize, this talk was about agents that can see and hear in order to understand their 3D environment. And I showed 3 new technical ideas. The first, we defined the challenge of audio goal as a new navigation challenge, as well as a simulation platform that allows experimenting with it. Second, we introduced a model based on audiovisual waypoints and an acoustic memory within an RL framework to try and address this new task. And third, we introduced an image feature learning called Visual Echoes that self-supervises a spatially informed feature from images alone. And at the closing here, I just gave a teaser about our work on occupancy anticipation, which is a top performer for this year's Habitat Challenge. We'll stop here, and thank you for watching, and I look forward to your comments and questions.
Thank you very much, Professor Grauman. And I believe there are quite a lot of applications based on the visual and audio and application. Because right now you are presenting in the indoor scenes. I believe in outdoor scenes, for example, in the nighttime or something like a hidden objects in the, for example, insects, and we want to identify some objects hidden. That is also pretty helpful for even for the wife. Even for the for the deaf people, and that is very helpful as well. So I have some questions from the audience, and let's say the first question is, does the agent have to constantly hear the sound in order to reach the goal? And what about if some agent responds to a short but acute sound in this case?
So I didn't hear the last part of it. I heard the part about you know, the sound could pause, but could you please repeat the second part of the question?
Oh, sure, yeah. So whether the agent needs to constantly hear the sound in order to reach the goal. And the second question is, how could the agent respond to a short but very acute sound?
Okay, yeah. So you're right. The tests we did are nearly constant sounds, as in every step it would receive a sound. However, experiments I didn't show, we've looked at time varying sounds where, for example, rather than the phone ringing, maybe music's playing. And so what makes that closer to the intermittent sounds is that, you know, intensity will go down and up and the tone will change. So it's not a constant signal. And that is more challenging, but still we found quite well handled once we have the acoustic memory, because it helps to deal with this and create more invariance to those changes over time in the sound. Now, I do think that, yeah, the more briefly we hear the sound, for example, imagine you walk in the door, you hear the short noise, and then you're done with sound. Well, that reduces to kind of having that first snapshot of audio observation, and then from there, needing to rely only on the visual. So, I mean, the model still holds, but certainly it's a scenario that's harder in the sense you're not getting a constant reinforcement of the acoustic signal.
Okay, and the follow-up question would be, you mentioned for GPS, if GPS is available in the indoor environment, that is very good. And but if GPS has noise, that would be good to use the model and the visual audio model. And what about if some audio also has noise? And how to deal with this issue?
Yeah, it's something we're testing too. And I only briefly alluded it with that one result where we saw that the audio goal, you know, was at a certain flat rate. And then if it dipped down maybe 2 points in SPL, this navigation metric, if there was a bad microphone, which was like 40 decibels signal to noise ratio. So again, in the latest model I showed today with like the waypoints and the acoustic memory, those ingredients are important for us handling this noise. And when we look at this as a function of the amount of audio noise, just like I showed you as a function of GPS noise, things are quite steady if we have the acoustic memory. And this is compared to our earlier model as well as that other model I was comparing with from the literature.
Okay. Another question from the audience, and one audience is wondering how you render audio for each location.
Yeah, so the rendering, it's all, in this case, it's all pre-computed, and just for ease of experimentation, which that means is like for every source and receiver location that you would like to be able to hear, you have done this audio ray tracing and collected after some number of bounces of the sounds what reaches the agent ears. And here it's ears as in binaural sound to microphones placed about this separation. And so so I think the question is like how to get it at a different position. You're kind of looking to that room impulse response function and then convolving it with the waveform you want to hear, like the phone or whatever. And now you'll receive that sound. You just need to specify where you want to hear it from and where you are as the agent.
So a follow-up question would be if you are in the, for example, in the indoor environment and you know the material is wall, and what about if some materials there, for example, some material may absorb some more sound and some may reflect more sound. In this case, is there any experiment to show the difference?
Yeah, this is actually captured in the simulation. And by the way, I should say we're making these simulations public so that others can kind of work on them and build on these results. But yeah, the transmission coefficients, et cetera, of the effects of materials on the sound propagation are in this simulator. So we think this is really a state-of-the-art capture of what the audio, to the extent in the simulation it can be achieved, what the audio will be like, respecting both geometry and materials.
Okay, and in general, maybe one more. We have one more time for one more question. And in general, for your audio and the visual work, and I believe quite a lot of time that is very specific. That is something are very good for visual clues. Something are very good for the audio clues, or something is very good for the mixture or giving different weight. Do you have some insight on which scenario we should use which clue to navigate or to do the scene depth estimation?
Right. Yeah, we're starting to get that sense. So we did a study that you could find, I think, in a video on our project page for this that I didn't show here, where we took the trained model with both cues and then start to ablate or corrupt one or the other, and then see the effects on the agent action selection. So you want to know what time points is it using one or both of these signals more heavily to make its own action choice. And you do see some interesting things. It's not just that both are good and contributing. Sometimes visual dominates. You can imagine like if I don't know, if I'm walking forward and it's like a couch that's big enough to trip on, but maybe not big enough to alter the audio response significantly, then the visual would be a stronger decision maker and counterparts for the audio as well. So yeah, we're trying to visualize this. You might, these figures that I referred to on the video might be a way to get a sense of that more fully.
Yeah, do you think it's good to extend to the outdoor environment, which has more noise in the environment, outdoor environment in this case?
Yeah, I think that's a great challenge. Now, if taking our literal approach over there, as far as audio simulation, I believe that's much more difficult because you're in open space and you're not getting these, you don't have the mesh. Maybe you don't have as good of a mesh or as complete as a mesh to get these. But yeah, worth considering whether in simulation or not. And I think definitely the directional cues, think of a self-driving car with the sounds around it, which people certainly want to exploit about, the ambulance coming by or other things. This would be helpful for the visual reasoning too.
Okay, great. Okay, thank you very much, Kristen, Grauman again, and I believe there are quite a lot more questions in the YouTube, and just we are run out of time. So thank you again, and there are about 200 people listen to your talk, and it's just a representation. So thank you. Yeah.
Okay, thank you very much.
Thank you.
Appreciate it. Bye-bye.
Bye. So let's go to the next one. Dr. Shuxue Chen, are you here?
Yes.
Oh, okay, great. Okay. Let me introduce Dr. Shuxue Chen, and Dr. Shuxue Chen is the Senior Director of Research in Computer Vision and Augmented Reality at Oppo US Research Center, where he built and leads the team of developing algorithm of SLIME, scene understanding, 3D reconstruction, human-computer interaction, and computational photography. And his team also built software frameworks and applications to enable AR on mobile devices and head-mounted devices. Before Oppo, he was a principal engineer at Qualcomm and on computer vision and machine learning and mobile cameras, and after a few positions in Sony, Macron, and Broadcom. Dr. Chen received his MS and BS on optical engineering from Beijing Institute of Technology and a PhD in imaging science from Rochester Institute of Technology, as my background image shows. Dr. Chen has granted more than 60 patents and academic papers. From the most recent market review, Oppo is the 4th largest mobile phone company in the world. And remarkably, his team takes the major computer vision research within the company. So he will give us an introduction from the industry research perspective based on his team's research outcome, which may appear in the future Oppo mobile phones very soon. Okay, welcome, Dr. Chen.
Thank you, Dr. Lu, for the introduction. Good afternoon, everyone. Thank the SLAM workshop committee giving me this opportunity to give a talk on building the SLAM system for smartphone and AR glass. So the content of this talk is very different from the previous ones. I focus more on the implementation side on mobile platforms to commercialize SLAM algorithms. So first, I give a brief introduction to my current employer, Oppo. So Oppo is one of the major smartphone makers in the world. It ranked number 2 in China and number 5 in the world in terms of shipment last year. So if you don't know Oppo, you may know more OnePlus. So Oppo is a parent company of OnePlus. So augmented reality, to my knowledge, first described in this paper by Boeing engineers in 1992. So which is elaborated the 3 features of AR. First, the 6 degrees of freedom tracking for head-mounted display. And the second, the real-time and photorealistic fusion of virtual of graphical information and real scene. Third, the interaction with the control software may occur through voice input. Actually, I mean, current days also the hand gesture is also a major input interaction approach. Since then, AR has been an active academic research topic. It also has certain applications in industry these days and also education and the medical area. So AR becomes well-known and popular when Pokemon Go was released in 2016. The interest of AR for consumers was ignited since then. Today, AR picture and the video has been everyday habit for many selfie likers. The history of smartphone AR is listed below. In 2017, because they released announcement of AR Kit and AR Core, it was typically called the beginning of smartphone AR. However, actually in the earlier times, like in 2010, 2012, Qualcomm has the so-called Euphoria SDK. It was still there, becomes a part of the PTC company. And in 2014, Google released the Tiger. It's also for mobile device. And then later, like since AR engine, Oppo AR unit, Snapchat, and so on, and also the so-called real-world AR platform was announced, and it becomes like a very active for consumers. And so in 2017, when the AR Kit was announced, the AR on smartphone becomes slowly becomes popular. So in the table below, the major components of Apple's AR Kit are listed and categorized. The essential components of AR Kit are VIO or visual scan, surface detection, and the light estimation. There are some additional APIs like image detection, tracking, object reconstruction, face tracking, and also for output, display, and the user experience. So the L core on Android, in the table below, the major components of Google's L core are also listed and categorized. So the essential components of L core are motion tracking, environment understanding, and light estimation. So the motion tracking allows the phone to understand and track its position relative to the world. So it's essentially the Y06 stuff. Environmental understanding allows the phone to detect the size and the location of all typical surfaces, horizontal, vertical, and angled surfaces like the ground and so on. Light estimation allows the phone to estimate the environment's current lighting conditions. There are other AR SDKs like the Euphoria I just mentioned, which was part of Qualcomm's AR strategy. Euphoria, and currently it has a cross-platform support on iOS, Android, and Windows. So again, the essential component in Euphoria is a SLAM or VR. The technologies for augmented reality are placed here as icons. You can see like a SLAM, visual inertial navigation, camera calibration, camera eccentrics. Those are for the sensor calibration and the sensor fusion, and then surface estimation, and the nonlinear optimization and bound adjustment are for the post-processing of the visual SLAM. The major SLAM algorithms, other than deep learning based, are put here along the time axis. We have been paying more attention to the orb SLAM and with Moulon due to their published performance and technology details and the availability of the open source code. So here you can see the SLAM as a new concept was proposed in 1986, and in recent years, like with Moulon in 2017 and the DSO direct sparse odometry in 2018, and then in recent years, deep learning based SLAM algorithms are popped out. So this SLAM algorithm was published. It's called Wins Moulon in 2017. The whole process starts with measurement pre-processing with camera at 25 Hertz and IMU at 100 Hertz. This frequency can be higher for some devices. And for camera, there's a feature detection and tracking, and IMU, there's a pre-integration. And then the data was sent for initialization, and then to the local visual inertial odometry with the relocalization, and later the second the backend is global post graph optimization and the map reuse, and after that the output is sent to the motion bound adjustment, and for propagation the output is a camera rate post estimation and IMU rate post estimation. So why need to build our own SLAM algorithm, a SLAM system? As I mentioned, Google's L core is available on many Android devices. So first, we can see like one SLAM system can be applicable to multiple areas. So on the diagram about the SLAM algorithm actually can be applied to XR head-mounted devices, can be applied to also drone, sweeping robotics, and the smartphone. The major difference is the sensors. Like for smartphone, it's a single camera plus IMU. For XR head-mounted display, it's multiple fisheye cameras plus IMU. And the drone is dual cameras plus IMU, and sweeping robotics is mono fisheye eye plus a step motor. So this is Google Air Core and the Qualcomm XR solutions. So on smartphone, Google Air Core supports smartphone, but it does not support air glass. And then Qualcomm's XR, it supports air glass, but does not smartphone. So at Opera, we want to build like a unified SLAM system for both a smartphone and the air glass. So on the right side is the illustration of the key smartphone air components where SLAM or VIO is in the center. So to build a SLAM for smartphone, we need to set up lab to calibrate the sensors and also evaluate algorithm iterations and benchmark it against competitive solutions. So these are actually compared with academic research, we need to have this kind of online performance. The online performance, then the algorithm is tightly coupled with the sensor intrinsic parameters, that is camera and IMU, and also the evaluation of the algorithms. We need to do it with the grounded truth data, and also we have a method to do side-by-side comparison. Also, since we want to run the algorithms on mobile devices like a smartphone or air glass, so the algorithm optimization and the acceleration is very important. So this involves the removal of third-party like a software dependency, like a Boost, OpenCV, and so on. And also we need to take advantage of the hardware acceleration, specifically on smartphone and air glass, like the ARM and near acceleration, DSP, and HVX acceleration. HVX is Qualcomm's Snapdragon hexagon vector accelerator, and then OpenCL, OpenGL, and so on. So the input of the to the SLAM is camera images, IMU, and also could be GPS, time of flight, depth sensor, and the stereo cameras. So here, one of the major difference to evaluate the SLAM algorithms is to, yeah. So this is the initialization for the algorithm to start work. So we, like I just mentioned, we evaluate on real devices instead of evaluate with offline data set. So here we have actually three solutions. The left is running air core on a device on the same device, and the middle is like a previous SLAM solution developed at Opera, and the right is our current solution. So you can see our current solution is very close to air core visually, and somehow the middle solution, that is our previous generation, messed up. So to measure the performance more accurately and repeatable, we use a robot to follow certain predefined paths, and the ground truth data were collected with a Vicon system. So you can see the difference between manual data collection versus data collection by robot. The data collection by robot, it's we can have a repeatable data, and also the motion control, the control in rotation speed, translation speed, and the motion pattern can be programmed. And also the environment is not limited to vacuum. It can be like an outdoor. So this, I think it was just played. So the vacuum system was installed, mounted on the ceilings and surrounding the center, the empty space. So here actually we compare the Opera Iris SLAM system with the air core. Here we have like a square path with normal speed, like a normal working speed. The air core performance and the Iris camera performance are compared side by side on the right two columns, the position arrow and the rotation arrow. The position arrow actually is about the translation, and the rotation arrow is about the accuracy of a rotation. So in this square path, for our solution, the translation is arrow is larger than the L core, and the rotation arrow is slightly smaller than the L core solution. Then with a different path, the circle path still normal motion. Normal motion, we found here the translation on the second to the last column. The translation arrow is also larger than L core. The rotation arrow is also larger, slightly larger, maybe 15%. So this is like another different path. We want to test it out on different paths because it involves different kind of motion and also the rotation. So here, somehow we have better translation accuracy and also rotation accuracy. Somehow the rotation accuracy is much smaller than the L core solution. So above we have some observation, like the regular thing, Iris is roughly equivalent to L core, and L core is more robust than Iris for indoor, and Iris is slightly more robust than L core for outdoor. So this is another path. It's like a 8 shape. So let's see for L core and Iris, the translation arrow is roughly the same. However, in this shape, somehow our Iris solution, the rotation accuracy is worse than L core. It's 1.55 versus 3.43. So this is another path. It's like a long path with back and forth. Then it involves dramatic rotation on the two ends. So here for L core and Iris, the rotation for Iris is better than L core, but the rotation is about 50% worse in terms of the rotation, the angle, the degree of rotation. So this is like a stress test. We still have like this square shape, but then we have like a fast motion, and we turn around and also fast motion. The Iris performance for the translation is kind of much worse than L core, and also the rotation angle is not as good as L core. And also the slow motion is another stress test for slow long distance square motion. the translation error is about the same. No, the translation error is about the same, but the rotation accuracy is worse than air core. So the algorithm is continuously evolving and improving, and also we try to make it work on like AR glass. So at the end of last year, Opera becomes one of the very first major smartphone vendor to announce like AR glass. So on the right side is the sensor components of the AR glass. We have two symmetrical fisheye cameras, and also in the middle there's a top depth camera and also a main RGB camera. So the algorithm, instead of running through the RGB camera plus IMU, we need to run the algorithm to run it with dual fisheye cameras and also plus IMU. The sensor calibration becomes more complex because it's a fisheye camera and it has two cameras, and also we need to make like a time stamping for the two fisheye cameras and also the IMU motion sensor. And the latency of SLAM is critical. The long electron to photon latency will cause dizziness for many wearers. If that's a typical problem for AR's adoption by people. And then because it's like a wearable device, the power consumption is also a top priority. The algorithm optimization and acceleration with available hardware components is very important. And here, actually, we have some solution on Qualcomm's Snapdragon chipset. The SLAM algorithm acceleration can be achieved through two ways. One is use the FastSW library on Neon and the DSP and the HVX. And the second is use the dedicated computer vision processor coupled, which is coupled with the DSP and HVX. Currently, you can see the CVP components, pre-processing and the detection. It is support like a pyramid scaler and a feature descriptor, and then the tracking and the motion processing, optical flow, a feature pointer extraction, and the binary feature descriptor, and the inline descriptor matching, and the NCC, and the classification, nonlinear classifier, low power, high quality image warping, and the depth from stereo, scheduling, and the concurrency handling. So on the right side, actually, is like a typical filter-based 6-off algorithm. The feature detector and tractor, this is the major tasks offloaded to the CVP, and then the extended Kalman filter, which will still be done in computer DSP and optionally in modem DSP, because this part it has to use the floating point computation, and it's so in this slide you can see when the CVP and the DSP are used together to offload all the computations from CPU, and this is the partition of the tasks. Like the pyramid scaler with a 3 levels of pyramid scaler on the CVP, and the feature tracking, basically fast 10 or Hertz corner, and then 3 levels of NCC, and then key point detection, and so on. So these are done on the CVP. The other part is done on the DSP. And from utilizing the CVP, you can see the power savings can be done from purely using only the Neon and the DSP, from 2x power saving to 4x power savings. So it's a lot to reduce the power consumption and on the head-mounted devices. They are devices. So this is when we modify our algorithms to run on opposite L class. And this is the real testing. The engineer is varying class and the algorithm is running on the class. And you can see when the engineer turns at the corner of the square, the shape it changes automatically to follow the path. And here is we put like a virtual log on the L class, and then we can observe this logo is in a fixed location of the word when we moving around the L class. And on the right side, we have created like a solo system to demonstrate this 6-DOF's performance. So you can see the virtual solo system is very stable on the L glass. So conclusions and future work. So at Alpha, we have built a unified SLAM system to support both the smartphone and L glass. The accuracy of the system on the device approximated state of the art, but still on some scenarios it lags behind. We found that the latency and the power consumption is critical for head-mounted devices, and utilize every means of the hardware to accelerate the algorithm and reduce the power consumption. And in the future, to create a more accurate and robust SLAM system, like an AI-based solution may be a better option. With 5G network, the computation can be offloaded to edge computing servers. With this, I concluded my talk. Thank you for your time.
Okay. Thank you, Dr. Quan, for your impressive talk. We have some questions from the audience. One question is how to deploy such a VIO SLAM system when you have low visibility. For example, there is fog or smoke, or there is a low lighting situation.
Yeah, actually, that is a problem. Currently, I think especially for AR glass, it's for indoor application. We assume the lighting is in the reasonable condition. The extreme condition currently it doesn't work, and probably need a lot more research and explore the more computation intensive algorithms.
And a follow-up question is, do you think the SLAM sensor will coverage a set of sensors that will be widely used? So by another saying, what kind of sensor is the most important for the SLAM system in your applications?
Currently, I think both the camera sensor and the IMU are they are equally important, because when the features are not useful for camera sensor, we rely on the IMU to make a SLAM work, and then IMU is not as accurate as a camera sensor when the feature points are reached. So both are important. And in addition, I think we also think like a time of flight depth sensor can be also very useful. It can reduce the like the initialization time and also the improve the accuracy. So these sensors probably there are more and more sensors to be added to the smartphone and the air glass. For example, like the event-based sensor, it theoretically and potentially could be very useful. So we expect more sensors to make the system more robust.
Okay. Another question is for AR glasses and the mobile phone, and would be the SLAM algorithm used for those two different platforms be different based on their sensors or based on their computational power difference? Or what is the difference? What could be there some difference between the AR glass platform and the mobile phone platform in the SLAM system?
We found like the dual fish eye for AR glass. Actually, it can see more features, and it can reduce the initialization time, and it also is more robust because the fish eye can see, like I just mentioned, more features, like a much more larger field of view. So other than that, the later part of the algorithms are actually the same.
Okay, and for mobile phone and AR glasses, what is the most important, the first priority? For example, timing performance and accuracy and memory consumption and power consumption. Which is the first priority you think when you realize a SLAM algorithm on those platforms, and you will consider, for example, compare the timing performance and accuracy and memory and energy, those several different perspectives.
Yeah, currently I think the application for smartphone and the AR glass, they focus differently. Like for smartphone, the gaming could be like a major application, and also like Animoji. Those things are major applications. So they like surface detection, which is like a post-processing of SLAM, is important. However, on AR glass, the gaming currently is not the major application, and the latency, like I mentioned, the latency from electron to photon is critical, because many people has this motion sickness when wearing the AR glass if the response is slow. So I would say on AR glass, the timing is higher priority, and then the power consumption is the second high priority, because when it generates a lot of heat, it creates some hazard for the wearers.
Okay, maybe we have time for the last question. That would be for AR glasses and for mobile phones. And which part? How much is the machine itself to compute, for example, and how much SLAM algorithm, which part of the SLAM algorithm is running on the mobile phones, and I believe quite a lot of SLAM algorithm will run in mobile phone. That would be something like on the mobile phone itself. But for AR glasses, many of the computation task is conducted on the server, and but do you have a number or idea, and how much percentage of the computation task is conducted on the machine itself, and how much is conducted on the server?
Currently, I think for the demos and the applications we work on, most of them are conducted locally. the servers have not been used because the slow connection to the server, like a cloud, will cause the algorithm to not run correctly. We need to run the algorithms in real time for both the phone and the air glass. So in the future, that's what I mentioned. If with a working 5G network, the computation can be offloaded to the servers. Currently, we still expect major computations are done locally, and that's why like a SLAM and even like the hand gesture, they are used for supporting AR applications. So the AR application, we expected to take more resource on GPU and also CPU. So that's why we try to offload SLAM to run on DSP or even the hardware like a CVP.
Yes, that makes sense. That totally makes sense. But I think in the future, there might be some changes, as you mentioned, with the 5G network, and there could be some difference. A quick question is, will those SLAM algorithm you demoed will be soon on the new generation of Oppo phones?
Hope so. Yes.
Okay, great. Thank you very much again, Dr. Chen, and it's an impressive talk. And there will be more questions on the YouTube channel, and you can interact with them. Okay, thank you again.
Yeah, thank you, Dr. Lu. Thank you, everyone.
Yeah, thank you. Okay, we will go to our last keynote talk today. That is from Pierre Moulon. Sorry, yeah.
Yeah.
Is my pronunciation correct?
Yeah. I'm just trying to set my screen.
Okay. Let me introduce Dr. Pierre Moulon. And Dr. Moulon is a principal research scientist at Zero Group. And he has published many influential papers and commonly used libraries, and like OpenMVG. And he's a creator of OpenMVG, which means here MVG means multi-view geometry, which is one of the most widely used open source 3D reconstruction toolbox. Pearson obtained his PhD in computer science from University of Paris East, and he later worked at Autodesk, which is also a 3D reconstruction company, and the Plenty system on large-scale 3D reconstructions. At Zillow, Pierre helped to develop Zillow 3D room 3D home product, which is an immersive real estate visualization tool built around 360-degree imaging. His recent work includes 360 imaging for indoor reconstruction and the implementation of the 360-degree structure from motion and multi-view stereo based on OpenMVG and OpenMVS. He has already developed for those open source framework. And I believe many of you guys have already used Zillow's product when you try to find a room, try to find a apartment or house, and part of those work coming from Dr. Pierre Moulon's research. I would like to welcome Dr. Moulon to give us the talk to introduce his work. Dr. Moulon, you can go ahead. I think you are muted.
Oh, yeah, now it should be working.
Okay, now I can hear you, yes.
Yeah. Do you see my screen?
Yeah.
Yep. Yeah. Hello, everyone. Thank you for your introduction and your invitation to speak at this workshop focused on visual localization and reconstruction. My name is Pierre, and I'm working at Zillow as a scientist. Zillow is a real estate US-based company. I will speak today about the open source project called OpenMVG that I created in 2013 and leverage this opportunity today to speak about OpenMVG in a retrospective mode. So let's go over the agenda first. So first I will speak about the genesis of the project, how it was created, and the context that allowed me to create it. I will then present the OpenMVG project and talk about its flexibility, how to create pipelines. And since we are speaking about retrospective, I will use this unique opportunity to speak about the challenges and opportunities that OpenMVG is facing today, and showcase how the community is using the project. I will then conclude and have the Q&A session. So first, for OpenMVG, all started with a dream that I got from a long time. So the dream was to create an open source project to create a patent-free and permissive library for 3D reconstruction. I want to create a framework to foster academia and industry to collaborate and use the 3D reconstruction technology to just showcase how we can do this. So if we look about the context and the timeline, everything starts into 2008. I was a programmer at this time. I was doing some contribution to an open source project called libmv, and libmv was a library to do match moving, meaning it was to do SLAM for the movie industry. And then I was able to finally do the research and start my PhD in collaboration with Micros and Université Paris-Est. And during this PhD, I was able to really start and build an OpenMVG library. If we look also about the context, I was very lucky because at this time, 2 big libraries came out and were able to allow me to do really OpenMVG in a permissive way. The first project was Ceres Solver to do bundle adjustment, and the second one was to do feature extraction with Akaze with a permissive license. If we look about the context also, many paper was really inspiring for me at this time, and I was able to leverage all the knowledge of those paper to bring new things for the SFM community. And if we look also to the context, we see that there is already some solutions that were able to extract either SIFT features, for example, but it was patented. So like you cannot use this to make a permissive libraries. And Bundler was here also a project that a lot of researchers was using, but this code was released under GPL license, so meaning that you cannot use this with a permissive license. So that's why I created OpenMVG, to have something permissive that anyone can use without restriction. And when I started this dream, I tried to set myself some rules to keep as a motivation for the project and to move forward. First, I defined a mission, try to share knowledge to the community. Then I create a vision to ease reproducibility research and allow our community to use, modify, and play with accurate implementation of the most relevant algorithm of the field. And then I try to use a credo to make things simple and easy to understand and maintain by all of us. So let's say that somehow I want to be in favor of easy learning curve rather than some code that is fast, but that you cannot understand or modify later. How hard could it be to just create a library from scratch to do SFM? So on one side, we can say it's easy because there is a lot of things that you can do with linear formulation. So meaning that you can do triangulation, rotation averaging, essential matrix, fundamental matrix with linear formulation. So it's very easy to code, and somehow SVD is your best friend to do that. But then you realize that by plugging things together, it's not as easy as you thought. And you have to realize that you need to do robust estimation, you need to deal with optimization, you need to deal with minimal solvers to have better speed and accuracy in some geometric configuration. And finally, at the end, you want also to create an API that allow users to just use your code in an easy way, or allow yourself to just plug new stuff later on. And doing those things is not really easy. As you see, it took a lot of iteration. I started OpenMVG in 2013. Now we are at version 1.6. And the project is still active. It's running since a long time. And I just put a sun here to show something that really was a turnover in the project and really empowers the project today. I'm going to speak about that later on. As you can guess, getting from version 0.1 to version 1.6 was quite a lot of work. you can see here a lot of non-exhaustive list of papers that have been implemented in OpenMVG. For your information, the bold papers are the contribution I brought to the community during my PhD. So you can see that we implemented a lot of things related to minimal solvers, triangulation, robust estimation, global structure for motion, and tracking. If I want you to remember things about the project, first is when I started it, I got the right context to create it during my PhD, and then we add many things to the project. But one main key point was when I created the SFM data container in the project. It's where you see the sun in this picture. I'm going to explain later why it was a key element in this process. Also, you can see here that some fun project was added, like the support of spherical cameras in 2018, or that you can use also OpenMVG on ARM platform. So meaning that you can use OpenMVG on iOS or Android phones. So now we see that we have a lot of things in the project, but we don't really know how to use it. So now let's speak about OpenMVG and its framework and discover how you could use it for your own purpose. So OpenMVG is a framework, so meaning that you can build a pipeline where you are connecting together multiple binaries to achieve the goal you want. For example, SFM, localization, or others that you can build yourself. In order to build the OpenMVG library, I rely on 3 abstraction layers. One abstraction layer is for the I/O, the input-output, meaning that it's just dealing with data. The second one is a data layer, meaning that you have some data on disk, but you want to load them and play with them to do interaction. And finally, you need to have algorithm implemented to deal and mixing all those data together. And this is the implementation layer. It's where the main code core is living. If you look about some concept, there is many in OpenMVG. You can see there is a lot of libraries, like to deal with images, features, matching, tracking, etc. All those small libraries, you can use them independently, or you can just mix them together to do SFM. Abstraction on features and matches are handled with the data provider interface that you can see on top. And then you can use those data provider to just integrate your own data in the OpenMVG framework, but you just have to add your own custom layer to do that. So now let's look about how to use OpenMVG and deal with this SFM data container to build pipelines. So SFM data is a kind of backbone where you can just build your custom pipeline on top of it. So if you want to remember something about OpenMVG, I want to say that you have to remember this. This is the main thing in OpenMVG that allow us to do everything we do today. This SFM data container is an interoperable data structure, and it allows to store the relationship between your images, camera intrinsic and extrinsic, and the same visibility. The nice things about this data structure is like we can store it as a JSON blob, as a binary file, or an XML file. And why we do this is just because it brings flexibility for speed and transparency for the user. So meaning you can use it with the format you want, where you need. So for example, you can build a pipeline on top of this. So meaning that first you're going to just initialize your scene. So meaning you have some image as input, and you're going to say I'm using 10 images with a pinhole camera model, and I'm going to add 20 images with a spherical camera. So it's just an initialization of the process. It can be done in Python, in C++ as you want, because you can manipulate this SFM data backbone just as a JSON blob or a binary file. Then you want to do some processing. So you're going to read from this file, and you're going to do SFM or localization to just update some information about the camera poses or the visibility of the features and the 3D points of the scene. Then when it's done, you can say, okay, now I'm going to export or evaluate the data. So meaning that, for example, you can export the data to evaluate the quality to some GT dataset, or just export to a different multiple view stereo framework to compute a dense point cloud or a mesh. Now that you know that the SFM data container is easy and you can interact with it, let's look at some example of manipulation in OpenMVG. So for example, here it's an example when you're going to do 3D construction and then use this scene to do localization of new images. So from the left to the right, you can see that first you're going to use some binaries and combine them together on top of the backbone that is the SFM data container. So first you're going to link cameras, image and model together. You're going to compute features, compute matches, and then do structure from motion. Once you have the output of structure from motion, you can say, okay, now I want to localize some image on top of it. And so this image could be new image as rectilinear image or 360 image. But it's not all, like it's a pipeline, so you can do many, many things. You can just set some known camera poses as input with the language of your choice, because you can use this SFM data container as a JSON blob and just use Python or C++ to initialize this file. And after you can say, okay, I'm going to compute features and then triangulate the point corresponding to the scene by using this compute structure binary. And this compute structure binary can do either triangulation of a match file, so meaning that features that have been matched, or just look for features along the epipolar line. Now let's say that you want to do something and just mix features that are from different type. So meaning that you can say, okay, we're going to do 3D construction with SIFT features in the first place. And then I'm going to use the output of the SFM and just triangulate features from another kind. So here, for example, I'm going to compute Akaze feature in the second step and just triangulate the feature from Akaze given the camera poses I found with SIFT. It's a very simple process. And since it's a pipeline, it's important to know what is the input and what's the output you can manipulate. And to ease the usage of the library, we added some interface to just import some datasets that exist in the community and to export to other software of the community to have a kind of transparency with the community. So meaning that you can use ETH3D datasets as input and just export them directly to PMVS or OpenMVS to compute a 3D point cloud if you want. Or you can just import the datasets and just compute SFM with OpenMVG and directly compute the quality of the reconstruction to know if the camera poses are very close or very far. I will just do a side note about OpenMVG SFM pipeline to just illustrate what is different from what was existing before. For the incremental SFM pipeline, what was introduced with OpenMVG was to use a noise adaptative robust multiple view geometry estimation. So meaning that in most of the pipeline, people are using RONSAC, and for RONSAC, you need to set up a threshold. And you don't know which threshold to use. So you can say, okay, I'm going to use 4 pixels for this dataset. I'm going to use 6 pixels for this dataset. But somehow you never know how to choose this threshold to be the best one for your dataset. And with AC RONSAC that we are using in OpenMVG, this threshold adaptation is done automatically with statistics computation. Another thing that was introduced in OpenMVG is to be able to start the SFM process in an incremental way with n views. So meaning that often you start with only 2 views and it could be very unstable because you don't know which 2 images to choose. And in OpenMVG, we introduced a method to start the reconstruction with n views, and it's often more stable. For the global SFM pipeline, what was new compared to the previous work was to use image triplets to enhance rotation averaging robustness and to do convex translation using triplets. And as you can see, I put a side note because like a lot of global algorithms are not really used today for large-scale SFM, but now they start to be used for SLAM and produce a very nice initialization. So now let's take a look to the challenges and opportunities that the OpenMVG project is facing on. And here you can see some reconstruction made with a 360 camera, for example. So first, for the challenges or opportunities, it's hard to gather feedback. So for us, we just made a survey to the community last year, and we were able to gather a representative set of 50 answers. And as the result of this survey, we were very glad to see that the community is using OpenMVG since a long time. Most of our users are using it since more than 3 years. So it's really a commitment, and we were really happy to see that. It also gave us some meaningful information about the size of the dataset or the SFM pipelines that the community is using. And now we see that people start to use more than 1K images to just reconstruct an object or reconstruct a building. And often people just use to choose the incremental SFM pipeline because it seems to be the most accurate and the most stable in average. And we were also very surprised by the fact that 1/3 of our community is able to leverage OpenMVG and to create its own custom pipeline. So it's something that I list first. It was a dream, try to empower the community and just share knowledge. And as a result, we see that now 1/3 of the community is building their own pipeline on top of OpenMVG. So I think my dream is achieved somehow. I was able to just provide code and enable others to do something stronger. We found also interesting to see what was the request of the community. We saw that without surprise that somehow people want to do real-time reconstruction, so meaning that SLAM is of a lot of interest, and that dealing with laser or LiDAR is also of interest. One interest is also along speed, so meaning that everyone wants things to be computed very quickly. For the moment, OpenMVG focus more on accuracy rather than speed. So it's something that you can help and gather in the project and just help us to be faster. If we look about opportunities in a general way, here it's something that I want everyone to remember, because those points could be true for every project you're going to start or you want to contribute to. So first, what is very important is awareness. So you need to be known and you need to be used. So like if you are using an open source project, you need to say to the community that you are using it to spread the good news. The second point is accessibility. So you want to make your code available. And to do that, you want to share codes with your paper. So for me, I have done it during my PhD, and I would invite every PhD student to try to do so, to share code, or even better, to share it within the existing framework, to just foster the contribution. What is important also is to build a community, so meaning that you can support each other within a project. And as you can think, it's really hard to have people contribute to an open source project. And the goal with OpenMVG is to foster reproducible research, so meaning that I want an emulation between the community from the academia and the community from companies. What is also hard is to have everything very fast in your library. So meaning that sometimes you have to do trade-off between I want my code to be really readable by anyone. I want to have it very accurate, so perhaps it's not going to be fast. So every time you have to do trade-off. In OpenMVG, often we are taking the trade-off of having something very easy to read, easy to maintain, and easy to parse by someone else. And finally, what is also opportunity is the relevance of the contribution. So meaning that it's really hard to just keep contribution aligned with what people need, because it's changing every time. And one opportunity that the community can leverage today is to align the interests of the machine learning community and the SFM community. Because there is a lot of emulsion around, can we find better features, for example, for matching images? Here, I will just cite Mark Eder as an example. So Mark just finished his PhD and made many contributions in the field of mitigating distortion for spherical image. And he's now working on implementing his work to the OpenMVG library. And his work is mainly on mitigating distortion for 360 image. One way he found to deal with this distortion factor is to use the right interpretation for mitigating distortion. So if you look for a cubic representation, you extract a face on each side of the cube. If you use tangent images, you start to make the cube look like a sphere, and you can use different subdivision of the sphere. So what is the impact? If you use a cube, you're going to see that the inner and outer area is very large. So meaning that you're going to have non-uniform distortion when you want to extract a face of the cube. But if you look on the right, by using tangent images, you're going to have distortions that are less important. just because the separation between the inner and outer area around the circle is just smaller. So you're going to have less distortion. And why is it better? It's just because somehow it's like you think you want to adapt the representation of the image and use the existing algorithm. So meaning that if you have a good algorithm that run on existing image, but don't really extend to spherical image, using tangent image, you can still apply your algorithm and be able to see the output on spherical images. Here, I will just show you an example where you see on the left, SIFT just run on a spherical image. So as you can see, there is a lot of clutter, like some points should not be there. And just because you are running SIFT with assumptions that does not exist on the spherical image. At the right, you see that SIFT was run on tangent images and merged back to the equirectangular image. As you see that there is less points, they are better aligned with the image. And our point here is like using SIFT on tangent image and would be better to do spherical image matching and SFM. So what's next for OpenMVG also in some other direction? Like we want to be more scalable, so meaning we want more speed for users. And we want to do that for image matching, for example, or new SFM pipelines. And one of the ideas we're going to explore is to use stellar SFM, so meaning that you can use N-view initialization to do structure for motion or global structure for motion. And we would like also to gather the help from the community and allowing interest of the machine learning and computer vision communities. Now let's look about how people are using OpenMVG, look about what are the alternative of OpenMVG, does there is other frameworks, and let's gather around the take-home message. So those two examples show how OpenMVG can be used by some laboratory to just build 3D cities from image collected by airplanes or from the ground. Here is one example with a digital humanities laboratory. On the right, you see an example where OpenMVG is used inside an Android app called Scan3D. So meaning that SFM can run on your phone directly with the image you can capture. Some other image that were totally unexpected is like OpenMVG can be used either for forensic reconstruction, so meaning that with human heads, for example, or even to try to save animals and to do 3D printed prosthetics. So meaning that you can take image of injured animals and after add a prosthetic that perfectly fit the nose of this toucan, for example. Some other example can be done in the field of surveying or science dissemination. So for example, for this survey, one company called 8K Images, 8,000 images of a castle, and they were able to build a very, very nice model of the castle to do explanation about the castle. As you can see here, you can see all the details about the roof, about the side of the castle. Here are some other examples where you see with green dots the camera poses, and on the right, one part of the top of the roof. You can notice that there is a lot of details and that you see a lot of very good alignments of the point cloud. Here is another example where you can see an archaeological survey for stone degradation monitoring. So here is also a big data set that was used by the community to just share a reconstruction of an environment. Now, if we look about other alternatives, like there is a lot of projects to do open source SFM in the web. But here I was trying to do a classification to show that it's hard to gather contributors and contribution in this field. So meaning that our community is very big, like there is a lot of people working on 3D reconstruction, SLAM, SFM, but somehow we don't all share content and knowledge to the community. And OpenMVG is one of the projects that is gathering most of the contributors today. And perhaps it's because our project is really open, meaning that we want to share knowledge and we want to just share implementation of state-of-the-art. One other very important point is to have continuous integration, as you see on the right. So meaning that everyone that want to do a contribution, you need to directly tell if the code is compiling, if the code is running nicely, because else you're gonna just give feedback and say, hey, your code is not compiling, please do that or this. So what is very important is to give feedback as soon as you can to your users that the code is going to be good or that some modifications are required to be integrated in the library. As a take-home message, I would like you to remember that OpenMVG is a flexible framework for reproducible research. So meaning that we have implemented a lot of state-of-the-art algorithms that you can use directly. I want you to remember that there is also easy interoperability. So meaning that the SFM data container used in OpenMVG is very, very powerful and allow you to do customization in a very, very easy way. There is a lot of convenient import and export functions, so meaning that you can import datasets, do evaluation compared to them, or you can export to other third-party tools. And finally, I want to say that this project is very community and knowledge focused. So it's like together we can achieve more. So please consider to join the project if you like 3D construction. And I would like to give a very, very big thank you to the OpenMVG community because the project will not be there without them. So this is the end of my talk. And now feel free to ask me questions.
Okay. Thank you very much for Dr. Pierre Moulon's fantastic talk. And Pierre has set up a very good example for all the PhD students who should share their code, make their code public, and for the community. And we have some questions from the general audience. Let's say the first question is, do you want to, I believe right now you have some functions in Python already in OpenMVG and MVG. And one audience is asking whether you are planning to implement a full Python version of OpenMVG, or is there any plan to add other direct method and, for example, dtime, LSD slime, and to OpenMVG?
Yeah, so my answer is going to be, if you want something, come in the project and help us to make it true. So it's like, there is an automatic wrapper that exists to just make C++ code available from Python. So we could try to play with that together and see how far we can go. Using the SFM data container as a file that you can log on disk and just interact with it, it's already a first step where you can mix C++ and Python pipelines together. But I'm very welcoming. So it's like, if people want to help to build Python wrapper or just extend some part of the interface, I will be really happy to help. And one other point I want to say here is like somehow we see that there is different language to write computer vision. Like you can use Python, C++, Java, whatever. And one of my other dreams is to say you write something only once and you just translate it to the language you want. So it would be a very nice dream that one day we could achieve. So meaning that you write an algorithm once and after you can just export it to any language.
Okay, great. Another question is, so how do you maintain your project over time? I think I can merge those two questions together from the audience. And do you maintain your OpenMVG and other open source framework at work, or you just use your own free time on weekends and night to maintain them? How do you maintain your OpenMVG? Sorry.
Yeah. Thank you for this question. It's like often open source is done on free time. And here I'm doing OpenMVG on my free time. And as you can see, the release spread over, like now it's 1 year, over 1 year. Yes, it's taking time to maintain OpenMVG open source project. First, it's because you have to concentrate, you have to write code, and you have to keep a good work-life balance. So meaning that you will not spend the entire night on coding. You need also to rest. So it's really hard to maintain an open source project in time. I'm very glad that I got a lot of major contributors in the library that really helped me and empower the project with really nice tools. I could cite them, like Romuald Perrault and Romain Janvier are two big contributors that really helped me. So at the end, I would say that to maintain an open source project in time, it's very nice to have some guidelines. So meaning that the credo, vision, and mission I used to just be sure that you are sticking to what you want to build. You have to welcome any contribution and to be fair to anyone. So meaning that you can have questions, you can have contributions, you have to welcome everyone with the same spirit to just build and foster a very good community.
Okay, and another question is, does OpenMVG provide ways to measure the accuracy and uncertainty of different SFM algorithms?
So I don't provide uncertainty. There is one tool that is called Evaluate Quality to just compare camera position in rotation and translation for many GT datasets. But for the moment, we don't compute uncertainty. We could add it because it's a function of Cirrus Solver, or we could use other tools. And here again, I would like to welcome anyone to do this as a contribution to the library.
Okay, and how do you manage the different versions of C++, C++ 11, 14, and later many other versions?
Yes, so for the moment, OpenMVG is very conservative, so meaning that we are using C++ 11 as a standard. And the main reason is because we want to keep up with compilers that are going on phones. So meaning that if you want to use OpenMVG on iOS or Android, most of the compilers for those platforms accept C++ 11, but they don't all accept higher standard. So for the moment, we are just using C++ 11, and we are okay with that. But we think that one day we're going to need to switch to access to more features.
Okay, so some follow-up questions from me is, you mentioned you are paying attention to the machine learning community and the geometry structure from motion community, and yeah, does it indicate in the future you will include many other open source code and for deep learning based solution for SFM, or in another thing, do you think in the future SFM based on deep learning will mainly play a more important or even dominant role in the future?
Yeah, this is a very good question. And for me, what matters is to keep what is working the best in each field. So meaning that there is geometric methods that are working very good, and there is some machine learning algorithms that are working very good, and we should just mix them in a very smart way. So meaning that if there is very good machine learning features detector, we should use them because they could be better than SIFT or Akaze. And on the other part, regarding if SFM going to switch to be totally done with machine learning, perhaps it's going to be done one day. I think what is really hard is to deal with wide baseline. So meaning that all the machine learning work we are seeing on SLAM and SFM are just not working really great for the moment for very wide baseline. They are working great for very small motion. And one of the opportunities is how to work with very large, high resolution images. So meaning that a lot of machine learning models are ingesting very small resolution images. So it's like how we can go to the next step and just use very, very large resolution images. Because if you think today, when people are doing a survey of a building or an object, they are using their DSLR and they are taking very, very large, high resolution images. So it's like how you can use those very large resolution images inside your machine learning models is also a very good opportunity, and how to mix them with SFM is another good opportunity.
Yeah, that is great. That is great answer. And I be in the morning actually in Daniel Cremers talk, and he also mentioned in current SLAM or structure for motion solution, traditional algorithms, geometry based algorithms still in some way plays get better performance than the machine learning based algorithms, for deep learning based algorithm, especially for the trajectory estimation. So I would say probably your answer is pretty straightforward and decent. Is you probably in the future a combination between these two, and geometry based and machine learning based would benefit each other in a long time, and is unlike some other domain, and probably deep learning algorithm is already taking over all all the best performance in some tasks like segmentation, detection, those things. So probably for the last question is for OpenMGV, and what do you think? You mentioned in one of your slides, OpenMVG attracts most contributors. What do you think is the reason behind it, that OpenMVG attracts more contributors compared with others? Is because it provides more function, or is more open, or provides more flexibility?
Yes, so for me, I would say the transparency. So first, like we welcome anyone in the community and we try to maintain feedback with them. So it's like if you open an issue on GitHub, we try to give an answer, and it's taking a lot of time, but it's rewarding that if one day someone is want to do a contribution, you help and guide him. It's very a nice feeling. So what I would say why there is more contributors is for this, just the hard work we are doing to be a community and welcome anyone. And the second one is what you cite. It's try to implement a lot of algorithm and be sure they are running as they should with test-driven development. So meaning that every time there is some features, you can directly know how to test them by looking to the unit test, or you can try to implement your own method and to compare with some existing algorithm.
Cool. So probably there will be more questions from the audience, and we are right at the time. So let's send to Dr. Pierre Moulon again, and for his great talk, and maybe you can interact with the audience on the YouTube channel, and maybe they have more questions.
Thank you.
Okay, and we end up today's talk, and in tomorrow, and we will have the same schedule, and starting from 10 a.m. in Eastern time and 7 p.m. in the Western time. And well, I also repeat the whole time, different time zone in 4 p.m. in European time and 10 p.m. in China time, and we will start our tomorrow's workshop and the same schedule, and from 10 to 5, from 10 to 5 in Eastern time. From 7 to 5 in Western time. We will have two challenges. We will have one challenge, localization challenge in the morning, and with another several speakers, and another several speakers in the afternoon. And so we will meet tomorrow again. Okay, thank you very much for all the talks. It's really impressive day with so many fantastic talks.
Yeah, it's great.
Thank you.
Yeah, you did really a great job. Thank you so much.
Thank you, Vincent. Thank you for your group support. Yeah.
Yeah. Okay, see you tomorrow.
See you tomorrow. Yeah.